friends. So from today I am planning to upload the videos on data structures. So in today's session we will see the introduction of a data structure. That means what is a data structure and what are the different concepts covered in these data structures. Right. Right. So data structures. What is meant by a data structure? So the name itself indicates data structure. So that means organizing the data in the memory is called a data structure. So there are different ways to organize the data in the structure. So one example we have seen in the C language, that is arrays. So array is also a collection of elements. That means a collection of memory locations. So because in the memory locations we are going to store the values, right? So in that the structure of data is a sequential. That means one after another, right? So it occupies the contiguous memory locations. So it is a collection of elements in that contiguous memory locations. So that way the data is organized using the arrays data structure. So finally the definition of data structure means organizing the data in the memory location. So how many ways we can organize the data in the memory location, right? Now let us see how many types of data structures. So there are two types of data structures. So one is primitive data structure and another one is non-primitive data structure. Primitive data structures and non-primitive data structures. Coming to these primitive data structures, we have already seen those data structures. See, so these primitive data structures are our primitive data types. Yes. So int, float, character, double, and pointer. Right? So all these comes under primitive data structure. Non-primitive data structure. Now, so these we have studied in C language. These we call them as primitive data types. Right? Integer, float, character, double, and pointer. It's a single memory location which can hold the value only. Right? Next, coming to this non-primitive, it's again divided into two types, that is linear data structures and non-linear data structures. Linear and non-linear. So linear means a sequential, that is nothing but a sequential. So non-linear, which is not a sequential, that we can call it as a random, right? So this is a sequential. This is random. That means in this all the data will be arranged in sequential manner. Here the data is arranged in random manner. Now what are the types of linear data structure? So first one is arrays, lists, stacks, queues. These four comes under linear data structure. Non-linear data structures, only two categories are there. One is the trees and graphs. Trees and graphs. So again, so this we have seen in C language, arrays, the sequential elements, right? So now we have to see about the list, stack, queue, trees and graphs. So how the data is arranged in list, how the data is arranged in stack, how the data is organized in queues, how the data is organized in trees, and similarly graphs. So these are the different types of data structures, right? So in the list there are a number of categories. So under this, one is single linked list, double linked list, circular linked list. LL means linked list, right? So here in trees, we are going to discuss about binary trees, binary search trees, and there are a number of trees, right? So we will discuss in those sessions, right? So finally, the data structure introduction is this thing. So primitive and non-primitive, right? And now there are common operations can be performed on these data structures. Operations. So the major operations which can be done is searching and sorting. So we can search an element in the data structure, right? So in the list, we can sort the elements, and then see, we can insert the new element, right? Insertion. Similarly, deletion. We can delete one element. Next, updation. So we can update the elements. So that means we can replace one element with another element, right? So these are the common operations to be performed in these data structures. So we can search an element in linked list, we can sort the elements of a linked list, we can insert an element into the linked list, we can delete the element from the linked list, and we can update the element in the linked list. So these are the common operations. So I will write here common operations on data structures. So this is the common operations on data structures, right? So we are going to discuss about the list. In the list, we have to apply all these operations, and then we have to see the stacks, and we have to apply all these operations. We have to cover the queues and all these operations. Similarly, trees and graphs, right? So hope you got an idea about these data structures, and definitely I am going to upload the videos on all these concepts, right? So let us stop here. So from the next session we will start with the arrays. So our arrays are already seen in our C sections. So we will see the advantage and disadvantages of arrays, right? And then we will move on to the list. In the list we have to see all these three. So in the coming sessions we will cover all these concepts, right? So hope you got an idea about this introduction of data structures. Seeing the introduction to data structures. So in that we have seen the two different types of data structures. One is the primitive data structures and the non-primitive data structures. So we have already seen the primitive data structures, that is the primitive data types in C language. Now we will focus on non-primitive data structures. So in that non-primitive data structures also, it is categorized into two categories, right? So one is non-linear and another one is a linear. So in the linear data structures, we have seen that all the elements are organized in a sequential order. So the best example for this linear data structure is arrays, right? So arrays, stacks, queues, linked list, all these comes under the linear data structures. So in that we will see one by one. In today's session we will start with arrays. So this arrays concept is already covered in our C language. So just we will revise the concept of array. So here the array is a collection of elements which is of a similar data type, right? So we can store a multiple number of elements under the same name, that is called array, that we have seen in the previous sessions, right? So now here how the memory is organized for the array elements. So here the memory is occupied in a continuous way, right? So the elements will be organized in a continuous memory locations, and also there are different operations we can perform on arrays. So first one is, so we have seen the basic operations that can be performed on these data structures in the previous session. That is, first one is like searching. So we have already seen the searching algorithms on array elements. So in that searching we have covered the linear search and the binary search. Another one is sorting. This is also a very important operation that can be performed on arrays. So here also we have seen bubble sort, right? Merge sort, selection sort, right? So there are different sorting techniques. So those we have covered. And then insertion. That means inserting an element into an existing array. This is also we have seen. And the deletion. So this is deleting an element from the existing array. So this operation also we have seen. See. So all these are the basic operations that can be performed on data structures. So I will provide the links of all these videos in the description. Right. Now we will see. So I don't want to repeat everything. Just I will give you the links in the description section, so that you just go through and you just follow that. So after these operations, there is a sort of advantages and the limitations of using these arrays. Now we will see those advantages and disadvantages. First we will go with the advantages. So what are the advantages of using arrays? Advantages of using arrays. So first one, it consists of similar data elements. So this is one of the advantages. Sorry. It consists of similar data type elements. So n number of elements can be stored in a single name. Next, so we can access any element. So we can access any element in the array with the help of index value. So with the help of index value. Right? That's why we are using the index. Right? So this is one of the advantages. We can access any element based upon the index value we can retrieve. Next, it is suitable when the number of elements are already known. So before applying the algorithms or before applying the application, before using these arrays, so we have to know the number of elements that this array can be used. So then only this is suitable, right? Next, another major advantage is this is used in implementation of the other linear data structures like stacks and queues, but not the list, right? So these are the simple advantages over using these arrays, and there are also the limitations of using these arrays. See, we will see the limitations. What are the limitations? So I will just erase this one. Advantages: similar data type elements, and one advantage is random access. So we can access any element from the array, that is with the help of index value, right? And when it is suitable, whenever we know the number of elements that array should have. If we know that the number of elements, then only these arrays are suitable. Next, disadvantages. So there are a number of disadvantages over using these arrays. So first one is, this is the major disadvantage of using arrays: static memory allocation. Static memory allocation. That means during the compile time itself, we have to specify the size of the array. So at the compile time itself, we have to specify the size of array. And there is no possibility to change the size of an array during the runtime, right? So that means if the array is declared as 10 elements, if the array is declared as 10 elements, there is no possible to increase the size. There is no possible to increase the size. And if the array is initialized with a more number of elements, and if we are using only the 10 elements, if 10 elements are used, then memory of 90 elements is wasted, right? Yes. So if we declare array with a maximum size, and if we are using only a few elements, then the remaining elements, the memory occupied for the remaining elements is wastage. The memory is wasted. So this is all about the static memory allocation, because of static memory allocation. So during the compile time itself, we have to specify the size of the array. During the runtime, we can't modify the size of array. Right. Next, the second drawback. The second drawback is insertion and deletion. This is the another drawback. So inserting an element and the deletion of element is expensive. Expensive means it requires a more complex loops. It involves in more complex. So see, if we use this insertion, let us take a of 0, a of 1, a of 2, a of 3 and a of 4, right? So here, if you insert an element, let it be 10, 20, 30, 40 and a 50, and if you insert 5 at a of 0, first of all we have to move, see, a of 0, a of 1, a of 2, a of 3, a of 4 and a of 5, right? So let it be a of 5. First we have to move every element towards its right position. So this element should be moved here, this element should be moved here, this element should be moved here, this element, and similarly this element. So 10 will be moved here, 20, 30, 40, 50 and finally 5 should be inserted here. So this is the process to be done if you want to insert an element at the beginning. So it is somewhat expensive. It takes some more time. So in terms, the expensive in terms means time taken, time complexity. Right. Now coming to the deletion. Deletion. Right. So this is all about insertion. See. Right. So if you delete 10, if you delete the 10, right, if you delete the 10, now see, you have to move everything towards its left. We have to move everything towards its left. So 20 will be moved to F0, 30 will be moved to F1, 40 will be moved to F2 and similarly 50 will be moved to F3. Right, here we are not deleting the elements, just we are moving the elements. That is the main drawback of arrays. So we are not removing the memory space. Here the memory occupied by the 4th index and 5th index are wasted. Right, so that is the main drawback of these arrays. So one is the static memory allocation, another one is this insertion and deletion. The wastage of memory is more, right? And due to these disadvantages, we are not implementing the list concept by using these arrays. So we will implement the list concept using the linked list, right? So hope you understood the advantages and disadvantages over these arrays. And once again I am saying that we have seen all the operations of arrays, that means searching, sorting, insertion and deletion. So I will provide the links of those videos in the description section, just to go through that. And mainly these are the disadvantages and advantages over arrays. So we will stop here. In the next session we will go with the implementation of linked list, right? Right. What is the difference between the array and linked list? So in the previous session we have discussed that in array the elements are stored in contiguous memory locations, right? So here in list that is not required. That means the elements need not be stored in contiguous memory locations. The elements can be stored in any location, but as the name itself indicates, there will be a link between one element and the other element. So we have to establish a link between the one element and another element. That's why these elements are need not required to occupy in the contiguous memory locations. Right. For this we need to create a structure for a node. So here an element is represented as a node. Element is represented as node, because here a node consists of two fields. So previously in the arrays, element means only one field, that is a value. So let it be either 10 or 20 or 30, right, and so on. So this is called elements. But here node means it consists of two fields. First one is data field, second one is address field, address or pointer field or a next field, right? In this data we have to insert the value, that means this type of data. So it may be integer, float, character, string or anything else. The actual value will be stored in data. What about this field? The additional field. In this additional field, the name itself indicates it will represent the address of next node, the address of next node. So this is the link of another element. That's why the elements need not required to occupy the contiguous memory locations. So different elements can have a different memory locations, but here we are just establishing a link. So one element, in every element there will be a one field called address field, which consists of address of the next node. So that's why we have to consider it as a node rather than element. So how to represent this node? Representation. How to represent a node? So a node is represented in two fields. See, so this is the data field, this is the next field. This is the data field, this is the next field. Then if list contains two elements or three elements, that means three nodes. So if list contains three nodes, see, let us take 10 and the memory location is 1000. 20, the memory location is 2000. 30, the memory location is 3000, right? So three nodes, so 10, 20 and 30. The address of 10 is 1000. The address of 20 is 2000. The address of 30 is 3000. So how to represent these elements? See, 10, 20, 30. So here, this is the, we know that this is the data, this is the address of next node. So here we have to store the address of next node. What is the next node? 20. What is the address of 20? 2000. So here the 2000 will be added. Here, coming to the second node, 20 is the value and the corresponding next, that means address field, it will save the address of next node. What is the next node? 30. So what is the address? 3000. So 3000 will be stored here. Coming to the third node, 30 is the value and what is the next field? That means address field. So here 30 is the last element. So obviously it will be null. So that means the last element, the address field will be fixed with null. So it indicates the list, the end of the list. It indicates the node is end of the list, right? And this linked list will be having the head and tail. The two other concepts, that is head and tail. So head will be the starting element, tail will be the ending element. Head, tail. The name of the node, right? So head and tail are name of the node. The first node name is head, the last node name is tail. So if it is having some 40th element with 4000 address, again we have to use the another node, that is 40, and here we have to insert 4000. Here it will be null and the tail will be here. Hope you understood this one, right? So a node consists of two fields. So far we have studying regarding these elements, only the element, but here we have to treat it as a node because it consists of two fields, right? So before going to the program, first we have to create a structure for this node. So if it is an element, we can directly write with a data type. We can declare it with a data type, that is int or a float or a double or anything else, right? So by using the primitive data types, we can declare the variable for assigning the element. But coming to this node, how to declare a node? So here it is having only one element, so we can directly use the primitive data type. Here it is having a two fields, so for every node there will be two fields, right? So how to declare this node? So we had a data structure which can accept multiple elements of different data types. So here the data can be anything, that means any data type, right? So it can be integer, float, character or a string, whatever it may be, right? So second one is purely address. So we know that if in order to store the address, we have to create a pointer. So this is a normal primitive data type. This is a pointer variable. So we have studied in a C language, it's in order to add two different elements with different data types, what we have to implement? We have to implement the structure, right? So structure is a collection of multiple elements with different data types. The same thing we have to apply while declaring a node, because it consists of data and data. First we will declare a node and then we will insert the elements, or we will create the list and then we will display in this session. Hope you understood the basic representation and how the node is represented and how the node, what are the fields available in this node. Now let us see declaring a node. Yeah, here we will write data and next. We can simply write struct node. We have to create two things. One is data, next. So simply we can write an integer value, int data. Second one is a pointer which is pointing with the self node, right? So which is pointing the self node. So we have to create struct node star next, right? So this is the declaration of a node. So here we have to declare a variable, that is some star new. Okay, see, this is for data, and next is a pointer variable, but it is a self pointer because this is also a field of the same node. It is also a field of same node. So we have to write a pointer variable of the same node. So that is called the struct node. So if you want to declare a variable, see, if you want to declare a variable, so just you right. So let it be consider this structure. So into data float percentage. Let us take this one. So if you want to create a variable, structure variable, what we have to do? So we have to the syntax for structure variable is struct node some s1, right? Struct node s1 is used to declare a structure variable. See, so s1 will be consists of data and percentage, isn't it? Right. Now here the same node must consist of a pointer. So how to create a pointer variable? Struct node star p. That's a pointer variable, pointer structure variable. So the same way we are using the same thing. Struct node star next. That means self pointer, the pointer, right? So this is called self-referential structure. The name itself indicates self-referential structure. So reference means the pointer. Self, that means which represents the same node, which is a part of the same node, right? And here, instead of using the normal structure variable, we have to use or we have to declare the pointer structure variable, because if it is a normal structure variable, see, hope you understood this one, right? Self-referential, because one is data, another one is next, which is also representing the same node. So for this we have created this one. So normally if you create the structure variable struct node new, struct node new, it will be having a data next. Excuse me. Next. So here there is a problem, because here data is a value whereas next is a address. So we can't store the address in a normal variable. So we can store the address in pointer variable. So for this purpose, we have to create the pointer variable. So all the structure variables for these nodes are pointer variables. Star new. Hope you understood. Don't get confused. So if it is normal structure variable, that variable will be having two fields, data and next. Data is normal data type and next is a address. So a normal variable can't store the address. So in order to store the address, we have to create the pointer. So that's why we are creating the pointer variable. Now this pointer variable will be having the data and address. So this is possible, right? So next, after creating a structure, we have to allocate the memory. So we have seen the drawback of memory allocation is the main drawback for arrays. That is the static memory allocation. So here for every node we can have a dynamic memory allocation by using malloc function, right? Next we have to allocate the memory dynamically. New typecast, for which we have to allocating the memory. Struct node star pointer variable. This is malloc. How much memory should be allocated? Size of operator is used to retrieve the size occupied by that particular data. Size of struct node, right? So this is for dynamic memory allocation. So this statement is used to allocate the memory dynamically. So for every node, before it's getting the value, we have to allocate the memory dynamically. So this is first a typecast. What type of for what type of data type we are allocating the memory, and a malloc function is used to allocate the memory. So how much memory should be allocated? That means the size of struct node. So the size will be calculated and that will be allocated to the new. Here new is a variable. New is a structure variable, structure pointer variable. So here new will be having both data and next. Hope you understood this one. Right. So this is all about the introduction. Now we will create a list and display the list. So as I have said that every list will be having the head and tail. The head will be the starting position and the tail will be the last position. So initially we have to assign the head and tail to the first element, because if there is a one element, we have to assign the head and tail to the same element, same node. If you keep on creating a list, if you keep on adding the list, we have to change the tail. Okay, hope you understood. So if there is only one node, that itself is a head and tail. If it is having a two nodes, the first one will be the head and the second one will be the tail. Let us see. So this is a structure. So I will write the structure here. Right. Creating a list. So if you want to create some 10, 20 and 30, see, First we have to allocate the memory, and then we will get the 10, and initially it will be null. 10 and null. Now this will be the head, this will be the tail. Okay, head, tail. New. Next, second iteration, the new will be this one. In the second iteration, the new will be this one. That means whatever the elements we are inserting, that will be the new. Now see, here head is 10, right? Tail is 10, null. The address position is null. Now it is not an empty list. It's not an empty list, right? It is a list with one element. So head will be fixed. Head will be fixed. Okay. Now coming to the tail, what we have to do? We have to establish the link first. Establish the link first. So what we have to do? First, tail of next. So here head and tail are also nodes, right? So similarly star new, similarly star head, comma star tail. So head and tail are also the nodes. Tail of next, that means the tail of next, this one will be assigned with new. Hope you understood this one. Tail of next. Here tail is this one, 10 and null. Tail of next, and that means the address part of a tail will be assigned with new. So let us take the address positions 1000, 2000, 3000. Now what is the new address of new? 2000. So here it will replace the null with 2000, right? Next, tail should be changed. Now the tail will be new. The tail will be new. So that's why again we will have the second element, that is 20, and now it is null. Okay, hope you understood. Initially the new, it's a new, the new will be some garbage and null. So whenever you are taking 10, this garbage value is replaced with 10, and the address bar will be, address position will be null. So head and tail will be assigned to new initially, right? See, and whenever you are inserting the 20 element, first we have to establish the link. So this is very important. First one means establish the link. Next, update value. Sorry. Create a node. Okay, create a node. So tail is equal to new, this one. So here the tail is replaced and it is assigned here. Okay, so head is having the two fields 10 and 2000, and the tail is having the fields 20 and null. Now once again in the next iteration, the new will be the third element. New will be third element. Now again, first we have to establish the link. Tail of next. Tail of next. So this is the next. This is the data. Right? So tail of next is equal to new. New means 30. Right? 30 of 30. The memory allocation, the memory address of 30 is 3000. So that will be assigned to tail of next. So this is very important. We have to follow this thing. This is the most important. First establish the link. So 3000, and then tail is equal to new. Assign 30 null, right? So tail will be assigned here itself, right? So this is for creating a list. So we have to apply this in loop, so that how many number of elements will be created in that list, right? So I will write the program and I will explain the logic. I mean, we will trace that. First, let us write the code and we will trace it. So after creating this one, we have to use a memory location, dynamic memory location. Some new is equal to struct node star malloc size of struct node, right? So new, every time the new will be allocated. See, okay. So we'll keep this in loop. So for every time the new will be having, so new struct node star malloc size of struct node, right? So once the memory allocation is done, then we have to take the value. Scanf some %d value, read the value and assign the value to head. New of, so here it is a pointer, right? This is a pointer structure variable. So we know that the pointer structure variable accessing the data members is done by using the array. So if it is a normal structure variable, that variable we can access the members by using the dot operator. If it is a pointer structure variable, it should access the members by using the array, I mean the arrow mark. Data is equal to a value and new of next will be null initially, right? Now we'll check the condition for head, if it is having the single element or multiple elements. So if head, so head is equal to null. So we have created the variables, but we are not assigned. So if head is equal to null, what we have to do? Both head and tail should be new. Head is equal to new because both will points to the first element itself. Tail is equal to else condition. That means if it is having multiple elements, right? So then we have to follow the same procedure. That means first we have to establish the link and then we have to change the tail. Tail of next is equal to new. This is for establishing the link. Tail is equal to new, right? So this ends the code. Now just write printf y to continue and to exit. Flash stdin, because we have to read the character. So read the character scanf %c $c h. Close the while loop. Whenever ch is equal to y, continue the loop until ch is equal to y. Whenever you press n, automatically it will be exited, right? Hope you understood this one. This is for creating the list. creating the list. So if you trace this one, let it be some 20 with 1,000, 30 with 3,000, some 50 with 5,000. The memory locations. Okay. Now see, first value. So just above this loop, you just declare the value, declare the ch. I have skipped everything, right? Just I am writing the logic. First, take the value. So value is equal to some 20. Value is equal to 20. Now new of data. So new consists of data is equal to value. That means here 20, here it will be null. Next, head is equal to null. So initially we have declared this head and tail, but we are not initializing. So automatically head will be consisting of some garbage and null. Similarly, tail will be also having some garbage and null. Tail is also having the garbage value and null. Now see, if head is equal to null, yes, head is null, then head is equal to new. So head will be again 20 and null. Similarly, tail is also pointing the same. Head and tail will be 20 and null. Now if part is if part is executed, so else will be ignored. Automatically y to continue and to exit. If you press y, again it will check the condition ch is equal to y, so it is true. Again it will go with the new. Now the new will be this ends with the first iteration. So now there is a node 20 and null, and the new will be the next node. That means the memory will be allocated for the new, and scanf value, some value 30 will be assigned. So 30 will be assigned to new of data. That means a 30 here, and next is null. Here it will be null. Then if head is equal to null, so this is the head and tail. Right? This is the head and tail. Okay. Now head is not a null because head is pointing the first element. Obviously, then this condition will be failed, else part will be executed. In the else part, tail of next, that means null. Here it will be null, so that will be assigned with the new. So new address is 3000, so that will be assigned to tail of next. So here null will be replaced with 3000, and then tail is equal to new. Tail is equal to new. So obviously one more node will be created. So here 30, here null, and the tail will be replaced with this one. Right? This ends. Obviously again y to continue and to exist. If you continue with y, it will go with here, it will check the condition, it's again true, again a new. That means iteration completes. Here again the new is a memory allocation is created, and value, scan value, so 50. So 50 and null. Right? If head is equal to null, head is not a null because it is pointing with some element. So this part will be ignored, else part will be coming. Tail of next, here tail is 30. Right? See, 20, 3000, 30, null. So this is the head, this is the tail. So tail of next is this field. So this is the next field, right? Is equal to new. What is the address of new? So address of new is 5000. So this null will be replaced with 5000. And then tail is equal to new. So obviously a tail will be created here with a 50 and null, and the tail will be removed here and it will be assigned here. Right? Next, printf y to continue and to exit. If you press n, while checking the condition ch is equal to n, that means a false. Automatically it comes out from the loop. So finally the list will be 20, 30 and 50. So 20, the node 20 is pointing the address of 30, and the node 30 pointing the address of 50, and the node 50 is having null because the node 50 is the end of the list. Right? So hope you understood this one. The creation of a list, a simple thing, a creation of a list. And then the second one is we have to display the list, display the elements of a list. See. So we'll see the display elements and we will stop here. We'll see the display and we will stop. In the next sessions we will go with the next further operations. Display. See, here we have created already some nodes 23,000 pointing the next node, that is 35,000 pointing the nodes 50 and null. So this is the head, this is the tail. Right. For display, so we have to move the head to the empty. Right. So till the head moves to the empty, we have to display the every node. So for that we will take one more variable called temp. Temp is also similar to head and tail. So first we'll assign the head to temp. So obviously the temp will be here. The temp will be here. Next, write down the loop while temp not equal to null. Temp not equal to null. Right? What we have to do? We have to print everything. Printf %d temp of data. So initially it will be head, so temp of data 20 will be printed, and next we have to move the head to the next one. So we can't move the head to the next one, so that's why we are assigning the head value with a temporary variable temp. So temp is equal to temp of next. Close this one. Simple thing. So this is the only logic for displaying the list. So let us trace here. So first temp is equal to head. Here temp will be this one. Next temp not equal to null. So true. Temp of data will be printed here. Next temp is equal to temp of next. So now temp will be temp of next. That means it is pointing with this one. Temp of next. That means this 3000. Address of 3000 means this one. Now again temp not equal to null. It will check with the null condition. So it is again true. So temp of data. That means 30 will be printed. And again temp of next. So it will be assigned with this one. Now again temp not equal to null. Yes. So temp of data. So 50 will be printed. And the temp is equal to temp of next. There is no other node. So that's why it will be assigned to null. So temp not equal to null. But here the temp is null. See here the temp is null. The condition fails. Automatically it will stop. So we are having the 3 nodes with 20, 30, 50, and here also we are displaying the 20, 30, 50. Right? So here we have to create a temporary variable, and just we are moving the temporary variable to end of the list. So whenever the temp is equal to null, automatically we can stop the loop. We can terminate the low. Right, hope you understood this one. So don't get confused, it's a very easy concept. So a normal element means storing a single value, but here the list consists of a node which is having two fields. One is a data field and another one is an address field. So here a variable consists of a multiple elements with the different data types is represented as a structure. So here we have to create a structure, and in that structure a normal variable can't store the address, so we have to create the address, that means a pointer variable which represents the same. That's why we are using the self-referential structure. And also the variable should have both the value and the address, so we are creating the variable as a pointer variables for representing a node, right? So here the main advantage is the elements can be stored anywhere, because we are establishing a link between one element and another element, right? And also we are using the dynamic memory allocation for the allocating the memory. So hope you understood. So we have covered the list introduction and how to create a list and how to display the list. Now let us see the insertion of an element to the existing linked list. So linked list. So here we will see the three cases. The first one is insertion of element at beginning. At the beginning, right? Second case, insertion of an element at ending. Similarly, insertion of an element at specified position. So these three cases we will see now, right? So one is inserting an element at the beginning of the linked list, and the second one is the insertion of an element at the ending of the linked list. Third one, we have to specify some position and we have to insert the element at that particular specific position, right? Now let's see one by one. Let us take one example and then we will see that. Right. Now, so just to follow the previous session for creating a list. So let it be, first we have created a list with 4 elements. I'll give you here. So first element, second element, third element, fourth element. See, every element, every node is having 2 fields. One is data. Let it be 20, 30, 40 and 50. So the memory occupied here is 1000. The memory address of the node is 1000. This is 2000. This is 3000 and this is 4000. So we know that every node consists of the second field, that is a address of next node. So here 2000 will be saved here. Right? So address of next node. Here the address of 40, that means 3000. Here the address of 50, so 4000. What about the last element? We know that the last element, the address will be null. So if any node consists of the null at the place of address, that we can consider it as a last element of a list. Right? So this is a head. This is a head and this is a tail. Now, for everything we have to first take the node and then we have to insert it. So for that, for every node we have to allocate the memory by using dynamic memory allocation. Right? So here we have to use the dynamic memory allocation for allocating the memory. So which overcomes the drawback of an array, right? So in the three cases, insertion at the beginning, insertion at the ending, insertion at the specific position, First we have to allocate the memory for the node and then we have to read the value. So this is a common statement for everything. So for in the three cases, so strut node star. So this is a memory allocation. So we have to use a malloc for memory allocation. So we have to specify the size of strut node. So that means how much memory to be occupied. So that will be as allocated to the element new. Now, so first insertion at beginning. Right. Insertion at the beginning. Now, see, first let us write the output so that we can easily identify. See, so 20, 30, 40, 50. This is the last element, so null. This is the 4000. This is the 3000. This is the 2000. Right? And if you add the element here, it will be 10, and this will be 1000. So this will be the head, this will be the tail. So first this is the output, right? So after inserting a node to the existing list, so which is 10, right? So the element is 10. So 10 will be inserted at the beginning, and for this node the address must be the next node address, that means 20. So 20 address will be here. See, it will be some 500, some 1000. So this is the address location, right? Let us assume. So this is the output. For this output, what we have to do? So first we have allocated memory for the element, and now we have to read the element. So for reading the element, simply we can write the scanf %d ampersand value. Let it be value. In the value there is a node, right? So now here after reading, the value is equal to 10. Now we have to place that in the beginning position. So first let us see, new of data, it should be filled. Similarly, new of next, it should be filled. So in the data the value should be here. In the next, the address of the next node must be here. So initially this one, so new of data, it's automatically 10, so we can directly assign it. New of next, so in the new of next, here we have to get the address of previous node. So what is the address of previous node? Head of next, right? So hope you understood here. Head, new of next is equal to head. Automatically 1000 will be this value. If you write head of next, then 2000 will be here, right? So head, that means automatically the head address will be assigned to new of next. So automatically this will be happened and the head will be placed here itself. So we are just inserting the element at the beginning, so head should be to the first element. So you can directly assign the new is, head is equal to new. So the three statements are required to get this output, right? So hope you understood. So initially this one is the list. So if you want to insert at the beginning, that is element 10, the 10 must be the first node and the address should be the 20, the node 20 address should be placed at first node, right? So for that we have to write the new of data is value and new of next. So this is the new of next. So in the new of next we need the head address. So previously this element is a head. So head address should be stored in new of next. So new of next is equal to head. So this means the connection is established between the first element and second element. And now head is pointing to the second element after insertion. So we have to move head to first element. So head is equal to new. Right? So hope you understood this one. Inserting at the beginning. Now let us move with the next one. Inserting at the ending. Right. So this is the head, this is the 1000, and if you want to insert here, so see 60, null, 5000, and here it should be 5000, it should be 10. So this one is the output. Right. So here if you want to insert an element 60, if you insert a node 60 at the ending, right, at the ending position. So initially the list is this one. If you insert an element 60 at the end position, so the output will be this one. Now we will write the code. So this is a common thing. First we have to allocate the memory for this new node, and we have to consider the value, we have to take the input for a value, and then we have to place, right, see, first automatically you can simply write new of data is equal to value, so automatically that will be there. Now see this position, so what is this position? This one is new address of new, right? Address of new should be placed in tail. See, initially the tail is 50. So if you want to insert a new node, this address should be placed at tail of next. So tail of next is equal to new. Automatically the node new address will be saved into the element 50, right? And the new of next should be null because it is a last element. So new of next is equal to null, right? So with these statements the node is created, but the tail is at the last but one position. We have to move this tail to last node. So tail is equal to new. Tail is equal to new, right? So this is the statements. See, simply we are adding the element at the end, so that we are replacing this null with the new node address. So obviously tail of next is equal to new, tail of text is equal to new, and tail new of next because the new node itself is the end element, right? End node. So that's why we have to fill it with null. Tail is equal to null because the tail is at the last but one element. So tail should be positioned with pointing with last element. So tail is equal to new. So whatever the element we are inserting, the tail will be pointing to the particular last element. So this is the simple code for inserting the element at ending position, right? So once we will see all these statements, and finally we will implement a program. I will show you the implementation of linked list. So we will see the create, display, inserting at the beginning, inserting the ending, inserting at the specified position. Also in the next sessions we will see the deletion part also, right? So let us see the third one. At specific position. Specific position, right? Now let us see this one. Now, so let us one second, I will write it so that right. So here 20, 30, 35, 40, 50. So here, so the address is 1000, 2000, 3000, 4000, 5000. So here it is null, 5000. Sorry, right. Three thousand, 4000, 2000. Now the position is 2000 here. Let it be some 2500, some other memory location. Okay, so that should be here 2500. So here it should be 3000. Here it should be 5000. Right? So simply we can see this one. So if you want to insert at the position 2, so here position is equal to 2 and the element is equal to, value is equal to 35. Right. So value 35 should be inserted at position 2. Here also we can consider the index value from 0 itself. So from 0 the index starts. That means the index of first node is 0, second node is 1, third node is 2, and so on. So here, see, initially this one, so this is our list. In this list, at the second position, we are inserting the element. In the second element, we are inserting. So simply we have to establish the link. See, first consider the temporary variable because we need not move the head, right? We need not move the head, just consider the temporary element. So this is the head, this is the tail. So first we have to reach until position -1 because this position should be changed, right? Previously in the node 30, the address of next, that means the 40th address, the node 40 address is saved in the next of 30, right? Now it should be changed to new node. The new node address should be sent to the position -1, right? We have to travel up to position -1, right? Now let us consider temp is equal to head. Let us assign the head value to the temporal. Now consider the position also. So here we have to write again scanf %d ampersand position. So value here is 35, the position is 2, right? Now use the iterative statements for I is equal to 0 because index we have said that. So I less than position -1 I plus plus. So until it reaches the position -1. So just move. That means temp is equal to temp of next. So next address. It will move until it reaches position -1. So until it reaches here. Right? Okay. Right. So now the iteration is here itself. So if you place this 2500 in this position, the position of 40th node will be erased, right? So we have to follow the steps. First we have to place this 3000 in new of next. So simply one statement is common, that is new of data is equal to the value. That is common. Now next one, here in the node 30, in the second field of 30, it should be the address of new node, right? And in the field of new node, in the second field of new node, it should be the address of next node, that means a 40. So first if you place here, right, if you change this one, right, if you change this one, we can't place the address of 40 in the new node, right? So first we have to assign the node 40 address to the new node. So new of next is equal to temp of next. So new of next is equal to temp of next. So node connection is not disturbed. No connection is not disturbed. Now place this with the new node address. So next temp of next is equal to new. Temp of next is equal to new. Temp of next is equal to new. Right? So these two statements are very important. We have to follow the same order. Right? So this one, if you reverse this one, that means first if you remove the temp of next is equal to new. So if you perform this statement first, automatically here it will be 2500, right? It will be 2500 and this will be null. And what address should be placed here? Because we lost the address of the 40. We lost the address of 40. When? If you implement this statement, temp of next is equal to new, before this statement. Right? So that's why first you have to establish the connection. So that's why new of next is equal to temp of next. That means 3000 will be placed in the new of next, and then temp of next is equal to new. So 2500 will be placed here. Right? So this is the code for implementing the insertion operation at the middle. Right? So hope you understood this one. So the three cases, so insertion of an element at the beginning, insertion of the element at ending, and insertion of the element in the middle position, I mean specified position. Right? So if you understand this list concept, it is very easy to write the code. So first write down the input and draw the output. Based on the output, if you write the code, then it will be very easy. Right? So we know the sequence of steps, what to be first and what to be next. Now in this session we will see how to delete an element from the linked list. So we'll consider one existing linked list, some with 5 nodes, and from that 5 nodes we will see the deletion operation. So how an element is deleted from the beginning, how the element is deleted from the ending position, and how the element is deleted from the specified position. Right? Now let us see that. So linked list. So in that linked list we are seeing the deletion operation. So first let us see the linked list, existing linked list. So let us consider 5 nodes. Let it be, these are the 5 nodes, some 10, 20, 30, 40 and a 50. The memory of this 1000, 2000, 3000, 4000 and 5000. So we know that linked list means 2 fields will be there. One is the data field, another one is the address of the next node. So here the address of 20 will be stored. Here the address of 30 will be stored. Here the address of 40 will be stored. And here the address of 50 will be stored. And here it is a last element, so the address will be null. Right? So this null indicates the last element of the list. Now consider this as head and this as tail. Right? Now first delete at beginning. Delete an element at the beginning. So what is the output? First we will see the output, then we will write the code according to the output. Right? So we know that if you delete the element node 10, the first node will be C. So the overall only 4 nodes will be available, and the first node will be 20, 30, 40 and 50. And here the memory location is 2000, 3000, 4000 and 5000. Now here it will be 3000, it's a 4000, it's a 5000 and it's null. Now So this is the output. That means if you delete at the beginning a node, this 10 will be deleted, right? So the first element will be, so this is the head and this is the tail. There is no change on tail, there is a change in head. So here we need not read any value, because here we are not inserting but we are deleting the element. So in the linked list, just deleting an element, so delete means simply disconnect the link. Disconnect the link, right? So how to disconnect the link? So here we said that this is a link between one node and another node. So how to disconnect this link? Means placing null at address position. Address field, not a position, address field, right? So by placing null at address field, that node will be get disconnected, because we said that number of elements will be occupying in different locations and we are establishing a link between one node and another node by placing the address of node in the present node. So here the node is 20 and the address stored is the address of 30. That means the second element address will be stored in first node address field. So here if you place null at the address field, automatically the link will be disconnected. So here if you observe here, if you place null here, then automatically there will be no link between the first element 20 and 30, because so it points to the address of the location, address of the node, the second node. So here the address is null, so it doesn't point to the another node. So automatically this will be the single node. So this is a linked list. So in such a way that we have to disconnect the link, that means we are deleting the element. See, we will see one by one step. Now, hope you understand this one, right? Disconnecting the link, that means placing null at the address field. So whatever the element we want to delete, we have to place the null in that particular element. So here, if you want to delete the 10, in the place of 2000, we have to place null. Automatically this node will be disconnected from the linked list. So in order to place null, see, we have to move the head to second element, because after deleting this node, the head will be on element 2, node 2. So see, just remember, we need not modify the head, right? So we can take one temporary variable and we can assign the head to the temporary variable. So temporary is equal to head. Now what we have to do? See, temp is equal to head. So here the temp is also here itself. It is pointing here. Now the temp of next. Head is equal to head of next. So after executing this statement, head will be moved to here. Head is equal to head of next. Now we have to place null at the address field. So temp of next is equal to null. Automatically here the 2000 will be replaced with null, right? So this connection will be disconnected. The connection will be disconnected. So the output will be this one. This one is the output, right? Hope you understood. So here we have to take care about the execution of a statement. First we have to execute this statement and then the second statement, right? We should not change the order of the statement, because see, I will show you that temp is equal to head, so we are assigning the temp. So if you place temp of next is equal to null and head is equal to head of next. See, the same, both are same, but these two statements I have been swapping, right? So first I am initializing null and then I am moving the head. So if you write this one, see, 2000 and this is the head. So if you execute this one, first temp of next is equal to null. So obviously temp of next is equal to null, right? Next we have to move the head. Head is equal to head of next. So here head of next, there is no address, so where the head should be moved, so it doesn't know where to be moved because the address is, we are assigning null. So here we can't move the head, right? So that's why, that's the main drawback here. We can't move the head after placing the null, right? So in the first step we are placing the null at the address position, so automatically the link has been disconnected. So we can't move the head to the second element because there is no link from the first element to the second element. That's why we have to first move the head and then we have to place the null. So we have to take care about the link. So first we have to move and then we have to disconnect the node, right? So this is the wrong step, right? This is the right thing. So this is the simple logic if you want to delete an element at the beginning position. Now, so hope you understood this one, right? Next we will see the second thing. Right. Here it is a tail and this is the out. This is the head. Delete at end. Now see, if you observe here, see, if you observe here, in the second case we are deleting an element at the end. So here we are deleting the 50, the number 50, so that the tail should be moved to 40 and the address field of this 40 node should be null because null indicates the last element, right? So now let us see this one. Here also we should not change the head value, so that's why we are taking temporary as a head, right? We are taking temporary as head. Next, so we have to move till 30. So while temp of next not equal to tail, so it doesn't not equal to tail means here the temp will be here. So we have to travel. Temp is equal to temp of next. So just we are writing some iterative statements, right? So this iterative statement means until the temp of next is equal to tail, the temp will be moving towards its right. So temp of next, temp of next, temp of next is null. So the temporary will be here itself, right? Here the temp will be here, right? So now simply place the temp here, so it ends the loop, right? Now place temp of next is equal to null. Automatically here, instead of writing 5000, we are just replacing it as null. If you place null, automatically the link has been disconnected, right? And the link has been disconnected. Now see, tail is equal to temp. Now initialize, we have to change the tail. So here it will be tail. Just move here. Here we are just assigning, right? So in the previous session, in the previous case, we are moving the head. We have to move the head, right? So here the last element, so we are just assigning the temp to tail. Okay, so this is the code for deleting an element at the end position. Hope you understood here, right? So this is the output. We got the output. So just we have to disconnect the link. So if you disconnect the link, automatically the element is deleted in our perspection, right? So how to disconnect the node? So placing the null value at the address field of that particular node, the previous node. Now, see the third case, specific position. Deleted specific position. Some 5,000, right? Here it is a tail. Now, specific position. So here we require a position. So where it should be inserted. Deleted. Which element should be deleted? So here we have to read the position. Scanf %d ampersand position. Right. So until that position, let it be POS is equal to 2. Right? 2. 0, 1, 2. That means this element. We need to delete that particular element. Now, so for that we have to move the head from 0th position to position -1. So that means simply see here in this field we have to place the address of 40. And here we have to place null, or we can simply leave that one. So here instead of 3000 we have to link this node with the 40th node. Now for I is equal to 0, I less than position -1, I plus plus. So until this condition fails, we have to move the temporary variable. So before we have to initialize head to temp. So we need not change the head value. Temp of next, sorry. So temp is equal to temp of next. Automatically until the temp reaches the position -1, it will move. So now the temp will be in this position, right? Now see temp of next. Here instead of 3000 we have to place here the 4000. That means address of 40. So in order to get this one, simply we can write temp of next. So temp of next means 3000. That means a 4000 will be there. And temp of next means 3000. And next, temp of next of next. That means temp of next 3000 of next 4000. Right? So this is a referential pointer, right? So temp of next means 3000 of next. That means at the position of 3000, what is the address? 4000. Here, if you put data, automatically we can get 30. Sorry. So temp of next means 3000. 3000 of data means 30. Here instead of data we are placing next. So temp of next 3000 of next. So in the 3000, what is the address? 4000. So 4000 will be placed here, temp of next. Okay, don't get confused. So just we are linking, right? We are traveling forward. So if you want to place 5000, you can simply write temp of next of next of next. If you want to print the data, directly we can print the data. Here if you print the data, we can get the value. Here we are printing the address, we are assigning the address. So temp of next of next. Temp of next is 3000. 3000 in the 3000 position, what is the next? 4000. So 4000 will be assigned here in the place of 3000. Right? So simple. simple, that's it. So we need not, so if you place this one, this is null, this is 2000, this is 4000, this is 5000, this is 5000, this is 4000, this is 2000, this is 1000. See, after executing this code, we will get this one because we are placing 3000 to 4000. So obviously the link will be disconnected here, and the link will be connected to here. So this node will be left single. This node will be left single. So after executing this code, the link, so here instead of 3000 we are placing 4000. So automatically the link is established between 20 and 40. So this node will be single. So in our perception it is eliminated. So there is no element, there is no connection for this element with our linked list elements. So that's why we can simply ignore. So the output will be this one. If you want to delete an element from the specific position, delete from specific position, simply we can read the position, we can travel this temp until the position -1, and then we can place the next node address into the present node. That means temp of next is equal to temp of next of next. So 5000 will be assigned here. 4000 will be assigned here, right? So there will be a link between this 30 node will be disconnected from 20 and 40, right? So this is about the deletion operation. So hope you understood this session. Right. We need to find number of nodes. So we know that it consists of two fields. One is the element, another one is the address. Let us take 3 nodes. So this is the null because it's the last node. Let it be 1000. 10. Let it be 20. Let it be 30. So address of 10 is 1000. Address of 20 is 2000. Address of 30 is 3000. So he holds the address of next node. So 2000 will be here. Address of next node, that means 3000 will be here. Right. This is the normal thing. Right. Let us take it as head. This is a head. Now, so the problem is we need to find how many nodes are there in the linked list. So for that, so let us write the code. So first store the head with the temporary variable. So temporary is equal to head, right? Because we need to move the temporary variable from the first element till the last element. Now we have to use the iterations, right? We have to repeat the iterations. So while temp not equal to null, temp not equal to null. So until it moves to null. So here it is a null, right? If there is no node, that we can consider it as a null. So until temp not equal to null, we have to travel. So what we have to do? We have to count the number of nodes. So let us take the count variable, count plus plus. Initially take a count with a 0. Int count is equal to 0. Count plus plus. So one count will be incremented. Now we have to move from first node to second node. So this is a temp, right? Now we have to move this to this one. Now temp is equal to, we have to move this one. So what is the address of this one? Temp of next. So temp of next. So hope you understood this one, right? So we need to move this temp from first node to second node. So how to move this temp? So we have to move this temp to the 2000 address, because these are not the contiguous memory locations, right? So if it is a contiguous memory locations which we are used in arrays, simply we can increment the temp value, right? So there is a no rule that all the nodes should occupy the contiguous memories, right? So an element can be stored in any memory location, but that memory location address will be linked to the present node. So that's why in the linked list we are establishing a link between one node with another node by using this self-referential node, right? So temp must be presented, I mean the temp should be moved to the second node, which is in the memory location 2000. So this 2000 will be available in the present node, right? So head of next. So this is the head of data, head of the next. See. So if you consider one node, this is called head of data. This is called head of next, which we have seen in the previous session, right? Now temp is equal to temp of next. So temporary variable will be assigned to temp of next, that means 2000. So now this temp will be moved to here itself, right? Now again, just close it. Just close it. So again it will check for the condition, temp not equal to null. No. So here initially count is equal to 1, and now temp not equal to null. Again count is equal to 2. So count plus plus, that means the count is equal to 2. So this is the first iteration, this is the second iteration. Again temp is equal to temp of next. So temp is equal to, right, temp of next. Temp of next means 3000. Now the temp is assigned here itself, right? Now again temp not equal to null. Temp not equal to null, yes, true, because in this node 30 is available. So count plus plus. So now count is equal to 3, right? Again temp is equal to temp of next. So temp is equal to, so next means null. That means null. Now again temp not equal to null, condition fails. Automatically it will exit from the loop. Here we can write the printf statement. So printf count is equal to %d count. So automatically this 3 will be printed here, right? So this is the code for finding the number of nodes in the linked list, right? Hope you understood this one. So we should not change the head value, so we are taking one temporary variable, right? One temporary variable, and we are assigning the head to the temporary variable before starting the iterations. So in next we are completely iterating, we are using the iterations so that we are counting the number of nodes by moving the temp from current node to the next node. So how to link that one? By using this statement, temp is equal to temp of next, right? So this is a small operation, that is finding the number of nodes in a linked list, right? Now we will see how to reverse the linked list. That means here 10, 20, 30. So 10 is linked with the address of 20, 20 is linked with the address of 3000. Now if you want to reverse the linked list, 30 will be the head. In the 30 it should have the address of 20, and in the 20 it should have the address of 10. So reversing, the first element will be 30, second element will be 20, and the third element will be 10. Now let us see the code and we will trace so that your doubts will be clarified, right? Right, now let us see the reversing of a linked list. Now let us take 3 nodes. So some 10, 20, 30. So the address is 1000, 2000 and 3000. So here it will be 2000, here it will be 3000, here it will be null, right? So this is the head and this one is the head. Now reversing a linked list. Now let us write the code and then we will trace it. So initially this one, so final output should be 30 will be the first element, that means head will be assigned to 30, and here head of next should be 2000, and next element will be 20 and head of 20 will be, next of 20 will be 1000, right? And here in the 10 the next element, the address will be assigned to null because 10 will be the end element. So further we will take two more nodes, that is we'll use three more variables, the structure pointer variables, like previous, current and next. Right. Now let us write the code and then we will trace so that your doubts will be clarified. Now, so let us take the variables struct node. So we have declared a structure with a node, right? Struct node star current next previous is equal to null. So three nodes we have declared. Now okay, then just current is equal to head. So assign current is equal to head because we need to move one element to the another, so that head should we can't move the head, so that just assign the head to the current. Right. Now iterations, follow the iterations because we have to move from first element to the last element by establishing the connections, right? While current not equal to null, so unless the current not equal to null, these iterations will be performed, right? The next is equal to current of next, current of next is equal to previous element, previous element is equal to current element, current element is equal to next element. After completion of this one, just assign the previous node with the head, right? So this is the simple logic for reversing a linked list, right? Now let us see that. So this is the existing linked list. Now let us see first one, current is equal to head. So it points here itself. 10, 20, 30, here null, here 3000, here 2000. See, right? Now current is equal to head. So here itself it is a head and also this is the current, right? And also previous is equal to null. So star previous is equal to null, right? So in the first, this is the initialization, first iteration, iteration 1. After in the iteration 1, current not equal to null. So here if we are assigning the current to head, so current not equal to null, it's a true, right? Okay, so current not equal to null, but here current is assigned with the 10 element, so this is a true, loop true, so it enters the loop. Now the next is equal to current of next. See here current of next is 2000, current of next is 2000, so 2000 will be assigned to next. That means current will be here, sorry, next will be here, right? Next, current of next is equal to previous. Current of next means this one. So this is the current, this is the next, this is the head, and previous is equal to null. Now current of next is equal to previous. So current of next, so this one is equal to previous means null. So 1000 will be removed and it is replaced with null. Hope you understood this one. Now previous is equal to, sorry, here I will write here, okay, current of next is equal to null, right? Now previous is equal to current. Now previous is equal to current. What is the current one? 10 is the current, right? Now 10. So previous is equal to current. So this is previous, right? Next, current is equal to next. Current is equal to next. Current is equal to next means 20 element. So current, right? So after the first iteration, see, after the first iteration, the previous value is assigned to 10. The 10th element address field is assigned with null, and the second element is assigned with null, next and current. Right? Now we'll go with the second iteration. So first we have to check the condition, and then we have to enter into the loop if the condition is true. Now, so this is about the first iteration. This is about the first iteration. Next, iteration 2. Iteration 2. Current not equal to null. So current is equal to 20. Is equal to 20, not equal to null. So true, condition is true. So now next is equal to current of next. So next is equal to current of next. Current of next means 3000. Now next is equal to current of next. So now the next will be assigned to this one. Next will be assigned to this one. Now let us see. Current of next is equal to previous. Current of next is equal to previous. So what is the previous? 10, right? Current of next. Current of next. So what is the current of next? So 3000 should be replaced with previous. So what is the previous? 1000, right? 1000. What is the previous? It's a 10 with the address 1000. So current of next is equal to previous. So as this is the address field, so this one is the address field, the address of field of previous, the address of previous should be assigned to current of next. So 1000 is assigned to here. So here 1000. Now previous is equal to current. Previous is equal to current. What is the current here? Current is 2000. Right? Current is 2000 or 20. Okay. Simply we can write the element. Previous is equal to 20. And current is equal to next. Current is equal to next. Sorry, previous is equal to 20. So just move the previous here. Sorry. Now previous is here. Current is equal to next. So current is moved to next one. Current is equal to next. So current is equal to next means current is equal to, what is the next one? That is 30. Right. So this is the second iteration. Second iteration. Right. Now 10 with the address field null. Next 20 with the address field of 1000. That means 10 address field. Third one is 30 with the address field null. Now we have to change that one. In the third iteration, let us move with the third iteration. So unless you trace the logic, you can't understand, right? So that's why I am tracing the logic. Now iteration 3, again current not equal to null. Current 30. So 30 not equal to null. True. Then move with one. Next is equal to current of next. So current of next means null. Current of next means null. Next, current of next is equal to previous. So current of next, this field, current of next is equal to previous. Previous means 2000. Right? Current of next is equal to previous. That means 2000 because previous is assigned to 2000. Now previous is equal to current. Previous is equal to current. Right? So this will be assigned here itself. Previous is equal to current. 30. Next, current is equal to next. Current is equal to next. Current is equal to next. Right? Next is equal to null. So here we can replace this next. Null. Current is equal to null because so here we have given the next is equal to null, and here current is equal to next means current is equal to null. Right? So now again, so this is the end of the iteration, third iteration. Now again it will move with the condition. So current not equal to null. This is false. Then the control will come out from the loop and head is equal to previous. So out of loop there is one statement. Head is equal to previous. What is the previous? 30. So here head will be removed here and it will be assigned here itself. Right? So 30, which is having the address field of 2000, which is of the next one, and 20, which is having the address field of 1000 of next one, which is 10 with the address field null. Right? So after the completion of iterations, we got the reverse. So first element 10, second element 20, third element 30. After the iterations, the first element head is 30, 20 and 10. Right? So we can just, no use of tail here. Okay? There is no use of tail. Right? So this is a simple logic for reversing the linked list. So just trace out it one. So if you trace step by step, automatically the clear-cut understanding will be there. Advantages. So this is the linked list. The first and foremost advantage is there will be no wastage of memory. So here, while creating every node, we are using the dynamic memory allocation for allocating the memory. Right? So that's why prior we are not taking any number of elements or number of nodes we need to add. Right? So that's why every time we are calling the malloc function to allocate the memory for the newly created node. That's why there will be no wastage of memory. Second thing, no need to use a contiguous memory locations. So here one more advantage is we need not allocate the contiguous memory locations for the number of elements, because here we are providing the link in every node which holds the address of the next field, next node. So that's why there is no need of using these contiguous memory locations. We can store the elements anywhere, but we have to provide the address in the current node. Insertion and deletion. The insertion and deletion becomes very simple. So here we have seen this is a disadvantage over arrays, because in both the cases, if you want to insert an element or if you want to delete an element, we need to move the positions, index positions. So that need not be taken here. So that's why this insertion and deletion becomes more simple. Right? The linear data structures like stack and queue can be implemented. Yes. So the linear data structures like stack and queue can be implemented by using this linked list in a very simple manner. Right? So this is one more thing. And then can store any type of data in the node. It can store any type of data in the node. Right? So we have seen that every node is having two fields. One is data field, another one is the address field. In the data field, we can store the either integer or a character or anything else, float. So we can store any type of data in the node. Right? So these are all the advantages over linked list, single linked list. Right? So no wastage of memory because we are using the dynamic memory allocation. No need to use the contiguous memory locations because we are already establishing the link between the two nodes. And then insertion and deletion become very simple because we are not moving any index positions. And linear data structures like stack and queues can be implemented by using the single linked list in a very simple manner. And we can also store any type of data in the node, in the data field in the node. Right? So these are the advantages. Now we will go with the disadvantages. Disadvantages. So what are the different disadvantages of using this linked list? The first one is random accessing is not possible. This is very most important disadvantage. So here we are not using any index positions, right? So here there is no chance of random accessing the elements. So if you want to access the fourth element, it is not possible until you access the third element. If you want to access the fifth element, it is not possible if you are not, until you access the fourth element. So random access is not possible. Second one, only forward traversing is possible. Only forward traversal is possible because so we are giving a directed link because every node is having a pointer field which holds the address of the next field. So it doesn't hold the address of the previous field. So that's why only the forward traversal is possible but not the backward. If you want to access the previous node, it is not possible in this single linked list. Right? Next. Binary search algorithm is not possible. So because here we are not using the index values, where the binary search algorithm will reduce the search space according to the middle element. So here there is no accessing of the index values. That's why the binary search algorithm is not possible in single linked list. Yes. So here one more disadvantage is reversing a linked list. The reversing of a linked list is somewhat complex because in order to reverse the linked list, automatically we have to change the links from one node to another node, right? So we have to change the links of all the nodes. So that's why the reversing of a linked list is somewhat complex. So hope you understood. So every node is having a link of second node, next node. So if you are using the reversing, if you want to access the, implement the reverse of a linked list, we need to change the link of every node, right? So that is somewhat complex. Another one is extra pointer is required. So why this extra pointer is required? So this extra pointer is required to store the address of the next node. So that's why one extra pointer is required. So that is one of the disadvantage of single linked list. So these are all the disadvantages. One is the random access is not possible, where we are not choosing the index positions, and also only forward traversal is possible. So it is not possible to find the previous one, and it is not possible to implement the binary search algorithm because here we are not using the indexes, so we can't reduce the search space. And here also reversing of the linked list is somewhat complex because we need to change every link of a node. And also extra pointer is required because here every node is having one pointer field which holds the address of the next node. That's why an extra pointer is required. So these are all the disadvantages of a linked list, single linked list. Right. In today's session, we will go with another topic, that is a circular linked list. So name itself indicates here it is a circular linked list. So in a single linked list, we had a last element which can store the null in the address field. Right. So we know that in the linked list, a node will be there, and every node is having two fields. One is the data field, another one is the address field. So in the data field, the actual data will be stored, and in the address field, it will holds the address of the next node. So if that particular node is the last node, it is not establish a link with the another node. That's why we will place null in the last node, address field of the last node, right? But here it is a circular linked list. So in a single linked list, if the last node in the address field of the last node holds the address of the head, then automatically we can say it as a circular linked list. See, let me explain. So consider three elements. Consider the three elements. Right, only three elements. So address field and a data field. So 1000 is the address, 2000 and 3000. The data 10, 20 and 30. Right. So here coming to the single linked list. Single linked list. So in the address field of the first node, it will hold the address of this next one. That means here it will be having 2000. Here it will be having 3000. Here it will be having null because it is a last node, right? It is a last node in the case of single linked list. Now our question is circular linked list. Circular linked list means instead of placing null, we have to place the address of the head. So this is the head. So we know that this is the head and this is the tail. So in the address field of the tail, there should be the address of head. What is the address of head? 1000. So here, if it is 1000, automatically it is linked with this one, right? It is linked with this one. So this is called, so now there is no question of a tail, right? Just okay, remove. So this is called the circular linked list, right? If the last element is having the address field which holds the address of the first node, automatically that is called a single linked list. So while creating the linked list also, we have to keep on updating the address field, right? So that's the only difference between a single linked list and the circular linked list. Now we will see how to create a linked list, how to create a circular linked list. So the logic is similar which we have studied in single linked list. See, so always we will take a new as a node, right? A newly inserted node. So first we have to create a structure for the node. So that's why we can simply write here struct node. So int data. So we can also take it character, right? So again, self-referential structure. Struct node star next. So next is a self-referential, which is representing the node. Here we can create a new head, tail, sorry, star, it should be star, right? Temp, etc. Right. Now, so new is having data and next, head is having data and next, tail is having data and next, temp is having data and next. Right. Now, we will see if you want to create a node. First, we have to allocate a memory by using the dynamic memory allocation. So, first step, we have to take the new is equal to struct node star. We will use a malloc function, size of struct node. So memory is allocated to the new. Now we need to read the value, the data. Right? Now let us read the value. Scanf %d value. Oh, sorry, ampersand value. Now we are reading the value. Now it should be placed in a node. So where it should be placed? Value should be placed in data and the address will be placed in next. So now new of data is equal to value. Similarly, new of next is equal to null. So initially first element, if it is a 30 is the first element. So a node is created here, it is a new, here it is 30, let us take a 10, 20 and 30. So first element 10, so 10 is stored here, this is the data part, this is the next part. So next, in the next we are placing null, right? Now we have to place this head and tail. For that we have to check the condition. If head is equal to null, if head is equal to null, so initially head and tail will be null. Initially the head and tail will be null. So if head is equal to null, so head is null. Obviously the head is equal to new. Similarly, tail is equal to new, because it is only one element existed, so head will be that element and also tail will be that element. So it points here head, tail. Else, so if it is not a head or tail, then see. So first element, it is safe. Coming to the second element, if you add 20, right, new of data. So now new is not this one. Again we are creating one more node. New of data is 20. So 20, this is the new, this is the data, this is the next. New of data is equal to 20. New of next is equal to null. So initially it is placed with null. Right. So now if head is equal to null, so we have given that one. Now, so sorry, it is null. Now it's a else part. It's not, head is not equal to null, and so it will be moving to the else part. Now here instead of null we have to place the address of new, right? In the place of null we have to place the address of new, right? So let it be, the address is 1000 here, address is 2000 here. So 2000 should be placed at the address field of head, right? Head or tail. All right. So we can write it as tail of next. See here, tail is pointing to the first node, head is also pointing to the first node. So tail of next means this field is equal to new. Automatically 2000 will be stored here. So null is replaced with 2000, right? Now we have to move the tail. So tail is equal to new. So now tail is removed here and it is assigned to here. And there is a link from this one to this one, right? Now, and after that one, if it is a last element, so here we are having two elements, 10 and 20. If it is a last element, what we have to do? Here it should hold the address of first element, right? It should hold the address of first element. So where we have to store? Here. What is this one? Tail of next. Tail of next is equal to, which one we have to store? The head. So head, right? So automatically null will be replaced with 1000. Null will be replaced with 1000. See this one. So this is a circular linked list. If in the third iteration, if you want to include 30, so here new will be removed and now a new will be having a one more node with a 30, right? This is the data part, this is the next part. Now let us see this one. This is one new. New of data is equal to value. So 30 will be stored here. New of next is equal to null. So here it will be replaced with null. If head is equal to null, head is not equal to null. So else part. Tail of next is equal to new. Tail of next. So tail of next means tail of next 2000. So if the memory is 3000, here tail of next is equal to new. So 3000 will be replaced. Next tail is equal to new. Now tail will be removed and it will be assigned here. Next tail of next is equal to head. So null will be replaced with, what is the head value? 1000. So automatically, see, it will be having a link from here and here it will be having a link to this one. This is called circular linked list. And again, if you want to add a 40, again there will be new node 40 next. So in the similar way, we have to keep on executing this one. So all these should be executed number of times. So that's why we can keep it in a iteration loop. So while some ch is equal to y, we can write here. So after this else statement, we can write here printf y2 exit n2 continue. Simply we can write here, right? So while ch is equal to y, it will stop, right? Okay. So all these statements should be executed repeatedly, that means iteratively. So like this we can create a circular linked list. So only one difference from the single linked list, that is this single statement, this statement itself. So in the single linked list we will not use this statement, so that the tail will be having only null. So there will be no link established for the last element. But here it is a circle linked list, so it should be, link should be established from the last element to the first element. So that's why here we are writing tail of next is equal to head, right? Hope you understood this one. This is how we have to create a linked list. Now we will see one more operation, that is how to display the elements of a linked list. How to display, right? So in order to display, again we have to use the iterative statements. Okay, so until when? So until the last element. How to find the last element? If any node is holding the address of the head, that element is a last element, right? Yeah. So let us take an example here. So 10, so 2000, 20, and let's say 3000, 30, and it's a 1000. So the memory address is 1000 here, it is a 2000, it is a 3000. Right. So this is a linked list. Let us take it. So we have to repeat this one. So while, so first we need not, we should not change the head value. So this is the head. We should not change the head value. So let us take one temporary variable and initialize the head to the temporary variable. And we have to traverse through last element. That means while, see, temp of next not equal to head, right? Because the address field of the last element will be holding the address of the first element, head element. So that's why we are using temp of next not equal to head, and we have to print the value, printf %d temp of data. So if you print temp of data, automatically that value will be printed, and we have to increment that one. So now increment the temp value. Temp is equal to temp of next. So automatically it will be pointing to the next element. So close this one, and then see, up to here it will be displayed, here it will be not be displaying, right? So circular linked list, right? So all these will be displayed. Now in order to display the last element, again we have to print temp of data. Okay, here also again we have to print the temp of data here. See, let us take an example. So if it is a temp of next not equal to head, what is the head value? 1000. Temp of next, so temp pointing the first element, temp of next is 2000, so it is not equal to head if the condition is true. So printf temp of data, so 10 will be printed. Next, temp is equal to temp of next. Now temp value is temp of next, so temp is 2000 here. Now temp is 2000, then temp of next 3000 is not equal to head, is not equal to 1000, it is true. So enters into the loop temp of data, that means 20 will be printed here. Temp is equal to temp of next, so temp will be moved to the next position. See, temp of next is 1000, right? Not equal to head, means 1000. False, automatically it will come out from the loop, so the last element will not be displayed. So that's why we have to print here the last element. So here we can write one more thing, printf %d temp of data. Now what is the temp of data? 30. So 30 will be printed here, right? So hope you understood how to display the elements or how to display the nodes of a circular linked list, right? Yes. So let us stop this session. So in this session we have seen the two operations. One is how to create the circular linked list and how to display the nodes of a circular linked list, right? So a slight difference between the single linked list and circular linked list. In the single linked list, the last node, the address field of the last node will be placed with null, and here in the circular linked list the address field of the last node will be filled with the address of the first node, that means head node. So that is the only difference over the single linked list to the circular linked list. So hope you understood this create operation and display operation. Circular linked list. Now let us see the insertion. So in this insertion, we'll see the three cases. One is inserting the node at the beginning, inserting the node at the ending, inserting the node at specific position. Right. Now, let us take an example so that you will be better understanding. Right. Let us consider one example with the 4 nodes. Right. The address of first node is 1000, 2000, 3000, 4000. Let it be 10, 20, 30 and a 40. Here it will store the address of the next one, that is 2000. It will store the address of next one, that is 3000. It will store the address of next one, 4000. Here 40 is the last element, so according to the definitions, the last element or last node of the circular linked list will be having, it will holds the address of the first element. So first element address is 1000. So here it will be 1000. So that there will be link from this to this one. Yes. This one is a head and this one will be the tail. We know that. Right. Now, insertion at beginning. Insertion at beginning. That means, let it be the value is 5. So first we will write the output. What is the output after inserting the element? C. See 10, 20, 30 and a 40. Two thousand, 3000, 4000 and 1000. Right. Now let us see if it is a new. That means we need to insert this new into this linked list. So for that we know that we have to allocate the memory by using the dynamic memory allocations. So first new is equal to struct node star, which returns a pointer using a malloc function, size of struct node. Alright. So a pointer will be assigned to this new, this one. Let it be 500. 500 is the address of new. And we have to read the value. So scanf %d ampersand value. So let it be value is 5. The value is 5. So 5 should be inserted here. Right? The address is 500. It is a new. Right? So the 5 should be inserted here. Now, new of data is equal to value. Right. The first step is new of data is equal to value. That means this is the data. This is the next. So new of data is equal to value. So 5 is placed here. Hope you understood. Next. New of next. What is the new of next? Here which address it should be? So it should fill with the address of head. So new of next is equal to head. Right? So new of next is equal to head. So the address will be placed here. So automatically a link is established. A link is established. Now we have to change the tail, because according to this, the tail, that means the last node, should contain or should hold the address of first one, but here it holds the address of second element after inserting new one. So we have to change the tail. Where it should be changed? This position. Here it should be 500. So how it will be? Tail of next. Tail of next is equal to, what is this? 500. New, the address of new. So new, right? So a link will be established from the ending node to this one. Now head should be changed, because head is in the second node. Now head should be changed to first node. So head is equal to new. So here head will be replaced and it will be assigned to new. Right? So this is a small logic for inserting an element at the beginning. Right? So once again, just we will observe, this is the new element. In this new element, here the data, the actual value should be placed in the data field. In the address field, the first element, this element address should be placed. So next, new of next means this field is equal to head. So what is the head address? 1000 will be placed. So a link is established now. Now tail should be linked with the head. So tail of next is equal to new. Now head will be moved to new. A simple logic for inserting an element at the beginning in the circular linked list. Okay, so hope you understood this one. Right. Now we'll go with the second case, that is insertion of an element at the ending position. Right. This is the tail, and let it be, this is the 5000, and this is the data field, this is the next one, and this is the new. Right. So second case, that is insertion of an element at ending. Insertion of an element at the ending. So this is the output, and here we have to establish the link. Now let us check it out. So first we have to create a node, so we have to allocate the memory. So the same step we have to write it here. The new is equal to struct node star malloc size of struct node. So now we have allocated some memory to the new, that is some 5000. Now we have to read the value scanf %d ampersand value. Let it be 50. So where this 50 should be placed? Here itself. What is the value here? I mean, what is the variable here? New of data. So new of data is equal to value. So automatically the 50 will be placed here. Right? Now the place of tail, what should be placed? The address of new. So here that means tail of next, because we have to establish the link between this node and the newly added node. For that purpose, tail of next is equal to new. Automatically the 1000 will be replaced with the address of new. That means 5000. So automatically here the link is disconnected and here the link is established. Hope you understood this one. Tail of next is equal to new, right? Now what should be placed here? Because this is the last element, the address field of the last element should have the address of head. So here it should be placed the address of head. That means 1000 should be placed here. 1000 should be placed here. So for that, new of next is this one. New of next is this one. New of next is equal to head. New of next is equal to head. Automatically the 1000 will be placed here and the link is established now here from last element to first element. Now the tail should be moved to the last one. Tail. So previously the tail is last but one position. Whenever the node is added, the tail should be moved to the last position. So now we have to assign the new to tail. Tail is equal to new. Obviously this tail will be assigned, removed here and it will be assigned here. Right? So this is the output after adding an element at the end of the circular linked list. Right? Hope you understood this one. So first we are just adding the value and then we are establishing the link from previous node to last element. That means this one, tail of next is equal to new. So next, new of next is equal to head, because as it is a circular linked list, new of next is equal to head. So if you place new of next is equal to null, automatically this will be coming to single linked list. Right? A slight difference. So unless you draw the diagram, you can't write the code. Unless you remember or mug up. Right? Just draw the diagram and finally we know what should be stored in the address field, what should be stored in the data field. Based upon that thing, just write down the statements. It would be very simple. Right? So this is all about the second case, that means inserting an element at the end position. Now the third case, let us see the third case, that is insertion of an element at a specific position. So we will specify some position and then so the data must be inserted at that particular position. Right? We will go with the third one. Right. See, here we need to take the third one, specified position. Here we have to take two inputs. One is value and position. Value and position. These are the inputs to be taken. So two scanners to be written. Now let's write the output so that you will understand. Right? Let the position be 2. At the second position, 0, 1 and 2. So here the logic is not changed for both the single linked list or double linked list, because the position, specified position, the logic is same for both the single linked list and circular linked list. Now let it be, there is a connection here and we need to insert an element here itself. We need to insert an element here itself. So it is the data, it is the next, and this is the new. Right. Now this is the head and this one will be the tail. See, now just read the value. First we have to write the memory allocation just before we have written that new is equal to struct node star, so that the address will be assigned to new. Let the address will be 2500 here. 2500. Value will be 25. Let it be. The value written is 25 and the position is a 2 at the position 2. So we have to shift the head from current position 2, that means the first element 2, position -1. So for I is equal to 0, so we should not change the head, so just initialize head to some temporary variable. Temp is equal to head. Now for I is equal to 0, I less than position -1, I plus plus. So it will move until it reaches position -1. What should be done? The temp is equal to temp of next. So simply we are moving the temporary variable. So in the first iteration it will move. So initially the temp will be here, right? After first iteration this temp will be moved to this one, right? And whenever in the second iteration, that means I is equal to 0. So here I is equal to 0. Whenever I is equal to 1, the condition is false because 2 minus 1, 1 less than 1, condition false. So it comes out from the loop. Now what we have to do? So here, right, so carefully observe, we have to establish the link between the newly added node and the next node, and the previous node and the newly added node, right? First we have to establish the link between the current node and the next node. What is the address of next node? 3000. Where it is been? So it is in this position. That means temp of next. Temp of next. Right? See. Now we will see. So we can simply write new of data is equal to value. So automatically this 25 will be placed here. 25 will be placed here. Will be placed here. Now new of next. New of next. What should be placed here? 3000. Where? Temp of next. Right? Temp of next. Temp of next. See. Now after executing this statement, temp of next is 3000. 3000 will be placed here. That means a link will be established from 25 to 30. Now here, see, here that means temp of next, it should be assigned with the address of new. Temp of next is equal to new. Automatically the 3000 will be removed, so this connection will be disconnected and 2500 will be saved here, so it will be connected. This node will be connected to this node and this node will be connected to this node. So just follow the address, just follow the statements. Okay, so hope you understood this one, right? So first we have to place the data. There is no issues. Next, new of data is equal to value. The statement is normal, right? Next, new of next. What should be placed here? New of next. So here it should hold the value of, it should hold the address of 30. What is the address of 30? 3000. Where it is placed previously? In here, 20th. So temporary. So temporary of next. So new of next is equal to temporary of next. Now a connection is established between this node, a newly added node, to the next node. Now we have to place a connection between the temp node and new node. So that's why we have given temp of next. Here we have to hold the address of new. So that's why temp of next is equal to new. So this is how we have to insert an element at the specified position. Right. Circular linked list. Let us take an example and we will start the session. So let us take 4 elements. There is 4 nodes. Right. So we know that every node is having 2 fields. One is data, another one is the pointer field. So let it be 10, 20, 30 and 40. The address of 10 is 1000, address of 20 is 2000, address of 30 is 3000, address of 40 is 4000. So the first node will holds the address of the second node, that is 2000. The second node will holds the address of third node, that is 3000. Third node will holds the address of fourth node, that is 4000. And it is a circular linked list. The last node holds the address of the first node, that means 1000. So there will be a link from last node to first node, right? And we know that the first node will be head and the last node will be tail, right? So we have discussed this deletion operation in the single linked list, that here deletion means just we are disconnecting the link between one node and another node. And if you want to deallocate the memory, we can use the free function. So that particular node, if you apply this particular node to the free function, automatically the memory will be deallocated. Okay. So first thing, we have to disconnect the link. How to disconnect the link? We have seen that just remove the address which is presented in the address field and replace with the null, so that automatically the link will be disconnected. Right. We'll go with the first case. So we are seeing this deletion operation. Right. So first one, deleting the element from the beginning position. That means if you want to delete a 10, so 10 should be deleted. 10 should be deleted. See. So I am drawing the output so that we will write the steps. So 10, 20, 30, 40, 3000, 4000, 1000. Right. So if you delete this element, the head must be moved to 20, and the address of the last node, the address field of the last node should contain the address of second one. Right. Now let us check it out. Head and tail. Right. So we should not change the head. So first I will give assignment to temporary variable. Right. I will just give a head to temporary variable. I am now moving the head from first position to next position, because the head should be in the next position, because we are deleting the first element. So head is equal to head of next. So automatically after executing the statement, the head will be moved from here to here, right? Okay, then see this tail, I mean the address field of tail should map with the address of the first element. Here the first element address is 2000. So tail of next. So what is the tail of next? This field is equal to head. So after executing this statement, tail of next, this will be replaced with 2000. So here also the connection is disconnected and here the connection is established. Now one more thing we have to do. What is that? This link should be disconnected. This link should be disconnected. So we have assigned head to temp. So here there will be temp. Simply we can write temp of next. Temp of next is equal to null. So automatically here it removes the 2000 and it places the null. That implies it disconnects the link between this node to the next node, right? So the output is this one. First element is 20, 30, 40 and the 40 is mapping with the first element. So hope you understood. So if you want to deallocate the memory, automatically if you apply the free function to the temp, automatically this memory will be deallocated, right? So hope you understood this. So first we are changing the head and then we are establishing the link, right? Head is equal to head, we are establishing the link from tail to head and then we are placing the null to the first node. That means we are disconnecting the first node, right? So this is all about the deletion of an element from the beginning position, right? Hope you understood. Now we will go with the second thing, that is deletion from the ending. Deletion from the ending. Yeah. See, here there is a link from here. It is 1000. It's not a 2000. It's 1000. Right. Now, second, deletion from end. Deleting an element from end. So here we have to delete this, the node 40, so that we have to move the tail to the left side and 30 will be the last element and the last element address should be the head, should be assigned to head. Okay, right. Now let us see. So just we will assign head to temp. We will assign head to temp. So automatically temp. Okay, we need to move the temp till 30. We need to move the temp till 30. So that means simply we can write the iterative statement while temp of next not equal to tail. So it will move until the temp of next not equal to tail. Right? So temp of next not equal to tail. So tail is 4000. Temp of next means 2000. Right? So every iteration we have to move the temp. So moving the temp means simply temp is equal to temp of next. Right? Let us test this one. First, temp of next 2000 not equal to tail 4000. True. So temp is equal to temp of next. Now temp of next means, so after the first iteration the temp will be moving towards this one. So here it is temp. Now temp of next 3000 not equal to 4000. True. Temp is equal to temp of next. The temp will be moved from here to here. Right? Next, 4000 not equal to 4000. False. So it comes out from the loop. Okay, it comes out from the loop. So after completion of these iterations, the temp is pointing towards the last but one element. Okay, so hope you understood this one. Now see what we have to do. Here we have to disconnect this one, right? We have to disconnect this tail. So simply replace this 1000 with null. So what is this position? Tail of next is equal to null. So automatically this 1000 will be removed and null will be assigned here. That means connection is disconnected here. Connection is disconnected. Then now what we have to do? Here we have to disconnect this connection between the last but one element and the last element, and also here instead of 4000 we have to place 2000, right? For that we know that what is this position? Temp of next. Temp of next means 4000 is equal to head. Temp of next is equal to head. Automatically here it will remove the 4000 and it will place 1000. So it was disconnected. It was disconnected here, and a connection is established from here to here. Right? Now tail is equal to temp because the last statement will be tail. So here we are assigning tail here. Just remove here. We can remove that one. Okay. So this is a small thing. Hope you understood. So how to delete an element at the ending position. How to delete an element from the ending position. So for here also, first we have to travel the temp from first element to last but one element. So there we have to disconnect the last element, right? So there is a link between the last element and the first element because it is a circular linked list. So first we have to disconnect the last element, that link between the last element and the first element, and then we have to disconnect the link between the last but one element to the last element, and we have to move the tail, right? So this is a small code logic for deletion at the end position. Right. Now we will go with the third one, that is how to delete an element from the specified position. Right, this is the third case. So how to delete an element from the specified position. So here we have to take the input as a position. So from where we have to delete the element. So the first statement is scanf %d ampersand position. So first we have to find the position where we want to delete the element. So then we have to move the temporary value because we are not moving the head. So just will assign the head to temp value, right? So now we have to change the head position or a temp position from starting point to the position -1. So this is a code which we have seen in the single linked list. Simply do the iterations. I is equal to 0, I less than position -1, I plus plus. So simply we have to move that one. So temp is equal to temp of next. So here see, so initially this is the temp, because here we are assigning temp is equal to head. Let it be position is equal to 2. Position is equal to 2. So in the first iteration, I is equal to 0, position, sorry, I is less than position -1, 2 minus 1, 1. So true. Automatically we have to change the temp value. So temp is equal to temp of next. So 2000. So this temp will be moved to 2000. Hope you understood this one, right? So temp is equal to 2000. Now the second iteration, I plus plus. So I is equal to 1. So 1 less than 1, false. So just stop the iterations. Just to stop the iterations. What we have to do here? So we have to disconnect the second element. That means this element. So this element should be disconnected. So we have to disconnect the link between temp and the next value. So here, what we have done in the single linked list, just we are placing the address of, sorry, it is not null. Just we are placing the address of the next element. We are just skipping the middle element, the positioned element. We are skipping the positioned element, right? So we are just disconnecting the link, right? So temp of next is equal to, that means this position. Temp of next of next. So temp of next means, see, 3000, and temp of next, that means 4000. So 3000 will be moved with 4000. Automatically this link is disconnected, and see, it is placing here itself. Okay, it is placing here itself, right? So hope you understood this one. So just we are placing the link, we are just skipping the link. Okay, so temp of next means this position is equal to temp of next, that means 3000 of next. So that means 4000. So 4000 will be moved in the address position of temp. Automatically that particular 3000 element will be disconnected from the linked list. Okay, so hope you understood this one, right? Right. So a simple thing. So there is no change in deletion of an element from the specified position. So the same code which we have used in the single linked list, the same thing we are using. So there is a slight difference in beginning position, deletion of an element from beginning position and ending position. Right, the name itself indicates here we have to establish 2 links for every node. So till now we have used a normal linked list, that means a single linked list, where every node is having one data field, another one is a pointer field or an address field which holds the address of the next node. Now in this double linked list, the name itself indicates every node will be having 2 address fields. That means every node will link 2 different nodes. So one is the next node, another one is the previous node. See, so how to represent this double linked list, a node in a double linked list. So a representation of a node in a double linked list is this one. That means, so it is a node which consists of 3 compartments. The middle one is the data. The middle one is the data. So next, rightmost one is the next. Leftmost one is the previous. Right? So see, this is the address field, and this one is also the address field. Right? So this stores the address of previous node. Address of previous node. And this holds the address of next node. Right? This holds the address of previous node. This holds the address of next node. Now, if it is a starting element, so that means if it is a head, then the previous, so there will be no previous node. Okay, so this is a head, that means a starting element, so it doesn't have any node, the previous one, so there will be no link for the previous node. So that's why here the previous must be equal to null if it is a head. If it is a head, here if it is a tail, so we know that a tail is a last element. A tail is a last element. So if it is a last element, then there will be no other node, so the next field will be null. Next will be null. Right? Hope you understood this one. If it is a only single node, then previous field will be null and the next will be holding the address of the next node. If this node is a last node, that is a tail, then previous will hold the address of previous node, and next there is no other node, so next will hold the null value. Right? Then, so this is the representation of a node in double linked list. So here we are using two different links. So that's why we are using this double linked list. Right? Now let us create a structure for this node. So how to create a structure for this node? So here there are 3 fields. One is data, 2 are the address fields. Simple. So we know that struct node, which we have created for single linked list. So here we have to use struct node star previous, so self-referential node. Next, int data, so integer or a character, whatever it may be. Again, struct node star next. So this is the structure for a node in double linked list. Okay, so three fields. 2 are the address fields, previous and next, and another one is a data. Right? So hope you understood this one. So if it is clear, then we can write the code very easily for creation and display. So in this session we will see the 2 operations, that is creation, how to create a double linked list and how to display the nodes of a double linked list. So that will be very easy if you understand this concept. Right. Now let us move on to the operations. Yes. So first one is create. So how to create the node? See, we know that here also the same concept which we have studied in the single linked list. So here also we have to allocate the memory by using the dynamic memory allocation. So here we can use the new is equal to first statement, new is equal to struct node star malloc size of struct node. So automatically the address will be assigned for this new. Now what we have to do, we have to read the value data. So scanf %d ampersand value. So if it is a integer, we have to use this %d. If it is a character, we can use the %c. Right. Now we had a value and node. Now what we have to do? So we have to place this value in the node. So whenever we execute this one, this will be created. See. So this is the previous, this is the next, this is the data, and this one is the new. Right. Now value, if we take excuse me, 10 as a value, right? Now we have to insert that one. So it is the first element, right? It is the first element. So the previous will be null and next will be null because only one element is there. So that's why we can simply write it as new of previous is equal to null. New of data is equal to value. So we are placing the value. New of next is equal to null. Hope you understood this one, 3 statements. So initially it is null, it is 10, it is null. Right? So we are creating only one element. So that's why we are just placing both the null values. Now, so in the second iteration, we have to read another value, then we have to place the address in the next. So that's why here we will check the condition. See, if head is equal to null, so initially consider the head. So we have to consider the nodes head, tail, temp. So all are the pointer values. All are the pointer variables. So that's why similar to our new. Right. If head is equal to null, then we have to assign the head and tail to this same node because initially this both are null. So head doesn't points to any node. Similarly, tail doesn't points to any node. Now we have inserted one element. So automatically the head and tail will be pointing to the single node, the same node. That's why we can say here head is equal to new, tail is equal to new. So automatically after executing this statement, so this is the head, this is the tail. Right? So all the three, new, head, tail, all are pointing towards the same node. Now else, now this part will execute if in the second iteration, from the second iteration, right? So after completion of the first iteration, second iteration, it will again read the value. So 20, if you read the value 20, and one more node is created here. Right? Now new is this one. So this is not a new. This is only head and tail. See, this is the second iteration. So 20 is the element. So initially after reading the value, new of previous is equal to null. So here it is null. Data is equal to value. So here 20 will be placed. Next is equal to null. Again null. Right? Then see, if head is equal to null, head is not equal to null because So let it be 1000 is the, okay, we will write here 1000 is the address of this one and 2000 is the address of this one. So head is pointing to the 1000 memory location, so head is not equal to null. So that's why this is condition fails, automatically else part will be executed. In the else part we have to write what we have to write. So we have to place the previous field, that means the previous address field should be holding the address of the previous one, right? And in the head, the next field, the next address field should hold the address of new. Hope you understood, right? So this should not be null and this should not be null, because this is not a single element, it is having the second element. So first element have to store the address of second element, and the second element, in the second element it should hold the address of first element in the previous field, right? So that we have to do that. See, first tail of next, tail of next. So tail of next is equal to, tail of next means this one, tail of next. What it should be? Tail of next 2000 should be placed here, right? So 2000, because 2000 is the second node, the address of second node should be placed in the address field of first node. So tail of next is equal to new. Tail of next is equal to new. Now here we have to place, in the null place we have to store the address of head, right? So here it should be 1000, because this is the previous one, right? This is the previous one. Now what is the position here? New of previous. New of previous is equal to tail. Why we have to take the tail? Why we should not take the head? This is the question. Because this is the second element. If you go with the third element, if you place the address of address of head there, automatically it will be wrong. So we have to move the tail from first element to second element. So our next one is tail is equal to new. Tail is equal to new. So automatically here the tail will be released and it will be assigned here. Okay. So hope you understood this one. Now see, this is the second iteration. In the third iteration, if you place 30, so one more node is created here. Right. So see, 30, new of previous is equal to null. So this is null. So it is new. Right? It is new. New of data is equal to value. So 30. New of next is equal to null. Again, null. Right. If head is equal to null, head is not equal to null. So else part will be executed. Tail of next equal to new. What is the tail? Tail of next. So this one, tail of next. See, this is the next part. So tail of next is equal to, let it be the address is 3000. Tail of next equal to new. So that means 3000 will be placed here. So automatically a link will be established from here to here. Next, new of previous. What is the new of previous? Here new of previous is equal to tail. That means 2000. So here we have to place 2000. Okay. Next, tail is equal to new. So tail will be replaced here and the tail will be here. Right? So whenever you place the 2000 here, a link will be established from previous node to current node to previous node. Right? So this is how a double linked list can be created. Okay, this is also very simple concept. So all these should be written under some loop, right? So iterations. So we have to repeat these statements until we want to exit, right? So hope you understood this create method, create logic, a simple logic, right? So I am not giving the program completely, just I am explaining the logic. So if you draw the diagram and if you trace every statement, automatically the concept will be very easy, right? So hope you understood this create method, create operation. Now we will go with the display operation. So once you created this one, then how to display the elements of a double linked list. So that is a normal logic which we have seen in the linked list and the circular linked list. See, the same thing we will follow. So hope you understood this create, how to create a double linked list. See, the second one is display. So how to display the elements of a linked list. So we will go with this one. So we have to travel this one. So first just assign head to temp, because we have to travel from first node to the last node. So while temp of next not equal to null, temp of next not equal to null, or simply we can write temp not equal to null. So anything is no problem, right? So temp of next not equal to null or temp not equal to null, right? So if you write the temp of next not equal to null, it will display up to here, and out of the loop we have to again display the temp of data. So if you write the temp not equal to null, it will move until the last node, right? So here what we have to do, we have to print every element. What is the element here? Printf %d temp of data, right? So if you want to print the data, statement is temp of data, and we have to, after printing the element, we have to move the temporary value. So temp is equal to temp of next, and close this one. So this is a simple logic for displaying all the nodes of a double linked list. So in the first one, temp not equal to null, first temp is equal to head, so here the temp will be here. So temp not equal to null, so temp not equal to null, so 1000, here temp is equal to 1000, so not equal to null, it's true, so it will display temp. Next, temp is equal to temp of next, so temp is equal to temp of next. So what is the temp of next? 2000, so temp will be here at the 2000 position. Now again temp not equal to null, so 2000 not equal to null, so obviously temp of data, it will enter into the loop and it will print temp of data. So 20 will be printed. Next, temp is equal to temp of next. What is the temp of next? 3000. Temp of next. This is the temp of previous, this is the temp of next, this is the temp of data. So temp of next is 3000. So it is assigned to temp. So now the temp is assigned to the next element. So temp not equal to null. 3000 not equal to null. True. So temp of data will be printed. So temp of data 30 will be printed. Temp is equal to temp of next. So what is the temp of next? Null. So temp is equal to null. Again, temp not equal to null. So condition false. Automatically it comes out from the loop. Right? So in such a way we can display all the elements of all the nodes of a double linked list. In this session we will go with another operation called insertion. So which we have seen in the single linked list and circular linked list. So insertion, all the three cases, that means inserting the element at the beginning, inserting the element at the ending, and inserting the element at specific location, at specified location. Right. Let us start the session. Double linked list. Right. Now, so let us say take one linked list and then we will trace the logic. See, let us have it will be having two links, the forward link and the backward link. Right. Let us take the three nodes first. Let us consider only the three nodes. So the address of this node is 1000, address of this node is 2000, address of this node is 3000. So let it be 10, 20 and 30. So here the previous, there is no element, so it is null. The next element address, that is 2000, the previous element address 1000, the next element address 3000, the previous element address 2000, and next there is a last node, so it will be filled with null. And this is the tail and this one is the head. Right. Now the question is, if you want to add an element, that means insert an element at the beginning position. See, so we will again draw this one. Right, sorry. Right, let us draw here. So this is the insertion. The insertion first at beginning. Insertion at beginning. So if you want to add this one, see, add the element. So for this, first we have to allocate the memory dynamically. That's the common thing. U is equal to struct node star malloc size of struct node. Right. Now a memory is allocated for the new, so let it be some 500. Okay. Now, so this one is a previous data next, and this is the new. This is the new. Now, see, I will write here itself. Okay, this is the new. Now, what we have to do? First, we have to read an element. So, scanf %d ampersand value. So a value is inserted, so let it be some 5. The value read from the keyboard is 5. So first step is just place the value in the data. So the new of data is equal to value, so automatically 5 will be placed here. Right, hope you understood this one. Then we have to fill the previous node and the next node. So this is, if you insert an element at the beginning, the previous node will be null. So new of previous is equal to null. So automatically here we can place null. Next, what should be stored in the next address field? So here the address of head should be placed. So new of next is equal to head. So automatically 1000 will be stored here. So a link will be stored here. Now the reverse link also to be connected. That means head of previous. So this is the previous data next. Head of previous should hold the address of new. So head of previous is equal to new. So after executing this one, this null will be replaced with the address of new, that is 500. So hope you understood this one, right? Now we have to move the head, because here, so whenever you place this one, automatically another link, the reverse link will also be established. Now here this is the second element. Now head is pointing to the second element. So we have to move the head to the first element. So head is equal to a new. That means here head will be replaced with, head will be moved to new. Right? So this is a simple logic for inserting an element at the beginning of a double linked list. Right? So here we have to take care about the address we have to store in the previous field and address to be stored in the next field. So that means for every node there must be two connections, one to the previous, another to the next. That should be remember carefully. Right? Hope you understood this one. It's a very simple logic. Now let us move with another case. If you want to insert the element at the last, that means end. See. Second one, ending. So just we will erase all these things. Okay, we'll erase all these things. Let it be the first node. So null should be placed here, and this is the head, and that is the tail. Now, if you want to insert the element at the end, that means here we have to place. Right, here we have to place. So this is a new node. This is a new node. So whenever you allocate the memory, some memory will be allocated here. Some 500 or 4000, whatever it may be. 4000 is the memory allocated for this node. Now we have to read the value. So if you read the value some 40, right? If you read the value some 40, so first place the value new of data is equal to value. Automatically 40 will be placed here because this is the data previous and next. Now we have to establish the connection between the previous tail node and the newly inserted node. Right, now see, so as if you insert a node, that will be the last node because we are inserting the node at the end position. So this is the last node. So if it is a last node, then we know that the next field, the address field, the next address field should be initialized to null because it doesn't point to any other node. So new of next is equal to null. New of next is equal to null. Then what about the previous one? New of previous. So it should hold the address of previous node. What is the previous node? Tail. So the new of previous is equal to tail. So here null, and after executing this one, new of previous is equal to tail. This 3000 will be here. So a link will be established here. Right? And one more statement should be written because the reverse connection also to be established, because here tail of previous is null. That means it doesn't holds the address of the last one. So it should hold the address of last one. So that's why, what is the field here? Tail of next. So previously it is null. So with which we have to replace with a new value. So the new value is replaced. So here the null will be replaced with the address of new, that is just replace 4000. So automatically a link is established here itself. Right? So hope you understood. Now we have to move the tail, because tail is assigned to the last but one. So we have to change the tail. So tail is equal to new. Automatically here the tail will be replaced and here it will be allocated. Right. So this is a small logic, simple logic for inserting an element at the end position. So if you draw this one and if you trace one by one, automatically the code will be very simple. Right? So now let us move on with the third case, that is inserting the node at specific location. Right. Right. See. Third one, specified position. Right. So here we need to read the two inputs. One is the value, another one is the position. Right now we have to read one more thing, that is a position. So let us take the position 2 and the element is 25. Right, the element is 25 and the position 2. So here we have to insert this 25 at the position 2. So here the position of this one is 0, 1 and 2. So here we have to insert the node. Right. So first of all, let us travel this one to that position. So assign temp is equal to head. So initially the temp will be here. For I is equal to 0, I less than position minus 1, I plus plus, we need to move the temp from one node to another node. Temp is equal to temp of next. So after first iteration, the temp will be moved to here. The temp will be moved here. Right? Now, after the second iteration, the condition fails, comes out from the loop. Now we have to replace all these things. So first we will place the data. So new of data is equal to value. That means here 25 will be placed. So this is the new. This is the new. So 25 will be placed in the value. Next we have to place the new of next. New of next. So new of next. So what should be filled here? New of next should be 3000, which is nothing but temp of next. Right? Don't get confused. New of next, that means it holds the address of the next element. What's the next element? 30. What's the address of 30? 3000, which is nothing but temp of next. So simply we can write temp of next. Then so here we can have 3000. Okay, here we can have 3000. Now we have to replace this one, because this should be let it be, the address will be 2500 here. So what about this one? Temp of next of previous is equal to, temp of next means 3000, 3000 previous 2000 is equal to, here it should be new, so 2500. Okay, so it maps here. Okay, it maps here. Now we have to replace this one. What is this one? So new of previous, new of previous. Okay, the new of previous must be filled with temp of previous. Okay, the temp of previous. So or we can simply replace this one. See, temp of next, here it should map the, it should point the address of new. So here we can write temp of next is equal to new. Simply here we can get 2500. Okay, it maps here. Okay, now what should be placed here? It should hold the address of previous node. What is the address of previous node? 2000. What is the 2000? Temp. So new of previous is equal to temp. New of previous is equal to temp. That means here the temporary variable. The temporary variable means 2000. So 2000 will be placed here in this position. So okay. So this is how we have to write the code for inserting the element at the specific position. Okay. So first we have to allocate the memory for the new, and then we have to read the value, we have to read the position, and then we have to travel up until the position -1, and then so this is the new node. So we have to fill the new of previous, new of data, new of next. So here first new of data is equal to value, so 25 will be printed, stored there. Then new of next. What is the new of next? It should hold the address of the next one. What is the address of next one? Is 3000, which is nothing but temp of next. So temp of next. Next, temp of next of previous. That means this field should be executed. Next, the previous field of next node should be holding the new. So temp of next of previous. Temp of next is 3000. 3000 of previous is 2500. Is equal to, this position is equal to new. New means 2500. So 2500 will be replaced. Next, temp of next. Temp of next means this field should be replaced. So before it is allocated with the next one, that is 3000. So temp of next is equal to new. So 2500 will be replaced. Now new of previous. What about the new of previous? New of previous is equal to temporary. So 2000 will be stored. Right? So hope you understood this one. So don't get confused. Simply draw the diagram, draw the nodes, so that everything will be clear. Location. In this session we will go with the another operation, that is deletion. So how to delete an element from the double linked list. Right. So just an introduction. So just let us recall this double linked list. So here in this double linked list, every node is having two links. One holds the address of the previous node, and another holds the address of the next node. Right. Now let us see the deletion operation. Deletion. So here also we will see the three cases. First let us see the logic for deleting the element from the beginning position. So let us consider a double linked list, and then we will see that. See. Right. So let us take 4 nodes. So the node 1 is having a address location 1000. So it is 2000. It is a 3000. It is a 4000. This is the memory location, right? So 3 fields, every node is having previous, data, and next. Here also let us have a 3 fields. Here also let us have a 3 fields. Here also let us have a 3 fields. See, the first one is 10, 20, 30 and 40. Yes, so in the previous node of the first element, it will be null because this is the first element, right? This is the first node, so it doesn't hold the address of the next previous node. So because it is a first node, so the previous will be filled with null. And next one means it holds the address of the next one, that is 2000. So coming to this 20, it holds the address of the previous, so 1000 here, it holds the address of next 3000 here. Right? Next, coming to the 30, it holds the address of previous, so 2000, it holds the address of next, so 4000. Coming to the 40, it is the last element, so it holds the address of previous, so 3000, and it is the last element, so the next is filled with null. Right? Hope you understood. Now it is having a double link. So single linked list is having only one link, that means we can travel from starting node to ending node. So the reverse process is not possible. So here it is having a double node. So both way we can travel from starting point to ending point or ending point to starting point. Right. See, so here the deletion of a node means we have to delete the data or we can disconnect the link between the nodes. Right. So the first case, deletion at beginning. Deletion at beginning. See, this is the head, this is the tail. Right. So if you delete the beginning, which element should be deleted? 10 will be deleted. Right. So 10 will be deleted, so that we have to disconnect the link between the 10 and 20. Right. 10 and 20. See, automatically if you if you delete this one, this position must be null, right? And this node will be the first node. So first node previous field must be null, right? And head should be moved to here. So three cases. Hope you understood. So if you place null in this position, automatically link will be disconnected and this will be the first element. So as this node is the first element, it should not map or it should not hold the address of any other node, right? So in the previous field, so in the previous field we have to place null. So all these three cases should be done. See, first let us move the head. So just store the head in temporary variable. Store the head in temporary variable. So now this is a temporary variable. Now move the head from this element to the next element, because after deleting the first element, second element will be the head. So that's why before disconnecting, you just move the head to the next, head of next. So after executing this one, this head will be moved to second element. Right? Head is equal to head of next. Now head of next means 2000, so head is moved here. Now what we have to do? We have to place null in here. So what is the position of this one? Temp of next. So if this node is a temp of previous this one, temp of data is this one, temp of next is this one. So temp of next is equal to null. So automatically this position is null. So obviously the link between these two nodes will be removed. Or simply we can use a free function, right? So free function is used to deallocate the memory, right? So dynamic memory allocation, that is the fourth fourth function, free function, which deallocates the memory. So automatically we can free the temporary variable so that the memory will be deallocated. That's another way, right? So here we are disconnecting the link. After executing this one, the link is disconnected. So this is the double linked list with head pointing to the 20. But here the problem is, here 20 node, the previous field is holding the address of another node, right? So that's why this position also to be set to null. So what is this position? Head of previous. Head of previous is equal to null. So 1000 will be replaced. So hope you understood. This is the head of previous, head of data, head of next. Here it is null. Okay. Now you can see this. This is a double linked list after deleting the first node, that is 10. Right? Now head is pointing with the first node because previously, head of previous is null because it is not holding any other node. Right? And 40 is the end because it doesn't holds any other address after this node, because tail of next is equal to null here, right? So this is a simple logic for deleting an element from the beginning, right? Now let us consider this one. And now let us check how to delete an element from the ending. So now we have to delete an element from the end position, that is 40 should be deleted. This 40 should be deleted. So if 40 should be deleted, what is the last element? 30 is the last element. So if it is the last element, we said that the next field, that means address field of 30 should be filled with null, and tail should be moved towards its previous node. So let us take temp is equal to tail, right? Temp is equal to tail. So here this is a temp. Now move the tail to the previous. So tail is equal to tail of previous. Automatically the tail is moved to previous node. So tail is moved to previous node. So if it is a tail, the tail of next should be null. And before going to that, the temp, that means a 4000, that 40 node previous is having the holding the address of the 30, right? Here there is a 3000 which is the address of 30. That means there is still a link between the last node and the tail, temporary node and tail. Now we have to place null at the previous field of 40. So what is this one? Temp of previous. Temp of previous is equal to null. So automatically here the 3000 will be removed and null will be placed, so that the link is disconnected now, right? The link is disconnected, and then still the problem is not solved, because here 30 is the last element and the next field holds the null value for the last element, but here it is holding the address of 40. So here we have to place null at the tail of next, right? So tail of next is equal to null. So here 4000 is replaced with null, right? Now there is no link between the 30 and 40. So automatically the head is 20 and tail is 30. So that implies we are deleting an element at the end position, right? Yes. So hope you understood these two cases, beginning and ending. Right. We will move on to the next one, that is how to delete an element from the specific position. See, we'll go back with the example. See, here it is a 4000, here it is a 3000, so a link, and here it is a 1000, so there is a link, and here it is a 2000, there is a link, it is a head, and this one is a tail, right? Now we will see the third case. Third case. Right. Now, see, third one, deleting an element from the specified location. Excuse me. So here we need to take a value, that means we have to read a value position. So from where we have to delete the element. So we have to write the first statement scanf %d ampersand position. So here we have to take input as of position. Let it be 2 as usual. So in all the cases we are going with the 2, right? So let us take a 2 itself. So 2 second position means 0th position, first position, second position. So this position should be deleted. This position should be deleted, right? Now see, first let us assign head to temp so that we can travel, right? So just move the temp, because if this element is deleted, see, just observe, if this element is deleted, so what is the position of this one? So 20 of next should be the address of 4000, I mean the address of 10. Is it right? Yes. So this should be changed to 4000. And what about this one? It should hold 2000, because this is one. So if you delete this one in the absence of this, so while 20 holds the address of next one, that means 4000, and 40 holds the address of previous one, that is 2000, right? Now we need to change these two fields, okay? Then automatically if you change these two fields, this field will be deleted, disconnected, automatically disconnected, right? See, first let us move the temporary variable till the position -1, because here we have to change. So for loop I is equal to 0, I less than position -1, I plus plus, just move the temporary variable. So temp is equal to temp of next. See, let us observe till this one. So if I is equal to 0, right, see, first temp is equal to head. So initially the temp is here itself, right? So okay, it's not visible for you, I will write here itself. Okay, this is the temporary variable. Now I is equal to 0, 0 less than position -1, 2 minus 1, that means 1, right? 0 less than 1, true. So temp is equal to temp of next. So initially temp is this one, temp of next means 2000. So temp is equal to 2000. So automatically the temp is moved to this position, right? So temp is moved to this position. Now again I plus plus, now I is equal to 1. So 1 less than 1, false. So just stop the iterations. Now temp is at position -1. Now what we have to do? We have to replace this with this one. Simply we can say that temp of next is equal to, so in this position what we have to place? 4000, right? 4000. So how this 4000 will be? Temp of next. See, so temp of next means 3000, 3000 of next means 4000. So 4000 is assigned to here. So don't get confused. Temp of next is 3000. 3000 of next means 4000. So here after executing this statement, so 3000 will be replaced with 4000. Right? Now this connection is disconnected. This connection is disconnected. Now we have to replace this one, and 4000, if it is a 4000, so it is connected here. Now we have to change this 3000. How to get this one? Temp of next means 4000, 4000 of previous. Temp of next of previous, right? Temp of next means 4000 of previous. 4000 of previous means 3000. In this position, what we have to keep? We have to keep this 2000. So is equal to simply temp. So automatically in this position, instead of giving 3000, it will place it there 2000. So again this link is disconnected and it will be moved to this one. So automatically this link is discarded. I mean this node is discarded. Right? So hope you understood this one, a simple logic. So we have to replace the next and previous value. So if you are deleting the 30, the 20 element next value should map with 40 element, and the 40 element previous field should map with 20 element. So that's why we are using this one, temp of next. Temp of next means this location. To that location what we are assigning? Temp of next of next. So initially there is a 3000, temp of next is 3000, of next 3000 of next, that means 4000. So 4000 is placed at temp of next. Next we have to replace this position. What is this position? Temp of next, next of previous. So temp of next is 4000, 4000 of previous, 4000 of previous means this one, right? This position is equal to temp. Temp means 2000. So 2000 will be placed there, right? So logic is clear and a simple. Sorry, this is completely out of loop. Yeah, it ends the loop and this completely out of loop, right? So hope you understood this one. So how to delete an element from the specified position. So in today's session, let us see about the another linear data structure, stacks. So first point, it is a linear data structure. So stack is a linear data structure. So linear data structure means all the elements are arranged in a sequential manner. So elements are arranged in sequential, right? Then it follows the last in first out mechanism. It follows LIFO, that is last in first out mechanism. So here the name itself indicates whatever the element inserted into that stack last, that should be removed first. So last in first out, whatever the element is inserted at the last, that should be removed first, right? Last in first out. The best example for this stack is arranging the plates in a tray. Plates in a tray, or coins, arranging the coins. Arranging the coins or books. So whatever it may be, anything we can consider it as an example, right? So consider these plates, arrange the plates. So if you consider a tray and if you start inserting the plates, so the first plate will be here, the first plate will be here, and the second plate will be on the above of the first plate. So the second plate will be placed on the above of the first plate. Third plate will be inserted here. Fourth plate will be inserted here. 1, 2, 3 and 4. Right? Now a tray consists of 4 plates. So if you want to remove the plate, which plate should be removed first? The fourth plate should be removed first. We can't remove the first plate. The fourth plate should be removed first. That means whatever the element which is inserted last, because in these 4 plates, what is the element which is inserted in the last? That is 4, plate 4. So that should be out. That means that element should be removed first, right? So see, here it is having 2 operations mainly. One is push operation, another one is pop operation. Push and pop, 2 operations. Push operation means inserting an element. Inserting an element. Pop operation means deleting an element. Right? Right. Inserting an element into the stack, deleting an element from the stack. That is pop. These 2 operations can be applied for stack. Next, here both the insertion and the deletion can be performed on only one side, that is at the top of the stack. So if you want to insert an element to the existing stack, we have to place that element at the top of the stack. And if you want to delete the element, you have to delete the element from the top of the stack. So either insertion or the deletion, both the operations can be performed on only a single side, that is top. So we can use a TOP, top, is it? Top of stack. So where can be performed both push and pop operations. In the top of the stack, both push and pop operations can be performed. Initially, if there are no elements in the stack, this top is equal to -1. If the top is equal to -1, initialization, right? Initial value of the top. So if the top is -1, that implies the stack is empty. No element is presented in the stack. And if you are trying to insert an element into the stack, first we have to update the top and then we have to insert the element. Similarly, if you want to delete the element from the stack, you have to delete the element from the stack and you have to update the top, right? You have to decrement the top, right? So now this stack can be implemented in 2 ways. I'll write here. So implemented in 2 ways. What are they? First one, using arrays. Second one, using linked list. Right. So 2 ways we can implement this stack, by using the arrays and linked list. So in today's session we will see the operations of push and pop. So these will not change. Okay. Only the implementation will be changed, but everything is same for both the cases. If you are implementing stack using arrays, the same thing will be applied. If you are implementing the stack using linked list, the same things will be applied, right? So the only difference is implementation part. So in the arrays we need to take the maximum number of elements prior to the insertion or a deletion, right? We need to take the size of the array. So coming to the linked list, we need not take the size of the array first, because size of the stack, because there we will use dynamic memory allocation, right? Here we are using the static memory, right? That means before starting the stack itself, before inserting the element into a stack itself, we have to decide the size of the stack. Okay, then let us see the push and pop operations of stack, which is implemented by using arrays. So hope you understood this one, right? So it's a linear data structure. It follows the LIFO format, the mechanism, and 2 operations will be there, push and pop. Right. There are two more concepts. Just I will explain and then we will go with the operations. See. So while implementing the stack, we need to verify two conditions. That is overflow condition and underflow condition. So while implementing the stack, either using arrays or a linked list, we need to check these two conditions, overflow condition and underflow condition. When this overflow condition will occur? When you are trying to insert an element into the stack already which is having the maximum elements, then this overflow will be occurred. For example, if stack consists of 5 elements, if you are trying to insert 6th element, into the stack which can hold only 5 elements, then this overflow condition will be occurred. Right? That means this will be used in push operation. That means we need to check the condition while performing the push operation. So inserting an element to the stack which is already having maximum elements, right? So this occurs when we are inserting an element to the stack which is already having the maximum elements. Then underflow condition. Underflow condition means the reverse. That means if you are trying to delete an element from the empty stack, so there are no elements in the stack, but still you are supposed to remove an element from the stack, right? So then this condition will be occurred. That means deleting an element from the stack, from the empty stack. Simply we can write from the empty stack. Then automatically this condition will be occurred, underflow. So that means this condition is to be checked at pop operation. In the push operation we have to check this one. In the pop operation we have to check this one. Right. Now let us go with the direct functions push and pop. Right. So implementation of a stack. Using arrays. So we will go with the arrays, right? Right. So in this we need to give the size of the stack before starting the insertion, right? So static memory allocation. So we need to give the size of the array. Let it be 10. That means maximum 10 elements can be inserted. And initially the top is equal to -1. That means let us take here right. So let us consider here top is equal to -1. Right. So coming to the push operation, first we need to read the element because this is an insertion. Push means insertion. So read an element. So scanf %d. Let us read a numerical element, right? So we are reading an element, so we need to insert this element into the stack. So we need to declare the stack also. We need to declare stack also. Stack, it's an array. It's an array of size 10. Stack is an array of size 10. So in the push operation, we need to check the overflow condition. So if top is equal to size minus 1. So here top is equal to minus 1 initially before inserting any element. That means 0 elements. Size is 10. So size is 10 means the index values will be from 0 to 9. That means size minus 1. So for every insertion we need to update the top of the stack. So if the top of the stack is equal to size minus 1, that implies the complete elements are inserted into the stack. That means the stack is full. So if this condition is true, we can print overflow, or simply we can print stack is full. Else, that means if this condition is fails, that means there is a vacancy in the stack to hold the element. Then we need to increment the top first, because initially top is minus 1 and after inserting the element top will be at 0. So first we have to update the top. So top plus plus. So we need to update the top so that the top will be updated to the next position. Then we have to insert the element at that position. So here if you, let us take the position top plus plus, top is equal to 0. So here it is, top is equal to 0. Now we need to store the element in this position. So then stack of top is equal to element. Stack of top, that means stack of 0 is equal to element. So let it be 10. The 10 will be inserted here. Right? So close the braces. So this is a simple push operation. Coming to the second iteration, right? So again, if you apply this push operation, again it will read an element. Let it be 20. Top is equal to size minus 1. Top is 0 is equal to 9. Condition fails. Again top plus plus. Now top is equal to 1. Right? Stack of top, stack of 1 is equal to 20. So 20 will be inserted here. Again, if you again call the push operation, 30. So top means 1. 1 is equal to 9. Again false. So again else condition. Top plus plus. Initially now top is equal to 1. Top plus plus means top is equal to 2. So obviously stack of 2 is equal to element 30. So 30 will be inserted here. Okay, so hope you understood this one, right? So initially first we have to check the overflow condition. If it fails, then we have to increment the top and then we have to insert the element into the stack. And the only disadvantage of this implementation is, before starting the implementation, we need to specify the size of the stack. So beyond that size, an element cannot be inserted into the stack. That's the main drawback of implementing the stacks using arrays, right? So coming to the linked list, there we will use the dynamic memory allocation, so there is no restriction to the size of the stack, right? Now, so hope you understood this push operation. Now we will move with the pop operation. See, after inserting the elements, the top is assigned to 2, right? Now pop operation. Pop means deleting an element. So before deleting, we need to check the underflow condition. That means whether we are supposed to trying to delete the element from the empty stack or not. So for that we need to check the underflow condition. So if top is equal to minus 1. So obviously if you are not inserting any element, then the top is always initialized to minus 1. If you insert an element, automatically the top must be get updated, so top will not be equal to minus 1, right? So if top is equal to minus 1, we can say that printf underflow. So if it fails, that means else condition. If it fails, then we have to remove the element which is available at the top, right? So here we have to remove the 30 element. We can't remove the 20 and 10 until you remove the 30, right? So that's why else, what is the element to be removed? So element is equal to stack of top. That means here the removing element is stack of top. That means stack of 2. Stack of 2 means 30. So that element will be removed, and after removing the element, this top should be updated. So top minus minus. So automatically top is equal to 2. After applying this pop operation, top will be 1. Right? That's all. This is a simple pop operation. Okay, a simple pop operation. Again, now top is equal to 1. Again, repeat the, if you want to again remove the pop, if you again apply the pop operation, then top is equal to minus 1. 1 is equal to minus 1, false. So else the element is equal to stack of 1, 20. In the second thing, if you want to again apply this pop operation, 20 element will be deleted and top minus minus. Now it will be 0 at 0. Again, if you apply this top, if you call this pop operation, next 0 is equal to minus 1. Again it is false. So element is equal to stack of 0. So element is equal to 10 and top minus minus. So it will be minus 1. Now automatically the elements of the stack is, see, after applying the pop 3 times, the top is equal to minus 1. Again, if you are applying the top, pop operation, the top is equal to minus 1. That means minus 1 is equal to minus 1. It's true because there is no element available in the stack. So that's why it will be printed underflow. Right? So hope you understood this pop operation also. Simple operations. First you have to delete an element and then we have to reduce the top. That means update the top, decrement the top. Right. Next, how to display the elements of a stack. Display function. We will see the display function also. If a stack contains 4 elements, so top is equal to 0, 1, 2, 3. So top is equal to 3 now. Top is equal to 3 now. Right? So display function. How to display the elements of a stack. Simple. We need to check whether it is an empty stack or not. So if top not equal to minus 1, if it is not equal to minus 1, automatically that implies there is a, there are elements available in stack. Then use a for loop for I is equal to top, that means 3, I greater than or equal to 0, until top is equal to 0. I minus minus. I minus minus. Every time we have to decrement because we are assigning I with the top element. Here we can print the element. Printf %d stack of I. Stack of I. Close. Else, if this condition fails, not equal to minus 1, that means if it is equal to minus, we can simply write printf, we can simply write empty stack. Empty stack. Right? Let us trace it. So initially here top is equal to 3 now. Top is equal to 3. In the first iteration, top not equal to -1, right? Top not equal to -1. So 3 not equal to -1. True. So for I is equal to top, I is equal to 3. First iteration, I greater than or equal to 0. So 3 greater than or equal to 0, condition true. Then stack of I. So stack of 3 will be printed, that is 40 will be printed. Next, I minus minus, now I is equal to 2. Then again 2 greater than or equal to 0. True. Then print stack of 2, which is 30. And again I decremented. Now I is equal to 1. 1 greater than or equal to 0. You need to print stack of 1, which is 20. Right? Next I is decremented. Now I is equal to 0. So 0 greater than or equal to 0. Here we are using the is equal to also. So that's why still the condition is true. So stack is stack of 0. That is 10 will be printed. Again I minus minus. I is equal to -1. -1 greater than or equal to 0. Condition fails. It come out from the loop and it ends the display function. Right? So hope you understood this one. Simple logic for push operation, pop and display operation. Right? So implementing the stack using arrays, we will be having two operations, push and pop. Insertion, push operation, for deletion, pop operation. So while inserting an element into the stack, before we have to check the overflow condition, and while decrementing an element from the stack, we need to check the underflow condition. Right? So these three operations. So let us stop here. So the main drawback of using arrays is the static memory. So before we have to declare the size of the array. And if you want to increase the size of the array, it's not possible here unless you use the dynamic memory allocation, where we will implement in linked list. Right. So hope you understood this one. Now in this session we'll go with the another linear data structure, that is called queues. Queue. So this is also a linear data structure similar to the stack, with a little bit difference, and here also there are two operations to be verified, that is insertion and deletion. So in the stack we have seen the insertion is called as push and the deletion is called as pop. Here the insertion will be called as NQ and deletion will be called as DQ. Right? And see, this is also a linear data structure similar to the stack. So it is a linear data structure. The first point, right? So that means all the elements will be arranged in sequential manner. So elements are in sequential manner. This is the second one. Third point. So in the stack, it follows the last in first out mechanism. That means the recently added element or recently inserted element will be removed first. So here the queue is, it follows the FIFO mechanism. So it follows FIFO, F-I-F-O. That means first in, first out. So that means whatever the element inserted first, that can be removed first. Right? So best example for this queue is standing on a line for ticket reservation. This is the best example for this queue, right? Standing on a line for ticket reservation. So the person who comes first, he will get the ticket first, right? First come first serve, similar to the first come first serve. So here, in the stack, there will be a top position, and both the insertion and deletion will be done at the top position, right? So here the insertion and deletion will be performed on different positions. See, here two operations will be there. First one, NQ and DQ. So NQ is inserting an element into the queue. DQ means deleting an element from the queue. Right. So NQ is inserting an element, DQ is deleting an element. And also there are two conditions to be checked while implementing these NQ and DQ operations. Two conditions are overflow condition underflow condition. Overflow and underflow. See, these two we have seen in stack implementation. So the definition is same. So overflow means insertion into queue which is full. Underflow means deletion from empty queue. See, full. So that is called overflow. This is called underflow. So overflow condition must be checked in NQ operation, and underflow condition to be checked in DQ operation, right? Then, so in the stack we have seen another thing that is called a top, TOP, which is a top of the stack. So both the push operation and pop operation will be performed on the same thing, that is top. Here the NQ will be performed on one position and DQ will be performed on another position, right? Let's go with that, and then we will directly go with the implementation part. Right. Here there will be two ends. Front, rear. Front points to starting element, whereas a rear points to last element. And here also we need to specify the size, okay? So that we will see later. So front and rear. So NQ operation, NQ means insertion, will be done at rear end. At rear, similarly DQ will be done at front. That's the only difference. And now the representation of the queue is in this way. So this is the front, this one will be the rear, right? So okay, front and rear. Here we will perform DQ, here we will perform NQ. So if you want to insert an element into the queue, that will be inserted here. If you want to delete an element from the queue, it must be deleted from here, because the first element entering into the queue will be the first element to be removed, right? So this way we have to represent a queue. So this is a queue. This is a queue, front and rear. Okay, so if you are right, so initially the front and rear will be initialized to -1. Initially front is equal to rear is equal to -1. So if you want to insert an element, first we need to update the rear and then we have to insert an element. If you want to delete an element, first we want to retrieve that element which we want to remove, and we need to update the front, right? Hope you understood this one, right? Now, like, we will go with the implementation part. Implementation. How the queue can be implemented? Here also a queue can be implemented in two ways. So first one, by using arrays, another one by using linked list, right? In two ways we can implement this queue. Now in this session we will go with implementation of queue by using arrays, right? In the later video we will see the implementation of queue using linked list, right? Queue using arrays. Implementation of queue using arrays. Now see, initially the front and rear will be -1, and if you are inserting an element, then first rear should be updated, right? So let us see this. First one, we need to fix the size of an array, because it is a static allocation. Before starting the queue itself, we need to specify the size, fix the size. So later we can't update the array size. That's the main drawback of implementing the queues using arrays. The same drawback we have seen in stacks also. So that's why we will move on to the linked list. Now let us take the size as some 10, right? Next, front is equal to rear is equal to -1. So both are equal, front and rear both are equal, and both are initialized to -1. Now after every NQ operation we need to update this one. After every DQ operation we need to update the front, right? Now let us go with the, so also declare a stack, I mean queue array with a size 10. Now we will go with the NQ function. So in the NQ, first we are supposed to check whether the stack is full or not. If the stack is full, then the insertion operation need not be done, right? So we can't insert the element out of the size. So we have to check the queue full. So if rear is equal to size -1, So after every NQ operation we are updating the rare, right? So rare points to the last element of the queue, so which we have discussed just now. So that's why if rare is equal to size minus 1, so here the size is 10, so the size of the queue is from 0 to 9, that means size minus 1. So if rare is pointing to the size minus 1, automatically that is a queue is full, so we can't insert an element into the queue. So that's why if rare is equal to size minus 1, simply printf overflow condition, or simply we can print the queue is full. Else, so if it is not size minus 1, then we can insert an element into the queue. So first read the element, scanf %d ampersand element. Here again we need to check one more condition, that if front is also minus 1. So because we have to update the front also. So initially this is a queue, this is the queue, so front and rare are minus 1. So if you insert an element here, let it be 10, rare will be updated, so rare will be pointing here, but still the front is equal to minus 1. So front should point at the top element, I mean first element. So if we have to check that condition, if front is equal to minus 1, what we have to do? Just assign it to 0. Then front is equal to 0. Right. So if it is minus 1, is equal to 0. Then after completion of this condition, before inserting, what we have to do? See. So here an element 10 is taken from the keyboard, and now front is equal to minus 1, so front is equal to 0. So this is the 0th position, 1, 2, 3 and 4. Now front is pointing to here. Front is pointing towards here, this position, right? So let us consider it as F, okay? So F is pointing here. Now rare is equal to minus 1. So in order to insert an element, we need to update the rare, right? So open the brace, close the brace. So just to avoid the confusion. Here we need to update the rare. So rare is updated. So rare minus 1. So rare is updated. So the rare value will be here. So that means pointing towards 0. So at the 0 we have to insert an element. So Q of rare is equal to element. So now the 10 will be here. Now the 10 will be here. That's all. Close and close. Once again, if you call this NQ operation, see, rare is equal to size minus 1. Now rare is pointing towards 0. 0 is equal to 9. False. It comes here. It reads the element. If it reads the 20, then if front is equal to minus 1, front is not equal to minus 1 because front is already initialized to 0. That means it's pointing towards the first element. That's why this condition is false. This is a simple if condition, right? Then rare plus plus 0. Now rare will be pointing to 1, right? Then Q of Q of rare is equal to element. Q of 0, so sorry, Q of 1 is equal to 20. So 20 will be inserted here. So this is the rare position. And again, if you want to insert another element, then again you call the NQ operation. So rare is equal to size minus 1, 1 is equal to size minus 1. So condition false, else condition, it reads another element. So 30. So front is equal to minus 1, front is not equal to minus 1. So condition fails and out from the conditional statement. Rare plus plus. Now rare will be pointing towards 2. Q of rare is equal to element. So here the 30 will be printed. Similarly 40. In the next call, right? In the next call, the 40 will be printed until this condition becomes false. If this condition becomes true. If it is true, we can't insert an element into the queue. So this is how we can insert an elements into the queue. So insertion always done at the rear end. Okay, that we should remember. So here there will be two positions, front and rear, and all the insertions will be done at the rear end. So first we have to update the rear and we need to insert the element into the rear. Now let us move on with dequeue operation, that is how to delete an element from the queue. So hope you understood this insertion operation. It's a very simple thing. Dequeue. So this is also function. Let us write the function itself. Right. So dequeue means deleting an element from the queue. So where we have to delete? From where we have to delete? So all the elements will be deleted from the front end. Right? Front end. So before deletion, we need to check the condition, that is underflow condition. If rear is equal to minus 1, if rear is equal to minus 1, simply that implies our queue is an empty queue, because if you want to insert an element first, compulsory we have to increment this rear. So if rear is equal to minus 1, that implies our queue is empty. That means no more elements available in our queue. So simply we can write printf underflow, or simply we can write empty queue, else. So if it is not an empty queue, then what we have to delete? The first element should be deleted. So element is equal to, this is the array, queue of front. So 10 will be assigned to element. So we can write the printf %d is deleted. Percentage, what is the %d? Element, right? Then we need to update the front, because we have deleted 10. So 20 is the first element. So we have deleted the 10. So deletion means just we are pointing towards another one, right? So the memory will be same. We are not freeing the memory, right? So 20 is, now the first element of the queue is 20. So we need to update the front. So front plus plus, front plus plus. So front will be moved to here now, right? Okay, then close. Hope you understood. Every time the element is deleted from the front end and we are incrementing the front. And here we can also check the condition. Rear is equal to minus 1, or front is greater than rear. This is also one condition. So if front is greater than rear, so deleting one by one element, the front will be pointing towards here. So 4 is greater than 3. That means no more elements are there in array. In queue. So that's why we can check this condition also. Front greater than rear. Front greater than. So if any one condition is true, automatically that indicates this is underflow. That means the queue is empty. So this is how we can delete an elements from the queue. See, rear is equal to minus 1, false. So initially let us see here itself. Underflow, else element is equal to queue of front. So 10 will be removed and front plus plus. Now front will be pointing towards 20. Again, if you again apply this dequeue operation, rear is equal to minus 1, false. So 1 is greater than 4, false. So total false, else part will be executed. So element is equal to queue of front. So 20 will be deleted and front plus plus. So front will be now here itself, right? Again, rear is equal to -1 false, front greater than 2 greater than 3 false. So element is equal to q of front. 30 will be deleted here. And front plus plus. Now front is pointing towards the same thing R. Rear is equal to -1 false, front greater than 3. So 3 greater than 3 false. So underflow again false. So else part will be executed. That 40 will be deleted. And front plus plus. So now front is pointing towards 4. Now again, if you are applying this, I mean if you are deleting this DQ operation, I mean you are applying this DQ operation, rear is equal to -1 false and front greater than rear. So 4 greater than 3, condition is true. So underflow, that means our Q is empty. So this is how we can apply the deletion operation on Qs. Right? So hope you understood this insertion and deletion, NQ and DQ. Now we'll go with the third one, that is display. How to display the elements of a queue. That's also a very simple thing. So this is the rear, this is the front. Right. Now display operation. So we need to display all the elements of a queue. First, let us check whether it is a empty queue or not. So for that we need to check if rear is equal to -1 or front greater than rear. So this is also condition. If any one of these condition is true, automatically we can say it is a empty queue. Empty queue. Right? Else, so if it is false, then we need to print all the elements from front to rear. So we need to use the iterative statements. For I is equal to front, simple for loop. I less than or equal to rear, I plus plus. Here we can print %d q of I. Simple display function, right? So I is equal to front. So I is equal to 0. 0 less than or equal to 3. True. So Q of I. So Q of 0. That means 10 will be printed. Next, I will be incremented to 1. So 1 less than or equal to 3. True. So Q of 1. That is 20. Next, I is incremented. So I is equal to 2. 2 less than or equal to 3. So again true. Q of 2 is equal to 30. So I is equal to 3. The third next condition, next increment. So 3 less than or equal to 3. Condition true. Q of 3 is equal to 40. Right? So I is equal to 4. So 4 less than or equal to 3 fails. So it comes out from the loop. It comes out from the loop and the display function will be stopped here. So these are the elements which are presented in the queue. So 10, 20, 30 and 40 which are here. So hope you understood this one, display function. Right? A very simple logic while implementing these queues using arrays. So here only drawback is we need to specify the size of the queue before starting the operations itself. So later we can't change the size of the queue. Right? So that's the only drawback in this queue implementing the implementation of queue using arrays. So here the NQ and DQ are the operations for insertion and deletion. NQ will be done at rear end, DQ will be done at front end. So stack can be implemented in two ways, that is by using arrays and using linked list. So in the previous session we have seen how to implement a stack using arrays. So there is only one disadvantage of that implementation, that is arrays will be having the static memory allocation. So the number of elements is restricted, so that if you want to insert more number of elements beyond that size, so that cannot be possible. So for that purpose, we are moving on to the second category, that is implementation of a stack using linked list. So here, before inserting an element, we will give a dynamic memory allocation. So we need not specify the size before implementing the stack, right? So let us see the implementation of a stack using linked list in this session. Implementation of stack using linked list. So first we need to write a structure for a node. So we know that a node in the linked list is represented in two compartments, that is, one is with the data value, and another one is the pointer value, which points to the address of the next node. So first we will create a structure for a node, and then we will start writing the operations. So struct node, right, some int data. So this is for data, inserting the data. Next, self-referential structure, struct node star next. Yes. So here we will create some new node, temporary node, top node. So top means the top of the stack, to represent the top element of the stack. Now we will see the push operation. So we know that the stack consists of two operations mainly. One is push and pop. Push means inserting an element into the stack. Pop means removing the element from the stack. Right. Coming to the push element. So we need to, if you want to insert an element, we have to allocate the dynamic memory. Right. I mean, we have to allocate the memory in a dynamic. So let it be new is equal to struct star node malloc function size of struct node. So automatically a memory is allocated for the new. Now we need to insert the data in new of data, and if we want to insert the address of the next node in new of next. So initially there is no element in the stack. So let it be first. See. So this is a stack, right? So initially top is equal to null. Initially top is equal to null. So similarly we will go with the linked list representation also, right? So first this is the first node to be inserted. Then just read the data, scanf %d ampersand element. So we are reading the data. So that data should be, I mean that element should be stored in this data. Now if top is equal to null, that means if it is a first node, what should be? So new of data is equal to element. See, right. Next, new of next is equal to. So this is the first element. So it should hold the address of next one, right? So address of next one is 0, right? Because this is the first one. See, in the linked list representation also we can use this one. This is the first one, right? So it is a stack. So whenever you are inserting another element, that element should be presented here, not here, right? To the left hand side, not to the right hand side. Here also, if you want to insert an element into the stack, that element should be at this position, not this position. Okay, so hope you understood this one. So here the element, for example, some 10 will be here, and this is null because no other element is there, I mean, right? So is equal to null. Now we have to change the top also. Initially top is null, so top is equal to new. So whenever you are inserting 10, automatically the top is changed to here. Right? So hope you understood. If you are inserting an element into the stack, that element should be inserted on the left hand side, not the right hand side, in the linked list representation. Coming to the stack representation, it should be on the above of the element. Right? So this field, this field is a next field. It should hold the address of the next element. So address of the next element means there is no element because this is the only first element. Right. Else part, when this else part will be executed, if the stack consists of any one element. Right? If the stack consists of any one element, then what should be done? So if you want to insert the second element, that means already the stack consists of one element, another element. So another element means, see, again calling the push operation, new node will be created, some memory will be allocated for the new, one element will be taken from the keyboard, that is 20, and if top is equal to null, top is not equal to null, so this part will not be get executed. Coming to the else part, here also, now we can write new of data is equal to element. Similarly, new of next is equal to, see, here also there is a 20. Which address should be placed here? It should hold the address of the next node. What is the next node? 10. So this address should be placed here. What is the address of this one? Top. Right? Here also, see, another node is created on the left hand side. So 20 is here. This holds the address of the next one. What is the next one? So initially, now top is here, right? So top, that means, top, some 1000, this is one. So this address should be placed here, right? So the link will be established from here. Hope you understood. So top. Now top should be changed. That means top should be positioned with the first element. So top is equal to new. Right? So hope you understood this one. So this is the simple logic for inserting an element into the stack which is implemented using linked list. So a slight difference between the implementation of a stack using arrays and linked list. Right? So the same representation, if you consider the stack representation, the last element. So see, if you are considering this one, if you insert a 20, it will be inserted here. If you insert 10 next, 10 will be here. That means 20 is the last element and 10 is the last but one element. And if you insert 30, 30 will be presented here. So 20 is the last element, last but one, and the top of the element, top of the stack is 30. So whatever the inserting, for first element we are inserting, that will be the last element in the stack. Right? So that's why we know that in the linked list, the last element, the address of the last element will be filled with null. So here, if you are applying the push operation for the first element, that address should be null because it is a last element in the linked list. Hope you understood. Again, if you perform this push operation, it consider 30 to be inserted. So top is equal to null. So after changing, the top is positioned here. Right? So this part will not get executed. This part will be executed only when we are inserting the first element into the stack. Now else part will be executed. New of data is equal to element. So 30 will be inserted here. 30 will be inserted here. New of next equal to top. New of next means this one. Top. That means 2000. So link will be established. Top is equal to new. Now top will be again changed. Top. Similarly here also. Consider this 30. Some 1000 is the position. Some 2000 is the position. Link. Sorry. Reverse. Okay. Right. Okay. So hope you understood this simple logic for push operation. We will go with the pop operation. Pop means removing the element which is at the top position. Right. So here both in the stack we have discussed in the previous session that both the insertion and the deletion will be done from one position, that is the top of the stack. Right. So whatever the element we are inserting recently, that will be removed first. So example also we have seen that organizing plates in an array. Right. Yes. So hope you understood the push operation. Right. Now pop operation. So before applying the pop operation, let us take 3 elements. So and then we will delete it. Right. This is the first element to be inserted. That is the last one. So 1000. So here it's 1000. Here it is a 2000. It's a 10, 20, 30, and this is the top. So this is the 3000 top position. Right. Now pop means we have to remove the element from the top of the stack. So whatever the element we are assigning at the top, that element should be removed first. So that's why here pop. First we have to check whether the stack is empty or not. So if it is if the stack is empty and still if you are trying to remove the element from the stack, that implies it is a underflow, right? Underflow condition, which we have discussed in the stack implementation, stack introduction, right? So first we need to check for the underflow condition. So if top is equal to null. Top is equal to null means there is no element in the stack. So that's why simply we can write here printf stack is empty. Nothing but underflow, right? So else if top is not equal to null, then which one should be removed? This one should be removed. So we need to change the top to the next element. So that's why we are supposed to assign that into a temporary variable. So temp is equal to top. Temp is equal to top. Now just move the top to the next position. So top is equal to top of next. So top of next means 2000, right? 2000 will be assigned to top. That means this top will be moved to here. This top will be moved to here. Next, simply we can write. So this is a temp, okay? So in the first line we are just assigning temp to top, right? So temp of next is equal to null. So this we can place it as a null. So the link will be disconnected. Okay. And this element can be deleted or else. So just we can write which element is deleted. So here we can write element is equal to top of data, right? So then we can write display printf %d is deleted. What is the %d? Top of data, right? After that, See, after that this statement, top is equal to top of next, temp of next equal to null, or simply we can use the free function. So here we are not deleting the memory, just we are disconnecting the link from one node with another node, or simply we can write a free of temp. So we know that there are different functions in dynamic memory allocation, right? So one is malloc, calloc and realloc and free function. Free function is used to remove the memory, clear the memory, which is allocated by using the malloc or calloc functions. So that's why we can simply free of temp. So temp is this one. Free of temp means whatever the memory allocated for this node, that will be removed, right? So automatically the element is deleted. Now the top of the stack is 20, right? This one. This is a simple logic for deleting an element from the stack. So deletion will be done from the top of the element. So before deletion, we need to check the underflow condition. So if top is equal to null, that means there is no element or there is no node existed in the stack. So then we can simply display the message that stack is empty. If it is not equal to null, that implies there are some elements in the stack. That may be one element or more than one element. So then we need to assign the top to temporary variable, and then we need to retrieve the element which is going to be deleted. So which is going to be deleted? Top. So top of data will be assigned to element. Element is deleted. Then we should move the top to the next element, because the first element should be removed. The top should be moved to the second element, because after deletion the second element will be the first element. So this statement moves the top to the second element. Now we have to remove the first element. So two ways. One is temp of next equal to null, placing the null at the next position. So the link will be disconnected, or we can use the free function which is available in dynamic memory allocations. So which is used to delete or free the memory which is allocated for this particular node. So that's why free of temp, right? So this is how we will implement this pop operation. Now we will see the display operation also. So display, how to display the elements of a stack implemented in linked list. See, let us take the three elements here. So this is the 3000 address. So this is the 2000 address. So this is the top, right? Now display function. So how to display all the elements? How to display all the elements of a stack which is implemented using linked list. Now here also we need to check the underflow condition. So if top is equal to null, that implies no element is inserted in the, no element is available in the stack. So then we can simply write printf stack is empty. Stack is empty. There is no element available in the linked list. Else we need to print. We need to print this one. So first initialize the top to temporary node, because we need to travel from first element to the last element without changing the top. So for I is equal to top, so simply we can write a while statement. Okay, so while, simply we can write here top not equal to null. So unless the top is equal to null, the loop will be inserted. The loop will be iterated. We can simply printf %d top of data, right? Or simply we can use here temp, because we need not change the top. So temp, right? So instead of using top, we can write the temp. So we have to move the temp to next element. Temp is equal to temp of next. That's it. So automatically in the first iteration it will check whether top is equal to null, that is false, else condition. Temp is equal to top, so temp will be here. So temp is equal to 3000 position, while temp not equal to null, true. Printf temp of data. Temp of data means 30 will be printed here, right? temp is equal to temp of next. So temp is equal to temp of next and 2000. That means 2000. So 2000 here. So temp rod equal to null. Yes, true. Temp of data will be printed. What is the temp of data? Temp is equal to 2000. Data available in 2000 is 20. So 20 will be printed here. And again temp is equal to temp of next. So temp is equal to temp of next. That means 1000. So again the loop will be started. Temp not equal to null. True. So this is true. This is true. This is true. And percentage temp of data. So what is the available data value at the temp 1000? That is 10. 10 will be printed here. Temp is equal to temp of next. What is the temp value now? Temp is equal to temp of next. That's null. Right? Next, coming to the value, temp not equal to null. Temp not equal to null. False. Automatically loop will be exited. Right? So the control will come out from the loop. Okay. So this is a simple operation of display function. So displaying the elements of a stack which is implemented by using the linked list. Right? So in this session we have seen the three operations: push, pop and display. So here we are implementing the stack operations using linked list. So in the insertion, the first inserted element will be the last element in the stack. Right? So likewise we need to implement the push and pop operations and the display operation. Right? So hope you understood all these operations. Right? Now we will go with the queues using linked list. Right. So we know that linked list means nodes. So elements will be represented as a nodes, and each node will be having two fields. One is for storing the value, another one is for storing the address of the next node. Right? So first we need to specify the structure of a node, and then we will go with the implementation. And coming to the queue, we have seen the two operations on queues, that is enqueue and dequeue. So here the enqueue means inserting the element and dequeue means deleting the element from the queue. And the third operation, that is displaying the elements of a queue. Right? So coming to this enqueue and dequeue, here there will be two ends. One is a front end and another one is a rear end. So here the queue will follow the first in first out mechanism. So first in first out. So whatever the element which is inserted first into the queue, that element should be removed first. So for this purpose, all the insertions will be performed at the rear end and all the deletions will be performed at the front end. So the best example for this queue is standing on a line in the reservation counter. Right? So all these things we have seen in the queues implementation using arrays. Right? Now we will go with the implementation. First we will write the structure of a node, and then we will go with the enqueue and dequeue using linked list. Right? So struct node int data. So two fields, that is int data, self-referential structure. Struct node star next star new star rear star front temp. So all these are the different nodes. Right. So new will be having data and next, rear will be having data and next, front will be having data and next, temp will be having data and next. So these are all the structures, right? Structure variables. Now we will go with the enqueue operations, that is enqueue and dequeue. Right? See. So queue representation is in this way. Queue representation is in this way. So this is the front, this is the rear. Okay. So initially initially front and rear will be null. Front is equal to rear is equal to null. So after inserting an element, we require to increment the rear, and then we have to increment, we have to insert an element. Okay, so front will always points to the starting position of the queue, starting element of the queue. Rear will point the end position, that means the last element of the queue. Now we'll go with the NQ operation. Right? We'll go with the NQ operation. Right. NQ. NQ means inserting an element into the queue. So first, in order to insert an element, first we need to allocate the memory for that node, and then we will read the element and then we will insert. So first, the new is equal to malloc right. So this statement will allocate a memory to the new. Then read an element. Scanf %d some ampersand element. Now we have to insert this element into the data value, data field, and in the next field we have to store the address of the next element. So as this is the first element, if this is the first element in the queue, then the next field will not having the address of the next node. That's why it should be filled with null. So initial, if it is an initial element, right? So before that, we'll check for whether this is an initial element or not. So initially, this rear is equal to null, front is equal to null. Initially, rear is equal to null, front is equal to null. So if it is a first element in the queue, then front or rear. So anything we can write, say rear is equal to null. So before seeing the condition, we can simply write new of data is equal to element new of next is equal to null. Then check for the condition whether this is the first element in the queue or not. So if it is a first element, so how can we know that it is a first element? So simply rear is equal to null. If rear is equal to null, that implies it is a first element, because rear should be updated for every insertion. Then simply we can update the rear, front. So front is equal to new, rear is equal to new. Else, so if you are inserting an element, first memory will be allocated. So a node will be created here. So scanf element, if you read 10, new of data is equal to 10. So 10 will be updated here. New of next equal to null, and null will be updated here. And then if rear and front is equal to null, yes, here also the same thing. Front is equal to new, rear is equal to new. So front and rear, right? If you are implementing again this NQ operation, the second element should be inserted, and same thing, new. So another node is created here, and if the second element is 20, right, and new of data is equal to element 20, new of next equal to null, it is placed here. If rear is equal to null, no. If front and rear is having the address of 10, so this condition false. Else part will be executed. What should be done here? Now the link should be established between first node and second node. So how? The rear of next. So in this field it should store the address of 20. So rear of next. Rear of next is equal to new. So obviously, see, this is a 2000, let it be. This is a 1000, let it be. So this null will be replaced with 2000. So a link will be established. Now update the rear, because every insertion will be done at the rear end. Rear is equal to new. So this rear will be updated to here. Hope you understood. Again, if you are inserting the third element 30, so there will be one more node is created. So new of data 30 will be here, and new of next null will be here. So if rear is equal to null, false, front, so else part will be executed. Rear of next, so rear of next, so this field will be filled with new. So let it be 3000. So 3000 will be placed here. So automatically a connection is established here, and rear is equal to new. So rear is equal to new. So rear will be pointing here. Right? So hope you understood. Only for the first element we have to change the front and rear. For after that, for every insertion or every NQ operation, we need to update the rear, because the insertions will be done at the rear end. So this is all about this NQ operation. So hope you understood this one. Now we will move on to the next operation, that is DQ. That means deletion. So deletion will be done at the front end. Right. DQ, that is deletion will be done at the front end. See, let us take 3 nodes in a queue, some 10, 20, 30, 2000, 3000, null. So this is the front, this is the rear. So 1000 here address, 2000 here address, 3000 here address. Right. Now let us implement the DQ. That means we have to delete an element from the front end, that is 10 should be deleted. Now if you want to delete the 10, first we have to check whether the queue is empty or not. When the queue will be empty, if the front is equal to null, because we are deleting the element from the front. So if front is equal to null, if the front is equal to null, that implies the queue is empty. So we can simply write printf queue is empty. Right. Else if queue is not empty, now we need to remove this front. Now for this, simply assign this front to some temporary value. Now move that front to the next element, because the first element should be deleted. So front is equal to front of next. So after implementing this one, front of next, that means front is pointing to this one. Right. Now we need to change this one, delete this one. So we can place a null in place of the address field, so that then the connection will be disconnected, or simply we can use the free function. So in the dynamic memory allocation, we had another function called a free function, which will clear all the memory which is allocated by using the malloc or kellogg functions, right? So we can use anything. Now here temp is equal to friend, here temp is pointing the first element. Temp is equal to friend, temp is pointing to the first element. Now we can remove this one. So either we can use temp of next equal to null. Automatically this will be removed and null will be placed here, so the connection will be disconnected. The connection will be disconnected. Or simply we can use free of temp. Free of temp. That means all the memory which is allocated for this node, that will be removed. Cleared. The memory will be cleared. Right? So this is the simple logic for deleting an element. See, after deleting this one, the front is 20, rear is 30. So if you are again applying this DQ, this 20 also will be deleted, front will be moving here. Okay, so hope you understood this one. Right? So this is called the DQ, that means deleting an element. So insertions will be done at the rear end and deletions will be done at the front end. Now, we will move on to the third one, that is display. How to display the elements of a queue. Right. Now we will go with the display function. So display. So here we need to start from the front and we have to move to the till the rear. So simply we can use here, first let us check whether the queue is empty or not. So we know that if we want to check the queue is empty or not, check the front is equal to null. So if this condition satisfies, simply we can display queue is empty, else starting from the front display all the elements. So until while front not equal to So here, in order to travel from the first node to last node, just use the temporary. Just use the temporary while temp not equal to null. Temp not equal to null. Right? So we should not change the front value. So that's why we are just assigning the front to the temporary variable, and then we are traveling through temporary variable. So here see, printf %d temp of data. So every value will be printed here, and after printing the value we need to update that one. So temp is equal to temp of next. That's it. Simple thing. So if you trace this one, see, temp is equal to front. So temp is also assigning to the same node. Front is equal to null. So initially the front is equal to 1000. So this is false. Automatically here it will be gone. So temp not equal to null. So here again temp is equal to 1000 because temp is equal to front. So temp not equal to null. Condition true. Right? So here I will write here. Okay. Temp not equal to null. Condition is true. Temp of data. Temp of data means 10. So 10 will be printed here. Temp is equal to temp of next. Now temp is equal to temp of next means 2000. Automatically this temp will be pointing to 2000. Again, temp not equal to null. Temp not equal to null. True. Condition is true. So printf temp of data 20 will be printed here, right? Then temp is equal to temp of next. So temp is equal to temp of next. That means 3000. Again, the temp will be pointing at the 3000. Now, again simple. Temp not equal to null. Condition is true because temp is equal to 3000 here. So temp of data 30 will be printed. Temp is equal to temp of next. So here temp is equal to temp of next, that is null. Right. Again loop. Temp not equal to null. Temp not equal to null. Here the condition fails. Here the condition fails. So automatically it comes out from the loop and it exits the display function. So this is how we can display the elements of a queue which is used implementing this linked list. Right. So hope you understood this display operation also. A simple things. So if you understood the linked list concept, and all the remaining concepts will be very simple. So my suggestion is, before going to the stack and queues, so just go through the linked list and then you can implement this stack and queues in a simple way. In this session we'll go with the applications of a stack. So where these stacks will be used. So here mainly the stack is used in evaluation of a postfix expression. Similarly, it is used in conversion of infix expression to postfix expression, as well as infix expression to prefix expression, and also the balancing the parentheses. So all these are the different applications of a stack. So before going to the actual applications, let us see what is meant by the infix expression, prefix expression, and the postfix expression. Right. Applications of a stack. Right. So first one is infix expression. Infix expression. So here this plus, minus, into, divided by, all we call them as operators. Right. So what are the variables we are using? Let it be A, B, C. All these are called operands. Operators and operands. Right. So if you consider any expression that will be in the form of A plus B, right? A plus B is an expression. So that means there will be an operands and operators in the expression. So if the operator is in between the operands, operator is in between the operands, so operand, operator, operand. So in between the operands there will be operator, then this is called infix expression. Example, the same example, we can say that A plus B, right? Second, what is meant by postfix expression? Postfix expression. Post, we have seen the terms post increment and pre increment. Similarly, post expression, postfix expression means first there will be the operands and after that we have to write the operators. See, operand 1, operand 2, and then we have to write the operator. So that means, example, it will be in the form A, B, plus AB plus, right? So this implies A plus B. Okay, this implies the A plus B, and this is how it is evaluated in our system. Right. This is called a postfix expression. Postfix. Similarly, the third one is prefix expression. Prefix expression. So prefix, pre-increment and pre-decrement we have seen. So prefix means first there must be an operator, then we have to write the operands. Operator, operand 1, operand 2. Example for this one is plus AB, plus AB. This is called a prefix expression. So three ways we can represent an expression: infix expression, postfix expression, and similarly prefix expression. Right. So infix expression is the expression which we know that, right? So we have to place the operators in between the operands. That we call it as a infix expression. And if you are writing the operands first and then the operators, then it is called as a postfix expression. And if you are writing the operators first and then the operands, then it is called the prefix expression. So here our stack has these are the applications. So one is the conversion of infix to postfix, infix to prefix, and the evaluation of postfix expression. So how this expression is evaluated in the system, and similarly the balancing the parentheses, okay, balancing the symbols. So all these are the applications. So let us write the applications first and then we'll move with the one by one. So first application, conversion of infix to postfix expression. Second one, conversion of infix to prefix expression. The third one, evaluation of postfix expression. And the last one is balancing of symbols. So all these are the different applications of a stack. That means where the stack is used. So in the conversion of infix to postfix, we will use the stack, and similarly the conversion of infix to prefix, we will use the stacks, and that means with the help of a stack only we will complete the conversion. Similarly, the evaluation of postfix expression, and then the balancing of symbols, right? So let us see one by one. So in this session we will go with the conversion of infix to postfix expression. Conversion of infix to postfix expression. Right. So for this conversion we are supposed to follow some steps, right? So we'll take the stack and we will read the expression, and by reading the expression we will use, with the help of a stack, we will convert the infix expression to postfix expression, right? See, So first let us write the steps required for this conversion. So, steps required for conversion. First one, see. So first we have to read the infix expression, that's an input, right? And after completion of this conversion, the final output will be the postfix expression. So reading the infix expression, read each and every symbol, read each and every character, right? So let us call it as a string. Let us call it as a string and read each and every character. Okay. So if the character, for example, see, some A plus B star C, A plus B star C. So here consider this as a string. This is an infix expression because we are using the operators in between the operands. So consider this as a string and read each and every character. So if the character is left parenthesis, so obviously our expression may also contain the parenthesis, right? So if our character is a left parenthesis, simply push to the stack. Push to the stack. Right? Simply, the first step is, if it is a left parenthesis, simply push the left parenthesis into the stack. Next, if the character is operand, so our expression will be having both the operands and this operators, right? So if the second case, if the character is an operand, then simply add to the postfix expression. Add it to the postfix expression. Right. The third one, if it is not a left parenthesis and if it is not an operand, if it is an operator, if the character is an operator, right, what we have to do? Check whether stack is empty. Right. Here two conditions will be there. So one, if stack is empty, one process should be done, and if stack is not empty, another process should be done. Right. So here, first case, if the character is left parenthesis, push the left parenthesis to the stack, and if the character is an operand, add it to the postfix expression, and if the character is an operator, check whether the stack is empty, and then if stack is empty, we have to do the particular operation, and if stack is not empty, we have to do the particular operation. Right. So now we have to check whether the stack is empty or not. Then see, two conditions, stack is empty and stack is not empty. If the stack is empty, then push operator into stack. Push the operator into stack. Second case, in the same condition, in the same case, we are having two conditions. Then, if stack is not empty, then check the priorities of the operator. Check the priority of the operator. So, here also again we are having the two conditions. First one, if the priority of operator is greater than, the operator present at top of stack, right? If the priority of an operator is greater than the operator present at top of stack, then push the operator into stack. So, once writing all these steps, we will see the example so that your doubts will be clarified, right? See, second point, the reverse. If the priority of an operator is less than or equal to the operator present at top of the stack, right? So, if the priority of an operator is less than or equal to operator present at top of the stack, now what we have to do? Then pop the operator from stack, and add to postfix expression. So we have to remove the top of the stack, the operator which is available at the top of the stack, and we have to move that to the postfix expression, and then we have to check with the further operators in the stack itself, right? So we can't place the operator which is having the priority with the less priority than the top of the stack. See, add to the postfix expression. Go to step 1. So again, after completion of this one, go to step 1. Okay, again we have to check the priority of the operator which is greater than the operator present at the top of the stack after removing the first operator, right? So first operator, now the top of the stack will be moved, so we have to check the operator with again the top of the stack, right? So this process should be repeatedly done. Next, right? Okay, then now we have seen the left parenthesis operand operator. There is one more thing, that is a right parenthesis. So if the character right parenthesis, then pop all the operators from the stack until it reaches left parenthesis. And add to postfix expression. Right. So if the character is a right parenthesis, then we have to pop all the operators from the stack until it reaches the left parenthesis. So already if it is a left parenthesis, we have placed it in the stack, right? We have moved it to the stack. So we have to remove all the operators which are available in the stack until it reaches the left parenthesis and add them to the postfix expression. Add them to the postfix expression. Right. Next, last one, after reading all characters, if stack is not empty, then pop and add to postfix expression. Okay, then pop and add to postfix expression. Right. So after reading all the characters from the infix expression, if you read A plus B star C, still the stack is not empty, then remove all the elements of a stack and add to the postfix expression. Right. So these are the steps to be followed while creating, while converting the infix to postfix expression. See, so if the character is left parenthesis, push the left parenthesis to the stack, and if the character is operand, add the operand to the postfix expression, and if the character is an operator, then we have to check two conditions, whether the stack is empty or not. If the stack is empty, push the operator into stack. If the stack is not empty, check the priority of the operator. So we need to see the operator precedence, right? So we have to check for the priority of the operator. Now if the priority of operator is greater than operator present at the top of the stack, simply we can push the operator into stack. If the priority of operator is less than or equal to operator present at the top of the stack, then pop the operator from the stack and add to the postfix expression and go to step 1. That means again we have to repeatedly check whether the priority of the operator which is greater than or equal to the top of the stack, operator which is available at the top of the stack. Right. If the character is a right parenthesis, then remove all the elements from the stack, that means operators. So right. See here, one thing to be remember that in the stack we will just push the operators, not the operands. So stack consists of only the operators. So if the character is a right parenthesis, then remove all the operators from the stack until it reaches the left parenthesis, then add them into the postfix expression. And after completion of reading all the characters from the infix expression, if still the stack is not empty, then remove all the operators which are available in the stack and then simply add to the postfix expression. Right? See, simply we can let us solve it. Right? So let us take stack, and this is a postfix expression. Stack postfix expression. See, first character is A. A means it's an character, it's an operand. So if the character is operand, add to postfix expression. So this is a postfix. See, I will show you this postfix, and this is stack. So if the character is operand, simply add to the postfix expression. So we have to add here itself. Next, this one is completed. Next character is plus. So if the character is operator, check whether stack is empty. Yes, this is an operator. We are checking for the stack. So stack is empty here. So if the stack is empty, push operator into stack. So push the plus to stack. So hope you understood this one, right? So next, this is also completed. Next, B. If the character is operand, add to postfix. So simply write B here, right? Next, star. Star is again operator. So if the character is operator, then check whether the stack is empty. So stack is not empty. So it will go with the second case. If the stack is not empty, check the priority of the operator. So star is having the so if the priority of operator is greater than operator present at the top of stack, so star is having highest priority than top of the stack operator which is available at top of the stack. So star is greater than plus. So this condition will be true. Then top of the stack present, then push the operator into stack. So just simply push star into stack, right? So this is also completed. Next, again, read the character. If the character is an operand, add the postfix expression. So C is added here, right? So the reading of all the characters from the infix expression is completed, right? The reading of characters from infix expression is completed. There is no other character available in infix expression. So that's why, see, last point. After reading all characters, if stack is not empty, here stack is not empty, then pop and add to postfix expression. So pop everything. So pop operation means we can delete the element from the top of the stack. So delete the top of the stack star and place it into the postfix expression. So then plus pop it again, place it in the postfix expression. So this is the postfix expression for the given infix expression. So in the previous session we have seen the algorithm for converting the infix expression to postfix expression. So also we have seen what is meant by infix, prefix and postfix, right? So in this session we will solve some examples so that your doubts will be clarified. So at a glance, let us see the algorithm. So there will be an infix expression, so we have to read it as a string, and then we have to maintain one stack and we have to maintain one postfix expression, right? So we have to read each and every character from the infix expression. So if it is a left parenthesis, then simply we can place that left parenthesis into the stack. If the reading character is an operand, simply place that operand into the postfix expression. If the reading character is an operator, we have to place that operator into the stack. So here one thing to be remembered, that is our stack consists of only the operators, right? So if the reading character is an operator, first we have to check whether the stack is empty or not. So if the stack is empty, simply we can push that operator into the stack. If stack is not empty, we have to check the priority of the operators which is available in the stack and which is reading from the infix expression, right? Here, if the reading character, that means a reading operator priority is greater than the top of the stack priority, I mean the operator available at the top of the stack, then simply we can push the operator into the stack. And the second case, if the priority of the operator which we are reading from the infix is less than the operator available at the top of the stack, simply we have to pop the operator from the stack and push it to the postfix expression. And then we have to again check these priorities with the second second top of the stack element, right? So after this process, if the character is a right parenthesis, then simply we can remove or pop all the elements, all the operators available in the stack until you reach just the left parenthesis and place them into the postfix expression. Right? So if the complete reading of all the characters from the infix expression is completed and still the stack is not empty, then simply pop all the operators from the stack and place it in the postfix expression. Right? So this we have seen in previous session. So I will just post the link in the description section so that you can once go through that and then you can listen it. So here in today's session we will solve a few examples. So how to convert this infix to postfix based upon our algorithm. Right. Infix to postfix expression. Example. So let us take this example. So how to convert this infix? So this is the infix, right? So this is the infix expression. Now we have to convert this infix expression to postfix expression, right? See. So this is the character which we are reading. So this is the stack for placing the operators, and this is the postfix expression. Postfix expression, right? First, A is a character, right? So we know that if it is a operand, simply place it in the postfix. So empty stack, and A is placed here. Next, minus. Minus is the operator. So if it is an operator, first we have to check for the empty stack. So it is empty, so directly we can push the minus. So see, minus, right? Then simply postfix expression consists of only A. And next, parenthesis, left parenthesis. So simply we can push into the stack. Simply we can push into the stack. So minus left parenthesis, right? The postfix expression is here. Next, B. So B is an operand. So simply we can add to the postfix. So B, and here the stack is same. There is no difference in stack, and here it will be A, B. Star. So it is an operator. So first we have to check whether star, the priority of star is highest than the top of the stack operator. So here the top of the stack, if the top of the stack is with the parenthesis, so left parenthesis, simply we can push the operator into the stack. So we need not check for the priority, simply we can push the operator. So after pushing the operator, see, minus, parenthesis, and star, 3. So here there is no change. A, B. C. So C is an operand. So we have to push into the postfix. So there is no change in the stack. Minus, left parenthesis, and star, A, B, C, right? Then again minus. So here stack is not empty, so we have to check the priority. So priority of the reading operator, that is minus, is less than the top of the stack operator is star, right? Top of the stack operator is star. So the priority of minus is less than priority of star. So we cannot push this minus onto the stack because top of the element is having the highest priority. So remove the element from the stack and place it on the postfix expression. So, and then follow the same procedure. So now see, minus parenthesis, and we have removed the star, so A, B, C star, and we have to check for the same condition for the next top. So now top is left parenthesis. So left parenthesis, we know that condition. If it is a left parenthesis, simply we can push the operator onto the top of the stack. So minus can be pushed here. Hope you understood, right? So the star is having the highest priority. We can't move this minus, that means this minus operator onto the star, so we have to remove the star and we have to place it on the postfix. Then we have to apply the same procedure for the next operator. So here the next operator is left parenthesis. So there is no constraint for the left parenthesis, so we can simply push the elements onto the stack if the top of the stack is left parenthesis. So minus, right. Next D. There is no change in stack, so A, B, C star D. Okay. See, after D there is a closed parenthesis. Okay, there is a closed parenthesis. So now see, closed parenthesis means what we have to do. So we have to pop all the elements of the stack until it reaches the left parenthesis and place it on the postfix expression. Right, now see. So let us take the stack here. Let us take that stack here. So minus, and so we have to pop this one. We have to pop the minus here, and next left parenthesis is here. So we need not write the left parenthesis and right parenthesis on the postfix expression. So we have to remove all the elements of the stack until it reaches the left parenthesis. Only one element is there, so we have done. Right. Next, divided by. So divided by is greater than, the priority of divided by is greater than the priority of minus. So we can simply push this divided by onto the stack. Minus and divided by. So A, B, C star D minus. Then E. So E is a E is an operand, so simply we can write it in the here. So there is no change in stack, minus and divided by. So A, B, C star D minus E. Now we have completed reading all the characters of INFIX expression, right? So even though the stack is not empty, so we can pop everything. So the postfix expression A, B, C star D minus E, popping, so top of the element. Next, this one. So this one is the postfix expression for this. Right? This one is the postfix expression for this given infix expression. So hope you understood, right? We have to read every character, and based upon the character and based upon the priority, we have to place that operator in the stack, and we have to pop the operator in the stack, and we have to place it in the postfix expression. So hope you understood all these things, right? Right. So let us solve one more example. So just based upon the algorithm, follow the instructions. Only one constraint, that if the stack consists of left parenthesis, then simply we can push the operator onto the left parenthesis. There is no constraints here. Okay. Now, so let us take one more example and then we will solve it. Right. A divided by B minus C plus D into E minus A star C. Okay, right? So a little bit large. So I will not write line by line. Just we will go with a simple process. Okay, so try to understand. So let us consider a stack. Okay, so let us consider a stack. Let us consider the postfix. Right. So this is the stack. This is the postfix. Right. So we are reading the characters one by one. So first one is left parenthesis. So simply we can push it in the stack. Right. Then A. This is an operand. Okay, this is an operand. So simply we can push in the postfix. So A is here. Divided by. So divided by is a operator. We have to check the priority. Here it is a left parenthesis, so there is no need of checking the priorities. So simply we can use divided by here. Okay. And the postfix expression is no change, that is A. Next, again open parenthesis. So open parenthesis is also having no constant, so we can simply push it into the stack. Okay. Then B, it is a operand, so simply we can place it in the postfix expression. Next, minus, so here the top of the stack is open parenthesis, left parenthesis, so we can simply push the minus here itself. There is no change in postfix. Next, operand C. So this is an operand, so we can simply place the C here in postfix expression. Next, operator plus. So here the stack is not empty, so we have to check with the top of the stack priority. The priority of plus and priority of minus both are equal. So that's why even in such case also we have to remove the element from the stack, and then it should be added in the postfix expression, and then we have to check the condition further, right? So here both are having the same priority, plus and minus are having the same priority. So we have to pop this minus and we have to place here, and then now top of the stack is left parenthesis. Again check the condition. So it is a left parenthesis, there is no condition, we can simply push it into the stack, right? So minus is placed in the postfix expression. Next, D, it is an operand, simply we can write here. Next, closed parenthesis. So if it is a closed parenthesis, we have to remove all the elements from the stack until it reaches the closed parenthesis, open parenthesis, right? Left parenthesis. So here until the left parenthesis there is only one element, so pop this element and place it here and remove the left parenthesis here. Okay, so we need not place the left and right parenthesis on the postfix expression, right? And again the right parenthesis, again do the same process. So here there is only one operator, that is division operator, until it reaches the right parenthesis, right? So left parenthesis. So remove this and place it here. Okay, now star. So simply place star in the stack because stack is empty here. Because stack is empty, simply we did not check for the priority, directly we can place the star in the stack. And again left parenthesis. So simply left parenthesis doesn't need to check the priority, so simply push onto the stack. Next, E is an operand, so directly we can write it in the postfix expression. Minus, so we have to place this minus into the stack. So before placing we have to check for the priority. So here the top of the stack is left parenthesis, so we need not check for the priority, simply we can place, we can push the minus operator into the stack, right? Then A is an operand. So simply we can write A in the postfix expression. And closure parenthesis. Again the same rule. So we have to pop all the elements from the stack until it reaches the left parenthesis and place them into the postfix expressions. Here there is only one operator, that is a minus operator. So you just remove the minus operator and place it here, right? And star, again star. So here also there is a star. So star and star both are having the same priority. Even though they are having the same priority, we have to pop the element from the stack and place it in the postfix expression. So remove the star and place it here, and it is a star. Now the stack is empty, so star is placed here itself. Okay. Now C is an operand, so C is placed here. So we have completed reading all the characters from the infix expression, but still stack is not empty. So we have to pop all the elements from the stack and place it in the postfix expression. So this one is the postfix expression. So this is the stack. Okay. So this is the postfix expression for the given infix expression. So hope you understood this one, right? So simply following the algorithm. So before solving these problems, so just go through the algorithm so that your doubts will be clarified, right? So shall we do one more example? Right. See, let us do one more example and we'll wind up. See, A divided by B minus C plus D star E minus A star C. See, so this is an infix expression. So now we have to convert it to the postfix expression. So let us take a stack here. So let us take a stack here, and let us take the postfix expression here. Right. So first read the character A. So this is the postfix. A. So A is an operand. So directly we can place it in the postfix expression. Next, divided by. Here stack is empty. So divided by will be placed in the stack. Next, third character is B. So B is an operand. So simply place it in the postfix. Next, operator minus. So here the stack is not empty. So we need to check the priority for the operators. So priority of minus is less than the priority of division. So that's why first we have to pop this operator from the stack and place it in the postfix expression, and again we have to check with the next top of the stack. But here the stop after removing the operator division, here the stack is empty. So that's why simply we can place the minus here itself. Next, C. So C is an operand, so we can place C here, and plus. So plus and minus, so both are having the same priority. Even though they both are having the same priority, we have to pop the element from the stack and place it in the postfix, and again repeat the process with this next operators. But after removing the minus, the stack is again empty. So simply we can push the plus operator into the stack. Next, D. So D is an operand. So simply we can write D here. Next, star. So star is a multiplication operator which is having the highest priority than the plus, right? So priority of multiplication operator is greater than the priority of addition operator. So simply we can push that particular operator into the stack. Alright. So if the priority is less, then we can't push the operator. So here the priority of star is higher than the priority of plus, so we can push the star into the stack. Right. Next, E. So E is an operand, so simply we can write it in the postfix expression. Next, minus. See, here such case. So minus and star. Top of the stack is star. Here reading character is minus. So the priority of minus is less than the priority of star. So we cannot push the minus on above to the star operator. So that's why here we have to pop this and place it in the postfix and check with this one. Minus plus. So now top of the stack is plus. Again we have to check with the top of the stack. Minus, plus. Again both are having the same priority. Even though they are having the same priority, remove the element from the stack and place it in the postfix expression, and again repeat the same process. So after removing the plus, the stack is empty. So we can simply move this minus into the here. Next, A is an operand. So simply we can write A here. And again star. So star is having the highest priority than minus. So simply we can push the star here. Okay. Next, C. C is an operand. So C can be written directly in the postfix expression. C. This is a C. Okay. Then we have completed reading all the characters from the infix expression. So still the stack is not empty. Now pop all the elements from the stack and place it in the postfix expression. First, pop star, place it in the postfix. Then pop minus, place it in the postfix. So this is the postfix expression for the given infix expression. So we have to read all the characters, and based upon the priority precedence, and we have to push the elements into the stack or not. Okay, so hope you understood this session's expression. So in today's session we will go with the second one, that is how to evaluate the postfix expression and how the stack is being used in the process of evaluating the postfix expression. Evaluation of postfix expression. Right. So here also there are some rules to be followed while evaluating this postfix expression. The first one is here only one stack is used. So only stack is used. And here we will store the operands in the stack, not the operators. So coming to this infix to postfix expression, we are pushing the operators but not the operands. Here the completely reverse. We will push the operands but not the operators. So this is called operand stack. This is called operand stack. That means it consists of only operands or symbols, right? So other than operators. Now let us see the first step. So here also we have to start reading each and every character of the postfix expression. So if the character is an operand, if the reading character is an operand, then push into stack. So first, if the character is an operand, then simply push into the stack. Next, if the character is an operator, if the character is an operator, pop top two operands from the stack and push the result back into stack. Right. So if the character is an operator, then pop top two operands from the stack and push the result back into the stack. So then last one. So after reading all the characters from the postfix, stack will be having only the value which is the result. So after successful reading all the characters from the postfix expression, then the stack will be having only one value, that will be the result of the postfix expression. Right? So this is a very simple, there is no comparisons of the precedence of operators. Simply read a character from the postfix expression. If it is a operand, simply operand or a number or anything else, right, simply other than operator, simply push that into the stack. And then if it is an operator, then remove the topmost two elements from the stack and perform this operation, and then push the result back into stack. See, oh, I skipped it here. Two operands from the stack, perform calculation, right? Right. So perform calculation and push the result into back into the stack. Right. So let us see the example so that your doubts will be clarified. Right. Now, so this is called an operand stack, because here in our stack we are storing only the operands, not the operators. Right. Example. Let us see that example. See, this is an example. This is a postfix expression. So now, how to calculate this postfix expression? See, first we can write here character stack. First 5. So simply it is an operand. So simply push into the stack. 5. Okay. Now 6. Again we have to push into the stack because it is an operand. 5, 6. Next 2. It is also an operand. Simply push into the stack. So now our stack is having 3 elements. Right. Next, star. What we have to do? We have to remove the 2 elements from the stack. What are the 2 elements in this from the stack? 2 and 6. 2 and 6. So see, observe carefully. First remove the 2 and next remove the 6 and write the 6 on left hand side of the 2, right? So 6. Apply the star. Apply the star. So how much? It is 12. So again push back into the stack. 5, 12. Okay, hope you understood. So first pop the element, first top element 2, and then pop the element and write the element left hand side to the top of the element, right? So 2 and left hand side 6. So 6 into 2, 12. 12 and 5. And plus, next one is plus. So again pop the element 12, pop the element 5, perform the operator plus is equal to 17. So push back into the stack. Right. Here we have completed reading all the characters of a postfix expression. So final output of this postfix expression is whatever the element which is available in the stack, that is 17, right? So this is the output for the given postfix expression, right? So hope you understood this one. A simple logic. So only one thing we have to remember while we are removing or popping the element from the stack. So write down the first element, second element first and first element next, right? Or simply pop the first element and pop the second element, place at the left side of the first element and apply the operations. Okay. So if you are doing the subtraction, the problem will be raised. So because 6 minus 2 will be something, 2 minus 6 will be here, right? This is 4 and this is minus 4. So in such cases, in the subtraction, you will get some mistake, right? So that's why we have to use this logic. Okay, right. So let us take one more example with the subtraction. So your doubts will be clarified once, and then we will wind up. Four, 3, 2, 5 star minus plus. Okay, so this is the postfix expression given. Now we have to find out the evaluation. After evaluation, what will be the result? So let us take here the character stack. Okay, now first 4. So consider a stack with 4. Consider a stack with 4. 3. Consider a stack with the 2 elements 4, 3. Next 2. Consider a stack with 4, 3, 2. 5. Consider a stack with 4 elements 4, 3, 2, 5. Okay, now star. So pop the elements. So what we have to pop? 5, 2, star is equal to 10, right? So first pop the element 5, pop the element 2 and place it on the left hand side. So 2 into 5, 10. So push back into the stack. So 10, 3, 4. Okay, hope you understood this one. So first 2 elements we have performed the multiplication operator on the first 2 elements. Okay, then minus. What we have to do? So we have to pop the elements from the stack. So 10, 3, place the 3 on the left hand side, right? 3 minus 10 and apply the minus operation. Is equal to minus 7. Is equal to minus 7. So push back into the stack. So minus 7 and a 4. Okay, so hope you understood this one. So first pop the element, pop the second element and based on the place on the left side, right? 3 minus 10 is equal to minus 7. Now the stack consists of 2 elements, minus 7 and 4, and there is one more operator called plus. So character and stack. So plus, so automatically again read the elements minus 7, 4. Okay, minus 7 and 4 addition operation, that is equal to minus 3. Right? Push that element into the stack. So minus 3, right? So there are no more characters to be read from the postfix expression, right? So here we have completed reading all the characters from the postfix expression. So whatever the element which is available in the stack will be the answer. That means what is this? Minus 3. So this evaluation after evaluating this my postfix expression, the value will be -3. Right? So hope you understood this one. So let us take one more example and we will wind up. A simple procedure for evaluating the postfix expression. So in such case we are also using the stack, so that's why we call it as an application of a stack. Right. So let us take an example, one more example. See, 5, 4, 6 plus star 4, 9, 3 divided by plus and star. See, this is an example. Let us take, okay, so 5, okay, 5, it is an operand, push it into here, so let us write here character stack. Okay, next 4, consider the stack 5 and 4. Next 6, 5, 4, 6 plus, so remove that, so that means 6 and 4, apply the operation plus, that is equal to 10, push back into the stack 10 and 5, 10 and 5. Okay, right. Next star, so again here also push, pop the element 10 and pop the element 5, apply the star is equal to 50, so the resultant will be 50. Okay, next I will write here character and the stack. Okay, next 4, so already in the stack there is an element called 50 and now 4. Next 9, 50, 4, 9, 3, 50, 4, 9, 3. Okay, now division. So for division, so first pop first element, next pop the second element and place it on the left hand side. So 9 divided by 3 is equal to 3. So and again push that into the stack, right? So 50, 4 and 3. 3 elements are available in the stack. Okay. Next plus. So pop the element, pop the second element, keep it on the left side. 4 plus 3 is equal to 7. So the resultant will be, and again push that resultant into the stack. So 7 and 50 are available in stack. Last one star. So pop the element 7, pop the element 50, apply the calculation, so it is 350 and push back into the stack. Right? Next, so this is an end character, right? This is the end character because that is the last character available in the postfix expression. So simply you can stop here and then remove the element from the stack, which is the result, right? So only one element is available in the stack, that will be the result for this postfix expression. So 350 is the answer for this postfix expression. Okay, so here we have seen two applications. One is the conversion of infix expression to postfix expression, and in today's session we have seen the evaluation of postfix expression. So how stack is involved in evaluation of postfix expression implemented. Now we'll go with the one more application, that is a balancing symbols. Balancing symbols. So here the main symbols we are supposed to use are parentheses, square brackets and curly braces. So these curly braces can be used to represent a block of statements, right? So block of statements. So block of statements, and these two can be used in expressions. In different expressions we can use these parentheses, right? So for everything there should be a balance of these things. So if we are opening the curly brace, automatically after some block of statements this curly braces should be closed. If you are opening the parenthesis, after some expression has been written, we have to close the parenthesis. If you open the square brace, after some expressions, I mean after writing the expression, we have to compulsory close the square, right? So this is the balanced. So all these three are the balanced symbols. Right? So one curly brace and one open curly brace, one closing curly brace, one open parenthesis, one closing parenthesis, one square braces and open square brace, and another one is closing square bracket. So this is the balanced symbols. So if it is a lot of code, then automatically we will use a multiple curly braces, and we should take care that every open curly brace should have one closed curly brace. Similarly, while writing the complex expression, so multiple number of operands and multiple number of operators, then we are supposed to write more number of parentheses and more number of square braces, right? So there also we have to take care that every parenthesis should be properly closed, every square brace should be properly closed, right? So all these evaluation, all this balancing will be done by the compiler, right? So in this purpose, how to get the correct balancing of these symbols? So one way is, the first way is counting open symbols and counting closed symbols. Open symbols and counting closed symbols. So these should be same, right? So how many open symbols are there? That should be matched with the number of closed symbols. Then we can say it as a balanced symbols. But here there is a drawback. See, so if it is an expression in the form a plus b, this one, so there are two square braces and similarly two closing braces and two parentheses and two closed parentheses. Now this is a balanced equation. If it is a plus b, if the expression is in this form, right? If the expression is in this form, is it right? See, here also we are having two open square braces and two closed square braces, two open parentheses and two closed parentheses. But here the expression is wrong, because first we are opening the square brace, next we are opening the parenthesis. So first we have to get the recently opened symbol. The closed symbol must be, the first recently opened symbol should be closed first, right? So the most recently opened symbol is parenthesis. So first this parenthesis should be closed, then only we have to move to the next one. But here the problem is the most recently opened symbol is parenthesis, but the first closed symbol is square braces. So where this is unbalanced, where this property fails, because here also we are having two open square braces, similarly two closed braces, two parentheses and two closed parentheses. So this property is satisfied because the counting and open symbols and counting the closed symbols both are equal, but the evaluation is unbalanced. The symbols are unbalanced, the expression is unbalanced, right? Because the most frequently used open symbol should be closed first, right? For this purpose, we will go with the stack implementation, right? So while calculating this one, while implementing this thing, or while implementing this code, we are going to use a stack as a mediator, right? With the help of a stack we can find this balanced symbols. Now let us write the algorithm and then we will go with the examples. See, first, similar to our postfix and infix expressions, first step is read character from expression. Right? First read every character from the expression. Second step, if character is open symbol, see, open symbol means it can be parenthesis, square brace or curly brace, whatever it may be, the three symbols, right? It can be. Then push the symbol into the stack, right? So if we get this symbol while reading the character from the expression, so we can avoid all the operands and operators, right? We can avoid all the operands and operators, just to concentrate on this parenthesis, right? So if the character is an open symbol, so either it may be parenthesis, square braces or curly braces, push the symbol into the stack. Next, if the character is closure symbol, either parenthesis, closure parenthesis, closure braces or closed curly brace, then we have to check one more condition. So that is, check if stack is empty. Check if stack is empty, right? Check for the stack is empty. So if true, that implies, so there is no open parenthesis or open square brace or open curly brace. That means there is no open symbol in the stack. That means without the open symbol in the stack, if you get this closure symbol, that implies the expression is unbalanced. If true, expression is unbalanced. If it is false, so that means if stack is not empty, we can simply write here. If stack is not empty, right, then pop the symbol from stack and compare with the character, compare with the symbol which is red. So we are reading the character from the expression, so we have to compare the symbol from the stack, and pop the symbol from the stack and compare with the symbol which is red. So if the symbol from the stack is parenthesis, so it should be, it should be compared with the symbol which is red, whether it is a parenthesis or not, right? So if matches or if comparison is successful, that implies balanced, right? Sorry. If doesn't matches, expression is unbalanced. Expression is unbalanced. Else, repeat the process. Else repeats the process. Simply we can repeat the process. That means reading the next character. So read the next character, and if it is an open parenthesis or open symbol, push into the stack. If it is a closed symbol, then check for the stack empty. If it is an empty stack, automatically it is an unbalanced expression. If it is not empty, then again pop the symbol from the stack. So pop operation means it will delete an element from the top of the stack, right? So it compares with the symbol which is red. If what doesn't matches, the expression is unbalanced. If it matches, else. That means if it matches, repeat the process. And finally, after reading all characters of expression, still stack is empty, that implies unbalanced. If stack is empty, that implies unbalanced, right? Sorry, our board is very small, so please adjust that. So last step is, after reading all the characters from the expression, still if the stack is empty, if stack is not empty, that implies it is an unbalanced expression, right? If stack is empty, that is called a balanced expression. So hope you understood this one. So reading the open symbol and reading the closed symbol, right? Open symbol just pushed into the stack. If it is a closed symbol, first we have to check for the stack empty. If it is a stack is empty, it implies it is an unbalanced expression. If it is not empty, pop the symbol from the stack and compare with the symbol which is read from the input. So if doesn't matches, expression is unbalanced. If it doesn't matches, because here this case, right? So A plus B. So in this case, so if it is an open parenthesis, if it is a closed parenthesis, so this will be compared with this one, which is not equal. So that's why it is unbalanced, right? Else repeat the process. If it matches, repeat the process until a completion of all the characters. So after reading all the characters of expression, still the stack is not empty, then it is automatically it's an unbalanced. Right? Hope you understood the process, right? Now we'll go with the example so that your doubts will be clarified. So if you are having any doubts still, so those doubts can be clarified with an example. We'll see the example. So let us take an example. So let us take to open A plus B, A minus B. Let us take this one. Okay, let us take this one. So just ignore the operands and operators. So just consider the symbols. First, this is the open symbol. So push it into the stack. Next, parenthesis. This is also open parenthesis. So again, simply push into the stack. Open into the stack, right? So next expression, leave it. And next one is closed parenthesis. So if it is a closed parenthesis, pop. We have to pop. So if you pop this one, what we will get? So closed parenthesis, so open parenthesis will be coming. Okay. So if you pop this one, after applying the pop, this one will be happen. So these two get compared. So this is the parenthesis, this is also a parenthesis. So matches, right? Repeat the process. Hope you understood. This is a parenthesis and this is a parenthesis. So we should just repeat the process. So again move on. Again open parenthesis is here. So if it is an open parenthesis, simply push into the stack. So this is an open square bracket and open parenthesis. And coming to the next closed parenthesis, again pop. Apply the pop operation. So we will get the closed open parenthesis from the stack, right? Closed parenthesis from the stack, and compare these two. So this is a parenthesis, this is also a parenthesis. So if it is a square brace, then it doesn't matches, right? So this is a parenthesis, both are the parentheses. So here also it matches. So repeat the process. Again repeat the process. Next, closed square brace. Again closed square brace means, see, we have to apply the pop operation. So if you apply the pop operation, we will get the open square brace, right? So we can get the open square brace. So matches, right? This is a closed square brace and here open square brace. So it also matches, right? Then repeat the process. So here there is no other character in the string, given string. So check for the stack. So here stack is empty. Stack is empty. So we can say that it is a balanced expression. Hope you understood this one, right? So if it is an open symbol, just push it into stack. This is also open, push into stack. If it is a closed parenthesis, closed symbol. So it is a closed symbol. First we have to check for the stack empty. So here stack is not empty. So here stack is not empty. So we have to pop the top element. So top element is open parenthesis. So now compare the open parenthesis with the read character. That is also closed parenthesis. Both are the parenthesis. So matches successfully. So again repeat the process. So again open parenthesis. So if it is an open symbol, simply push into the stack. Next closed parenthesis. Again check for the stack empty. It is not empty because it is having two fields, two elements. So pop the element. So if you pop the element from the stack, the topmost element is open parenthesis. So now check with these two, open parenthesis and a closed parenthesis. Both are the parentheses, not the square brace and everything. So here also it matches. Okay, it also matches. So automatically we have to repeat the process. So now the stack will be having only the open square brace. The last one is closed square brace. Now check for the stack empty. Now the stack is not empty because it is having the one element. So apply the pop. So topmost element, that is a open square brace, it is removed from the stack and compared with the reading character. So if both are equal, here both are equal because both are the square braces, right? So here also it matches. So automatically we have to repeat the process. So here there is no other character from the string. Here there is no other character from the string. So we have to stop and we have to check for the stack whether it is empty or not. Here the stack is empty. So if it is a stack is empty, we can say it is a balanced expression. Now let us move with the unbalanced expression. So your one more doubt will be clarified, right? If you are having still doubts, so your doubts will be clarified. See, I will go with, right? So this is the expression. This is the expression. Or simply we can consider the previous example. See, A plus B. This is a parenthesis, okay? Don't confuse. This is the parenthesis, right? Okay. Now let us consider the open square brace. So open symbol, just push into the stack. Just push into the stack. Next, open parenthesis. So no need to check the condition, simply we can push into the stack. Next, remove the operands and operators, ignore it. So coming with the symbols, see, close square brace, close square brace. So if it is a closed symbol, we have to check whether the stack is empty or not. Stack is not empty, right? Stack is not empty. Now we have to pop. Okay, pop. So if you apply this pop operation, we will get the parenthesis. We will get the parenthesis. Okay. We will get the parenthesis. Now square brace is equal to parenthesis. So this fails because both are not equal. Both are not equal, right? So this is a square brace and this is the parenthesis. So it fails. It fails. So if it fails, automatically we can say it as unbalanced expression. Unbalanced expression. Right? So hope you understood this one. The example one we have seen with the balanced expression, another one we have seen the example for unbalanced expression. Right? Go, don't get confused. It's a very simple thing. Right. Now let me explain the three applications once again. So whenever we are using an expression, see, a plus b, a minus b, right? So the first step, if you want to execute this expression, first the conversion will be done, conversion of infix to postfix expression will be done. Here we will use operator stack, right? Here we will use the operator stack. So once it is done, right, once it is done, we will get the postfix expression. Now the evaluation of postfix expression will be done. So now evaluating postfix expression, right? Evaluating postfix expression. So in this evaluating postfix expression, we will use operand stack, right? Operand stack. Okay. So in this we are using operand stack. So we are just removing the operators and we are just only taking the operands. And the third one, balancing, checking the parentheses, the symbols, balancing symbols, balancing symbols. So this must be done, right? So in this symbol stack will be used. That means a stack consists of symbols. Okay. So if we want to execute any expression in the compiler, the compiler will work with the three stacks. One is for operator stack, another one is the operand stack, another one is a symbol stack. Right? So if it is a balanced symbols, then only it will execute all these things. If it is an unbalanced symbols, then the expression will be wrong. Right? So hope you understood this one, where we are implementing the stack. So this is the applications of a stack where we are using, right? So we are simply writing the expression and we are getting the result, but in the back end all this process will be done. So in this session I would like to explain various searching mechanisms. That means there are two major searching mechanisms, that is a linear search and binary search. So here the search procedure is, we have to consider some number of elements and we have to search a particular element in that group of elements. So this process can be done in two ways. One is linear search and another one is binary search. So for this concept we have to use arrays. So for reading the elements, that means we are for storing the group of elements, we can use a single dimensional array, and in that single dimensional array we have to search for the particular key element. Searching procedure. So here there is a linear search, another one is binary search. Linear search and a binary search. So what are the inputs we need to implement this linear and binary search? So for both, the inputs are group of elements and the key element to be searched. The key element to be searched. So we have to search for this key in the group of elements, and we have to print whether the key is found or not found. So let us start with the linear search. So in this linear search, we have to consider a key element, and we will keep on searching each and every element until we found the key. So there is no logic here. So we have to compare this key element with each and every element in an array. For example, let us take array of 5 elements, that is 10, 20, 30, 40, 50, and the search key element is 30. Key element is 30. So write down the main function. Declare an array with some 5 elements. So I am declaring in a compile time, that means direct initialization. Now declare one search key, so that we have to find this key for in the group of elements. So we have to read that key. So write down printf, enter search key, scanf. So for reading the key value, %d ampersand key. Now after reading the key, we have to compare this key value with each and every element in an array. So for that purpose, I have to use a loop. So I have to repeat the process from 0th element to last element, that means 4. So for in every iteration, I have to compare this key value with a of I. So that means every element. If the key is found, let us take one more variable, flag, initially 0. So set this flag to 1. Set this flag to 1 if the key is found, and we need not search for remaining elements. Right? So if you found the key value in the second position, we need not execute this program for remaining 2 cases. That means we need not search this key for the 3rd element and 4th element. So we have to stop the procedure where we have to find the element. So irrespective of this condition in the for loop, if you want to stop the execution, the one and only statement is break. So immediately after the key is found, set the flag to 1 and break. That means the control comes out from the loop. Right? Close the for loop. Now check the condition. If flag is equal to 1, it implies printf. So when this flag becomes 1, whenever the key is found. So the key is found. Else means if the flag is not equal to 1, that means this case is not a true for all the such elements. I mean for all the elements of array. Else printf key is not found. Close the main function. So this is a simple program to implement this linear search. So here there is no logic, just we are comparing the key element with every element in an array. So let us trace this program so that you can clearly understand. Let it be search is 30. So for I is equal to 0, so in the first iteration, if key is equal to I, that means key is equal to a of 0. That implies 30 is equal to a of 0 is 10. So here the condition fails. So there is no else part. Automatically I will be incremented. So I is equal. So sorry, the condition will be checked. And so okay, I will be incremented. And 1 less than 5. The condition is checked. 1 less than 5 true. So again key is equal to a of I is 1 now. So key is 30 is equal to I of 1 is 20. Again the condition fails. So there is no else block. Again I will be incremented. So I is equal to 2. The condition checks 2 less than 5. True. So again if key is equal to a of 2. That means here key is 30 is equal to a of 2 element is 30. So condition is true. So if this condition is true, set the flag to 1. So here the flag is 1. Here the flag is 0. So flag doesn't changes its value. Initially we have initialized the flag with 0. So here the flag will not change. Here the flag is set to 1 and break. So automatically the control will come out from the loop, and if flag is equal to 1, so flag is equal to 1, again true, so key is found. So hope you understood this simple linear search problem. If you like my videos, share my videos with your friends, and so the advantage of this linear search is the order of elements can be in any order. That means there is no restriction of considering the elements. Whatever the order it may be, the search will be executed. That means there is one more drawback for this linear search, that is if our search element is the last element in an array, so the user have to wait until it completes all the iterations of an array. So it would take most number of time to get the result if the search key is at the last position in the array. So because it will search for every element in the array, so it takes much time to execute and to get the result. So that is the main drawback of linear search. For this purpose, we are moving on to the another search procedure, that is binary search. So here in the binary search there is a constraint. So before applying this binary search, we have to take care that all the elements of an array should be in a sorted order. So first we have to sort the array and then we have to apply the binary search. So in this binary search, we will just reduce the problem space into small parts, search space into small parts. So let us have a look on the binary search procedure, and then we will move on to the program to implement this binary search. So in this binary search, as I said that first we have to sort an array or just take the input as a sorted array, sorted elements, and then apply the binary search. So let us take the sorted elements in an array and then we will apply this binary search. So let it be A is an array with an elements of 6. Those elements are 10, 20, 30, 40, 50 and 60. So these are the 6 elements in an array. So now we have to apply the search element. So apply the binary search. So that means we must have one search element. So which element to be searched? So let it be, it is a key. Key is equal to, similarly we can take it as 20. We can take it as a 20, or so we can say take it as a 50, right? We can take key as 50. That means we have to find the number 50 whether it is presented in array A or not. So let us take here 10, 20, 30, 40, 50, 60. So index values are 0, 1, 2, 3, 4, 5. These are the index values. Next, these are the elements, right? Array elements. So array elements are A of 0, A of 1, A of 2, A of 3, A of 4 and A of 5. So these are the elements, these are the index values, and these are the array representation, element of array representation. Now initialize the first value with low and the last value with high. So here always the low will be less than high, because low is the initial position, high is the last position of an array. So first we have to initialize this low as 0 and high as last element, that is n minus 1. If n is the size of an array, we can take it as n minus 1. Here we are taking 6 as the size of element, so fifth position is the high element. Now calculate the middle value. So middle value is equal to low plus high by 2. The middle value is low plus high by 2. So there we have to use floor function. Floor, that means we have to consider the lower element. So here let us consider low is 0 plus high is 5 by 2. So that is 2.5. So we have to apply this floor function. So round it to lower value, that is 2. So if we round this function to upper value, it will become 3. So here we have to consider the flooring function. That means we have to round the value in the lower value to the lower value. So here mid is equal to 2. Mid is equal to 2. So carefully observe this: mid, low and high. All these three are the positions, that means index values. So here low, high, mid, all are the positions, that means indexes, right? So index values. So low is the index value 0, high is the index value 5 and mid is the index value 2. So after calculating this middle value, we have to compare this key with middle element. So here middle is equal to 2, here 2 is the index value. So in order to check the value at this index, this should be written as A of 2. So this is the middle element. Hope you understood this. Here 2 is the index. So I want the value at that particular index, so I have to write it as A of 2. Now we have to compare this mid value with key. Middle element with key. So that means comparison means we have to find the relation between this middle element and the search element. So based upon the result, we have to change the next lower value and higher values. So that means we have to consider mainly the relation between two variables are nothing but either they will be 0 or less than or greater than. So we have to check all these three things. So first case, key value is equal to A of mid. First we have to check it. Key is equal to A of mid. So if this condition is satisfied, it says that the element is found in the array at the position of mid, at the index value mid. So here if key is equal to A of mid, key found. So if this condition fails, that means key is not equal to A of mid, then the key will be less than mid or key will be greater than mid. Let us write here, key is less than A of middle value. So key element is less than the element which is at the position middle. So as I said that the constraint for binary search is the elements in an array should be in a sorted order. So if the key is less than A of mid, automatically the search space will be reduced. That means, so here the A of mid is A of 2. So this is the middle value, right? So if the key is less than mid, the key that implies the key element is presented in the left hand side, left hand to the mid. Hope you understood. So if the key is less than middle element, as it is the sorted order, as the elements are in a sorted order, obviously the key may be found in left side from the mid. So we can discard the right side of the mid and we have to consider only this part. So we have to change the middle position. So here low is equal to 0 and middle position will be mid minus 1. So middle position will be mid minus 1. So sorry. High position will be mid minus 1. So the search space, we are reducing the search space based upon this condition. So here key is less than the middle element, that implies the search space is on left side. So we have to consider the space, the search space on left side. So on the left side, the lower value is low and the high value is mid minus 1. So we have already compared with mid. So we have to compare from low to mid minus 1. So that means from low to mid minus 1. So low will be always 0. So the high value I have changed it for mid minus 1. If this is also fails, this condition also fails, then go to the third condition, that is key is greater than A of mid. So here if key is greater than middle element, that means the element may be on the right hand side. So the key element may be on the right hand side. So all the left hand side from the mid can be discarded. So we have to follow the search procedure from mid plus 1 to high, because the element may be on the right hand side. So we have to, so that means from mid plus 1 to high. So search space is, so this is a search space. So if key is less than A of mid, the search space is low to mid minus 1, and if key is greater than A of mid, the search space is middle plus 1 to high, because in the middle element we are already comparing that with the middle element in the first condition. So here we have to change the lower value. Low is equal to mid plus 1 and high will be always high. Again follow the same procedure. So the high has been changed and in this condition low has been changed. So again you have to find out the middle element, middle value for the modified high or low. So here these are the conditions, that means either one among these three conditions will be true. So not both the conditions. So any one condition among these three will be true. So either high will be modified or low will be modified. If high is modified, then find out the middle element for lower value and the modified high value. And if the low value is modified, find the middle element for modified low value and high value. And again repeat the same procedure to find the key element. Again find the key, compare the key with A of new middle element. So we will get the new middle value. So that new middle value is compared with the key, and if this condition again it is false, again you go for this condition. If it is true, modify the high value, and if it is false, go to this condition. Again you have to modify if this condition is true, again you have to modify the low. So finally, either in these three conditions, any one condition will be true, because this is the relation between two variables. So we can strongly say that the relation between two variables is either one variable is equal to another variable, or one variable is less than another variable, or the first variable is greater than second variable. So any one condition will be satisfied. So we have to repeat this condition, all these conditions, until low becomes greater than high. Low greater than high. So we know that the lower value is the initial position and high value is the last position. So the low value will be always less than high. So we have to repeat these steps until low is greater than high. So if we get this low is greater than high, even though we are unable to find this key, so that implies the key is not found in the given array. So if the key is found in the array, so before going this condition becomes true, we will get the result. Before this condition becomes true, we will get the result. So we didn't get the result, and this condition becomes true. Automatically, it implies the key element is not found in the array. So all this happens only when the array elements are in the sorted order. So that means the user or the programmer should be careful that before implementing this binary search, that all the elements in an array should be in a ascending order. So if those elements are not in an ascending order, first we have to apply the sorting mechanism on that array and then apply the binary search. So let us have an example, and then you can clearly understand here. Let us have an example now. See, key is equal to some 50. Now let us write here the summary so that it will be clear. So key is equal to A of mid, then found, set the flag, then key is less than A of mid, so change the high value, high is equal to mid minus 1, and if key is greater than A of mid, and that means middle element, then low value will be changed to mid plus 1. So this is a summary. So we have to repeat this until low is greater than high. I have to repeat that procedure. See, let us take elements 10, 20, 30, 40, 50 and 60. So here key element is 50. So let it be, this is a high value, this is the low value. So that means 0, 1, 2, 3, 4 and 5. So here low is 0, high is 5, middle value is L plus H by 2, that is 2. So we have to apply the flooring function here, 2. So now check the condition, key is equal to A of 2. So here key is 50 is equal to A of 2. So this is the middle element. This is the middle element, right? So this is the middle element now. 30. So condition fails. Now check the another condition. Key is less than A of 2. That means 30 is less than 50. This is true. Key is less than 50. Sorry, I just written wrong. So here the condition is false. So again go to the second condition. Key is less than A of 2. That means here key is 50, less than A of 2 is 30. Again condition false. Now third condition. Go to the third condition. Key is greater than A of 2. That means 50 is greater than 30. Condition true. That means we have to change the low element. So low is equal to mid plus 1, M plus 1, that is 3. And high will be as usual, that is 5. Now calculate the middle value, L plus H by 2, that is 3 plus 5 by 2, that is 8 by 2, 4. So again calculate the same. If key is equal to A of 4, now mid value is 4. Mid value is 4. So here key is 50 and is equal to A of 4 is 50. Condition is true. So here we find the key element in an array. We found the key element in array. So in the similar way, we have to repeat the procedure until we find this search element. So we have to repeat this until this low is greater than high. So if this condition becomes true, low is greater than high, we have to stop the procedure and simply we can say that the element is not found in the array. So let us write a program and let us trace that so that you can clearly understand here. So let us declare an array 10, 20, 30, 40 and 50. Let us stop here. So then enter the key element. Let it be the key element will be some 50. Key element will be 50. So we have to search the key element in the array. Now initialize low value to 0, high value to n minus 1, that is 4, 0, 1, 2, 3, 4, right. So calculate the middle element. Middle is equal to low plus high by 2 Now while, sorry, we can write it in the loop so that it will be easy. While low is less than high, so we have to repeat this loop until low is less than high. So low is always less than high, so we have to repeat this loop. That means the control will enter into the loop whenever this low is less than high. If low is greater than high, it implies the key is not found. So until the last element, we will repeat the same set of statements. Low is less than high. Now find the middle element, low plus high divided by 2. Now find that if middle is equal to, if key is equal to a of middle element, so we said that printf key form, or simply as in the linear search we can set the flag. Let us set that flag. Some flag is equal to 1. Initially take that flag, so int key is equal to 50, flag is equal to 0. Initialize this flag with 0. So if key is equal to bit, write the flag 1. Then flag 1, stop the procedure, so we have to write the break statement. Else if, that means if this condition is false, key is less than a of mid. So if key is less than a of mid, now we have to change the high value. So high is equal to mid minus 1. Else, so if these two conditions are false, automatically the third condition will be true. So we need not write again the condition, so simply we can write else, change the low value. Low is equal to mid plus 1. So close the while loop, and here check the kind of flag. If flag is equal to 1, printf key is found. Else, so if the flag is not equal to 1, that implies printf key is not found. Close it. So see, this loop will continuously executes until this condition is true. That means low is less than high. Whenever this low is greater than high, automatically it will come out from the loop. So here we are just finding the middle value, and we are comparing this middle value with key. So key is equal to mid, key less than mid, or key greater than a of mid. If key is less than a of mid, high value will be mid minus 1. If key is greater than mid, low value will be mid plus 1. Now let us trace this so that you can clearly understood. So let us trace here. Now initially take key, so here we have taken this key as 50. So first low is equal to 0, high is equal to 4. So calculate the middle value. So middle value is equal to 0 plus 4 divided by 2, that is 2. Now, so low is less than high, 0 is less than 4, so control will enter into the loop. Now calculate the middle value is 2. Now compare this condition. So if key is equal to a of mid, that implies here key is 50 is equal to a of mid, that means a of 2. That implies 50 is equal to a of 2. So this is the first element, 0th element, first element, second element, third element, and fourth element. So this is the index values. So here a of 2 means 30. So the condition fails. Automatically it will not enter into this condition, if condition. Automatically the control will go to the else if condition. Again it check for this one. So now key is less than A of mid. That implies 50 less than A of 2 element is 30. 50 less than 30. Again the condition fails. So here also the condition is fails. So automatically the third condition will be true. That means now low will be changed. So low is equal to mid plus 1. So mid plus 1 means here mid is 2. 2 plus 1 is equal to 3. And high will be same. High is equal to 4. Now calculate, low is equal to 2 plus 1 and high will be 4. Now again, so after ending this loop, again check the condition. Low is less than high. 3 is less than 4. So condition is true. Again calculate the middle element. Middle element is equal to 3 plus 4 by 2. That means 7 by 2. 7 by 2, that is 3. We are applying the floor function. Now again start procedure. Key is equal to A of middle element. That implies 50 is equal to A of 3. That implies A of 3 means 40. So 50 is equal to 40. Condition fails. Go to the second condition. Key is less than A of middle element. That implies 50 less than 40. Again the condition false. So third condition will be executed. That means low is equal to mid plus 1. So here low is equal to, here again mid, that means 3. So 3 plus 1, that implies 4. And high will be, again it is a 4. Then or equal to, if we set that less than or equal to, right? So here just change the condition. We have to change less than or equal to. That means the last statement. So if here 4 less than or equal to 4, that means again enter into the loop. So middle element is equal to 4 plus 4 by 2, that means 4. Again check the condition. If key is equal to A of mid, that means key is equal to A of mid. That implies 50 is equal to A of 4. So that implies 50 is equal to 50. Condition true. So flag is set to 1. So here flag will be set to 1. Break. Automatically the control will come out from the loop. So if flag is equal to 1, yes, flag is equal to 1. So automatically the printf key is found. Hope you understood this simple procedure of binary search. So in today's session, let us have a look on sorting mechanism. So there are many techniques to sort the elements in an array. So among those, we are seeing the one technique, that is bubble sort. So today's session, let us have a look on this bubble sort. So first consider the elements, some 70, 40, some 50 and 10. Let us have the elements, the 4 elements. Now we have to perform the bubble sort. Just I have taken a little number of bits because so the explanation will be simple. So in the bubble sort there are 5 elements, so 4 elements, so n is equal to 4. Now in the first iteration, we have to compare the first element with immediate next element. So the input for the first pass is the first element and second element. So if the first element is greater than the second element, perform the swap operation. That means we have to interchange the numbers. That means 40 must be bring to the first position and 70 must be sent to the second position. So that means interchange the values. So the output for this is 40, 70, 50 and 10. Again, now compare the second element with the next immediate element. So this will be performed. Again, the same condition will be checked. If the first element is greater than the second one, we have to interchange those elements. Again, 70 is greater than 50, so we have to interchange. So swap, apply the swap in between 50 and 70. The resultant will be 40, 50, 70 and 10. Again, now compare the third element with the last element. Next immediate element. So now 70 and 10 will be compared. So here also the 70 is greater than 10. So we have to perform swap operation. That means we have to interchange the 70 and 10. The resultant will be 40, 50, 10 and 70. So this is the resultant of pass 1. Here we get the highest element, that means largest element. So after the first pass, the largest element will be set to the last position. Now let us have the second pass, next iteration, pass 2. So pass 2, the first input is 40, 50, 10 and 70. So we have to again repeat the same process. First we have to compare the first and the next element. 40 is less than 50. So 40 is not greater than 50. So no change should be done. No swap. So we should not interchange those values. So just the same value will be returned. Again, the second element and the third element will be get compared. Again, 50 is greater than 10. So we have to perform that swap. That means we have to interchange the elements. So we have to interchange the swap. Next, the resultant will be 40, 10, 50 and 70. Again, perform the last element. So next, third element with the fourth element. 50 is less than 70. So no swap. So the resultant will be 40, 10, 50 and 70. So here this last position is the largest position. It was fixed, and now in the second pass the third position is also fixed. The second largest will be fixed. Now coming to this pass 3, third iteration. The input for the third iteration is 40, 10, 50 and 70. Again follow the same procedure. So here the 70 is fixed, 50 is fixed. So now first element and second element will be get compared. So as 40 is greater than 10, we have to perform the swap. That means we have to interchange the 40 and 10. So the resultant will be 10, 40, 50 and 70. So these are fixed. Again now the 40 will be compared with 50. Though no swap because 40 is less than 50. So 10, 40, 50 and 70. Again 50 is compared with 70. So again no swap. So the resultant will be 10, 40, 50 and 70. So we got the final sorted list. That means if there are n elements to be sorted, the number of iterations must be 3 iterations. In the 3 passes, we will complete the sorting procedure. And in each pass, we will perform total n minus I iterations. If I is the pass, here I is the pass, n is the number of elements. So in each pass we will perform n minus I iterations to get the result. So we have to use nested loops. In the outermost loop, that is I for the passes, and innermost loop, that is j for the operations done in each and every pass. That means comparisons in each and every pass. So in each and every iteration we have to compare the present element with the next element. So if the present element is greater than the next element, automatically we have to perform the swapping operation. That means interchange. We have to interchange the values. So as we know that the swapping procedure, the logic for swapping is we can use the temporary variable, third variable. So if a is equal to 10, b is equal to 20, so swapping procedure, applying the swapping procedure using the third variable, we can write temp is equal to a is equal to b is equal to 10. So here the temp is equal to 10, here a is equal to b 20, b is equal to 10 means 10. So a is equal to 20, b is equal to 10. So after swapping. So this is a simple logic we have to perform in each and every inner iteration. So two iterations there will be there. First iteration, that is outer loop, will be for the passes, number of passes, and the inner iteration or inner loop iteration is for comparing the corresponding elements, immediate elements. So hope you understood this procedure. We have to repeat the same procedure until you reaches the n minus 1 passes. So if there are 4 elements, we require 3 passes to get the result. If n is equal to 10, it requires 9 passes to get the result. So n minus 1 passes will be performed for getting the result. So for this, in order to implement this bubble sort, first we have to read the size of an array, and then we have to read the n elements, and then we have to perform the bubble sort. That means for outer loop, the outer loop for passes, and the inner loop is for comparisons. If the previous element is greater than the next element, we have to perform the swapping procedure. So hope you understood this procedure. Now let us write the program so that you can clearly understand. So now let us write the program so that you can clearly understand. So first we have to declare an array and a single dimensional array, and we have to declare the size, and then we have to read the elements into an array. For example, let us write here. So int a of 4. So I am taking a of 4. Let it be, or a of 10. Let us declare the array with the 10, and then scanf %d ampersand n, where n is the size of an array. So I am not writing the printf, right? So after reading the n, we have to read the value. So for I is equal to 0, I less than n, I plus plus, we have to write the scanf function to read the every element into an array. %d ampersand a of I, so that the elements will be stored in a of I. That means a of 0 to a of 3, because here we are giving the n value as 4 in this example. Right, after reading the elements, we have to use the nested loop for performing the bubble sort. So for I is equal to 1, I less than n, I plus plus. So this is for passes, and immediately next for j is equal to 0, this is for iteration to compare each and every element. So j less than n minus I j plus plus. Now compare each and every element, that is a of j is greater than a of j plus 1. So we have to compare the present element and the next element. So I have written j and j plus 1. So if j is equal to 0, a of 0 and a of 1. If j is equal to 1, a of 1 and a of 2. So the immediate elements will be get compared. And if this condition is satisfied, we have to perform the swapping operation. So temp is equal to a of j is equal to a of j plus 1, a of j plus 1 is equal to temp. So this gives the swapping logic. Now obviously close the inner loop and close the outer loop, and then print the elements in an array so that we will get the sorted out. So in order to print the elements, I is equal to 0, I less than n, I plus plus, printf percentage d a of I. So this closes our program. This is the simple logic for the bubble sort. So this is for inner iterations or for comparisons. This is for passes, number of passes. So if n is equal to 4, we require 3 passes. If n is equal to 5, we require 4 passes, n minus 1 passes. So let us trace here so that you can clearly understand. So without tracing the program, you can't get the logic, right? So we don't know whether the logic is right or not. So if you trace the program, we can get the correct logic. So let us take n is equal to, so let us take here. So n is equal to 4. So we will take the previous values, n is equal to 4, and the values are 70, 40, 50 and 10. 70, 40, 50 and 10, 4 elements. So this index value is a of 0, a of 1, a of 2, a of 3. Hope you understood, right? So after reading the values, now start the iterations. Now I is equal to 1. So first pass, I is equal to 1. So 1 less than n. Here n is 4. 4. So the condition is true. Obviously next j is equal to 0. Then 0 less than n minus I. That means 4 minus 1. 3. This is also right. So the control will enter into the loop. Now a of j value 0 is greater than a of j plus 1, means 1. So a of 0 is 70 greater than 40. So we have to apply the swapping operations. So temporary is equal to a of j. So t is equal to a of j. A of j here is 0. So 70. Next a of j is equal to a plus 1. So a of 0 is equal to j plus 1, that means 40. Then a of j plus 1, that means 1. A of 1 is equal to temporary, that is 70. So clearly observe that temporary is equal to 70, a of 0 is equal to 40, a of 1 is equal to 70. Now the values will be So a of 0 value is 40, 70, 50 and 10. So this is the output of the first iteration. Now this is the index value 0, 1, 2, 3. So index value, I am saying that it is an index value. That means a of 1, a of 0, a of 2, a of 3. Now again j is equal to, so j will be incremented. So j is equal to 1 comma 1 less than n minus I, that is I is still 1, so 4 minus 1, that is 3, 1 less than 3. Here the condition is true. So again perform the operation. So a of 1 greater than a of 2. So a of 1 here is 70 greater than a of 2 50. So the condition is again true, right? Here also the condition is true. Second swapping will be done. Temporary is equal to, so temporary is equal to a of j, that means a of 1. A of 1 here is 70. 70. A of j is equal to, that means a of 1 is equal to a of j plus 1, a of 2, that means 50. Similarly, a of 2 is equal to 70. Then now the result will be 40, 50, 70 and 10. So this is the position of 0, position of 1, position of 2, position of 3. So this is the output for second iteration. Now again j is equal to 2. J value will be incremented, j is equal to 2. So here j is equal to 2, 2 less than 3. Again the condition is true. So a of 2 greater than a of 3. A of 2 here is 70 greater than 10. Again the condition is true. Again there will be swapping. The same logic. Temporary is equal to 70, a of 2 is equal to 10, a of 3 is equal to this 70. So the output for this, so swapping will be performed. So the output will be 40, 50, 10 and 70. So a of 0, a of 1, a of 2, a of 3. So this is the output for the third iteration. 0th iteration, first iteration, third iteration, second iteration, sorry. So 3 iterations, 1, 2 and 3. Now again condition j will be incremented. So now j is equal to 3. So if j is equal to 3, 3 less than 3, the condition fails. So automatically now I will be, the control will come out from the loop. Now I will be incremented. I is equal to 2. Let us take here, okay. So I is equal to 2, second pass, that means this ends the first pass. I is equal to 2, 2 less than 4. So condition is true, right? So inner loop will be started. J is equal to 0, j is equal to 0 and 0 less than n minus I. Now I value is 2, so n value is 4. 4 minus 2, 2. So this is also condition also true. So now a of 0 greater than a of 1. So a of 0 is 40, a of 1 is 50. So condition fails. So if the condition fails, we didn't write any else function. So obviously the j will be incremented. So this condition fails because a of 0 is having 40 greater than 50. So this condition fails. So nothing will be happened, just j will be incremented. J is equal to 1 and 1 less than n minus I, that is 2. Again the condition is true. Now a of 1 greater than a of 2. So a of 1 value is 50 is greater than 10. So this condition is true, swapping will be done. So 50 will be placed to the a of 2 and 10 will be placed to the a of 1. So the same operation will be performed here. So after that we will get the result. So 40, 10, 50 and 70. So this is the 0th index, first index, second index and the third index. Now j is equal to 2. So j is equal to 2, 2 less than 2, condition fails. So it ends the second pass, because we need not compare the last element and the next element, because already 70 is the largest element here. So we need not compare the previous element with the last element. So we will stop here itself. Then I will be incremented now. So this ends the pass 2. Now I is equal to 3, third pass. So 3 less than 4. This condition is true. So the control will enter into the inner iteration. So now again j is equal to 0. So 0 less than n minus I. N is 4, I is 3. 0 less than 1. Again the condition is true. Now a of 0 greater than a of 1. That means 40 greater than 10. This condition is true. Now the swapping should be performed. So after swapping, the values will be 10, 40, 50 and 70. 0th value, 1 value, 2 value and the 3 value. Now j will be incremented. J is equal to 1 and 1 less than 1. So condition fails. So here the condition fails. Automatically it comes, control comes out to the outer loop and I will be incremented. Now I is equal to 3. Now I is equal to 4. This ends the third pass. I is equal to 4. The condition 4 less than 4. Again the condition is false. Again the condition fails. So the control comes from the outer loop, and for I is equal to 0 less than n I plus plus printf a of I. So here a of I means in the first iteration a of 0 10 will be printed, a of 1 40 will be printed, a of 2 50 will be printed and a of 3 70 will be printed. So finally we get the complete elements of an array in a sorted order. So if we take the n number of elements, we require n minus 1 passes to complete the iterations. I mean to complete the sorting procedure in the bubble sort. To our channel. So in today's session, let us have a look on sorting algorithm. So previously we have seen the bubble sort algorithm, and now we will see one more sorting technique, that is insertion sort. So the name itself indicates the insertion sort. That means we will compare each element with all the previous elements and we will insert the correct element into the desired location, right? So it will be very easy, simple logic. So first let us see the logic and then we will go to the program. So consider some 5 elements which are in a which are not in a sorted order. So for example, take 30, 10, 40, 20 and 50. So there are 5 elements. So this is the index position 0, 1, 2, 3, 4. This is the index. This is the element. Right? So we have to compare each element with the previous element. So first we will start from the index 1. So first we will start from index 1. Right? So the index 1 element is 10. So the 10 must be compared with all the previous elements. That means all the elements which are on left hand side, right? So these elements must be compared. So here 10 is the second element, that means first position. So only one element should be compared. That means it should be compared with 30. So at index 1, let us take some temporary variable. In that temporary variable, just place the element which to be compared. So first element is compared, I mean the second element is stored in the temporary variable, and this variable or this value will be compared with all the previous elements. So first, So 10 is less than 30. So 10 is less than 30. So we know that if the elements are in the sorted order, so if we consider any element, all the elements which are less than that particular number will be on its left side. Right? If we take 5, so less than 5 will be on the left side, greater than 5 will be on right side. Right? So here 10, so we have to compare with previous element. 10 less than 30, so this is true. So it is true, that means that element should be on left hand side of the particular 30. So now this is true, 30 will be moved to right side. Okay, so initially this index value is 0, so the element will be moved to the index value 1. So this is the index value. Right? So next one will be 30, that will be moved on to the first index. So 30, 40, 20 and 50. So there are no more elements on the left side, right? So this is the only element because we are comparing the second element with the first element. So directly replace the value of 10 at the position of 0. So 10. So this is the output of first iteration. After the first iteration, the output will be 10, 30, 40, 20, 50. So we can observe that after the first iteration, the first two elements will be in a sorted order because we are comparing the second element with the first element, and based upon their condition we are just inserting the element at the desired position. So first two elements will be in a sorted order. Next, after the next one, second iteration. So first position is completed. So here I am writing the index value 1. Now the index value must be 2. So we have to consider the second index. So, sorry, I have written already the index 1. Now the index value is 2. That means, so this is the input for the second iteration. The index value 2. That means here. Right? So 40 should be compared with all the elements previous. That means all the elements which are left hand side of this 40. So there are two elements here. So we need not search for the first element. I mean, we need not go move on for all the elements. Just we can compare with the immediate element. If this condition is true, then we have to move to its right. Right? So see, for example, here we will see this. We will follow the same procedure. So we have to compare all these things, 10 and 30. So 40 is compared with 30, right? So 40 is less than 30. Here the condition is false, right? 40 is not less than 30, right? So we should not change the positions of the current elements. So no change on the positions. Obviously, if 40 is greater than 30, 40 is always greater than the first element because these two elements are in a sorted order, right? So we are comparing 40 with index 1, element in index 1. So if this is greater than index 1, we need not go for index 0 because these both are in a sorted order. Obviously, the second element will be greater than the first element, that is index 0. So false. Or else we can compare 40 compare with 10, that also greater than, so no change will be occurred. So at the index 2, temp is 40, so we have compared everything, so no change for the second iteration. So the output of second iteration is 10, 30, 40, 20 and 50. Now coming to the third iteration, index equal to 3. Index equal to 3. So index is equal to 3 means 20. Now we have to compare this 20 with all the previous elements. That means these 3 elements. So first 20 must be compared with 40, right? So 20 less than 40. Yes, true. So if the condition is true, that means the element should be on left hand side of this 40. So move the 40 towards the right side. So 40, the index of 40 should be moved to next index, that is index 3, right? Now the output will be 10, 30, 40, 40, so here 10 is equal to 20, right? 40 and 50. Okay, we are just copying the 40 to the next position, right? Now again the temp must be compared with this one, because already the temp is compared with the second index. Now temp must be compared with the first index. So again 20 less than 30, right? 20 less than 30. 20 less than 30 means again the condition is true. So again the 20 should be on the left hand side of this 30. So again 30 should be moved. So what is the index value of 30? 1. So move to index 2. So the output will be 10, 30. So 30 will be copied into second index. So 40 will be replaced with 30, 40 and 50. Right? Don't get confused. Just we are replacing the values. But the comparison value will be stored in the temp. Right? So after getting the desired location, then we are copying this temp value to the particular location. Just we are replacing. Here we are not exchanging, we are not swapping any two numbers. We are just copying the number to at the particular index values. So before we are just saving the value at the temp, and after finding the desired location of that particular element, that element will be replaced with the element which is residing in the desired location, right? Now 20 is compared with 30. Now 20 is compared with 10. So 20. So now 20 must be compared with 10. 20 is less than 10. So here false. Here it's false, right? So no change. No change. And we have to copy this temp at the particular location. So 10, 20, 30, 40, 50. So this is the output of third iteration. So this is iteration 1, iteration 2, iteration 3. Right? So this is the output of third iteration. Now again there is another number. So move on to the fourth iteration, that is index 4. So index 4 is 50. Now consider, so the output of third iteration is 10, 20, 30, 40. Okay. Now the element to be compared is at index 4. So index 4. So temp is equal to 50. Now 50 should be compared with these elements, right? So 50 is less than 40. 50 is less than 40. Is it true? Say false. Right? So as it is a false, no change will be occurred. So understand clearly, if the value of the immediate element becomes false, we need not check all the remaining elements, because already these 4 elements are in a sorted order. So if the given number is greater than the previous number, obviously it will be greater than all the remaining elements, right? So no change will be occurred, so the output will be 10, 20, 30, 40 and 50, right? So where we have to stop these comparisons. So when j greater than 0, j is a loop variable, and obviously temporary value less than a of j minus 1. So temporary value less than a of j minus 1. So previous one. So at this condition we have to stop the comparisons, right? So hope you understood this simple logic. So first consider all the elements, start from the index 1. So consider the element at the index 1 and compare it with all the previous elements. That means all the elements on its left side, and after completion, so find the desired location of that particular number. So here we are finding the location of, in the 4th iteration we are finding the location of 50. In the 3rd iteration we are finding the location of 3rd value. In the 2nd iteration we are finding the value of 2nd value, right? So after every iteration we are getting the particular desired locations of a numbers. So here we are not using any swappings or interchanging, just we are copying that number to the right hand side, and just we are copying the value which we are comparing to the desired positions. Okay, now let us write the logic so that you will clearly understood, and after that I will show you by executing this program, and also I will show you in a presentation, right? See, take the loop variable. So from the first element, index value 1, 2, 3, 4, if n is equal to 5. This is happened in the given example which we have taken, right? So I is equal to 1, I less than n, I plus plus. So we have to repeat these iterations. In that iteration, first we have to store the temporary variable. Temp is equal to a of I, because we are replacing, right? So we are just copying the number to the just immediate positions. So we are just save this number in a temporary variable. Next, compare all the previous elements. So consider this element and compare all the previous elements. So for j is equal to I, j greater than 0, right? J must be greater than 0, and we are using logical AND. Temp should be less than a of j minus 1. So if any one condition is false, automatically the iteration will be stopped. J minus minus, we have to decrement. So we are moving from right side to left side. We are moving from right side to left side, comparing each and every element. So we are considering from I to j minus 1. So if this condition is true, what we have to do? We have to replace. That means we have to move the current value to the previous value. A of j is equal to a of j minus 1. So we are moving, right? We are moving the value to the next number. Close. If this has not happened after this completion, that means after this loop, we will get the position. So at this position we have to place the temporary value. So a of j is equal to 10. So temporary value will be stored in the location. Close. This is a simple logic for insertion sort. There is no exchange. Just we are comparing the elements. So this is for comparing with previous elements. Right? This is for inserting the element at desired location. Right? So this is, so how many iterations? So n minus 1 iterations should be done. If n is equal to 5, 4 iterations will be done. So we have to start from index 1 to n minus 1. That is 4. So that we have seen in the example. Right? So hope you understood this simple logic for this program. Insertion sort. Now I will show you this procedure using the PowerPoint presentation, and then we will implement this insertion sort using the C editor.
We have discussed the insertion sort. Let us see the presentation so that if you are having any doubts, those doubts can be easily clarified. See, so as we have discussed that in this insertion sort, first we have to consider the second element and it must be compared with the first element. And if the second element is smaller than the first element, then the second element must be inserted in the position of first element, and the first element should be moved towards its right side. So after the first step, the first two elements of an array will be in a sorted order. Similarly, in the second iteration, so here steps means the iterations. So in the second iteration, the third element will be considered and it will be compared with all the remaining previous elements, that means the first and second elements. So here, if the third element is smaller than the first element, then it must be inserted in the position of the first element. And if the third element is larger than the first element but the smaller than the second element, then it must be inserted in between the first and third elements, that means the position of second element. And if the third element is larger than both the elements, then it must be kept in its position as it is, that means no change will be occurred. So after the second iteration, the first three elements of an array will be sorted. Similarly, we have to repeat the same procedure for all the remaining elements of an array until we are comparing the last element with all the previous elements. So after completion of all these iterations, automatically the elements of an array will be in a sorted order. Now let us take an example. So let us consider the 5 elements. So here you can observe the circle with a number is a index values. That means 0, 1, 2, 3, 4 are the indexes. So here we are considering 5 elements. So the index from 0 to 4. And inside the square, those are the actual elements. That is 20, 50, 10, 30 and 40. So first we have to consider from the first index. That means the second element. Second element is here the index value is 1. So the what are the elements we have to compare? All the previous elements of the current index. That means the 0th index element must be compared with the first index. So on the rightmost corner top, we are writing the element which we are comparing with the remaining previous elements. So we are comparing here the 50 with all the elements which are before the 50. So here before the 50 we are having only one element, that is 20. So 50 is compared with the 20. So here 50 is less than 20. So 50 is less than 20. It's a false. So no change must be occurred. So after the first iteration, we have to there must be no change, and after the first iteration, the values will be as is. That means 20, 50, 10, 30, and 40. Now in the second iteration, consider the third element, that is index value of 2. So temp is equal to 10, and this 10 will be compared with all the elements before the 10. That means here we are having two elements with index values 0 and 1. Elements are 20 and 50. We have to compare this 10 with 20 and 50. So 10 is less than 50. The condition is true. So the 50 will be moved to the right side. So here 10 will not be inserted in the first position. Just we have to compare with 20 also. So here 10 is again compared with the 20. So it is also true because the 10 less than 20. So 20 must be moved to the index value of 1. That means the right side. So 10. So as the 20 is at the index value 0. So the 10 will be inserted in the index value of 0, right? So here we are comparing 10, and the 10 must be compared with the remaining two elements. So first 50 is compared, so 10 is less than 50, so 50 should be moved on it to its right side. Again 10 is compared with the 20, so it's also true, 10 is less than 20, so 20 is also moved on its right. So as the 20 is at the index value 0, so the 10 will be inserted at the index position 0. So after the second iteration, the values are 10, 20, 50, 30, 40. Now coming to the third iteration, the 30 will be compared. So temp is equal to 30. The 30 will be compared with all the elements before the 30. So here there are three elements. So 30 is compared with 50. 30 is less than 50. It is true. So 50 is moved on to its right. So again 30 is compared with 20. The condition is false. No change will be occurred. Again the 30 is compared with the 10. 30 is less than 10. Again the condition is fails, so no change will be occurred. As the 10 is in at index 0, so there are no more elements to be compared, so the 30 will be inserted into the position of index 2. So only index 2 position is free now. So previously index 2 is having 50, so the condition is true, so 50 is moved to the right side, so the position 2 is free, so we are inserting 30 into the position of index 2. So after the third iteration, the values will be 10, 20, 30, 50 and 40. Next iteration, the value is 40. Now 40 must be compared with all the remaining elements. So there are 4 elements before 40, 50, 30, 20 and 10. Now let us compare one by one. So 40 is less than 50. The condition is true. So we have to move this 50 to the right side. Again 40 is compared with 30. So condition false. So no change will be occurred. Again 40 is compared with 20. Again false. No change will be occurred. Again the 40 is compared with the 10. Again false, no change will be occurred. And as the 10 is at index 0, there are no more elements to be compared. So this 40 will be inserted in the position of index 3. So previously in the index 3 the position, the value is 50, so 50 is moved on to its right side, so the 40 will be inserted in index 3. So here 4, index 4 is the last element, so there are no more elements to be compared. So we have completed all the iterations. So after completion of comparing all the elements with the previous elements, the resultant array will be 10, 20, 30, 40 and 50, which are in a sorted order, right? So hope you understood this simple logic for insertion sort. Now let us trace out with by implementing this insertion sort using the C program. Hope you understood the procedure of insertion sort. Now let us see the implementation of insertion sort using the C editor. Yes. Let us implement this, the logic of insertion sort. So first include the header file, write the main function, and try to avoid declaration at the first time, right, at the beginning. So after completion of the program we can use the declaration. So first we need an array, so we have to specify that array, the size of the array. Enter the size of an array. So we have to save that in one variable. Let it be n. Now we have to enter the elements into an array. Printf, enter the elements into an array. So we have to enter the n elements. So we have to write the for loop I is equal to 0, I less than n, I plus plus. specified on the scanf. So as the scanf is only the single statement, we need not include the braces, right? So percentage d ampersand e of I. Now we have to write the logic. For the iterations, let us take I is equal to 1, because first we are starting from the second element, right? So here the index values will be from 0 to n minus 1, n minus 1. So the first element, from the first element we have to start the iteration. So I is equal to 1 till I n minus 1 I plus plus. So if n is equal to 5, we have to work out with the 4 iterations. See, first let us store the first element into the temp, so that we can compare this temporary variable with all the remaining previous elements. So temp is equal to f5. Now again we have to compare each and every element of an array to get the desired position of the current element. For that, j is equal to I, j greater than 0. So we have to do the number of iterations such that until this condition becomes false. That means j greater than 0, as well as the temp must be less than a of j minus 1, the previous element. That must be less than previous element, right? See. So for this, if the condition is true, that means the index value is greater than 0, and the temporary value, that means the current element is less than the previous element, then we have to move that into the right side. So a of j is equal to a of j minus 1, right? We are moving to the right side, and after moving all this one, we will get the desired position. In that desired position, we have to insert the element. So which element we have to insert? Whatever the element we are comparing with all the previous elements, that element should be inserted into the desired location. Then a simple logic, that's it. Now after completion of all the iterations, we can get the array elements in a sorted order. So in order to print the elements of an array, we have to use iterative statements. Printf percentage d slash t e of I, right? So for understanding purpose, let us print all the elements before sorting, so that it will be useful, right? Printf before sorting. Sorry. For I is equal to 0, I less than n, I plus plus, printf percentage d slash t p of I, right? So this is for size of an array, this is for elements insertion, this is for printing before sorting, and this is the logic. Here let us replace it after sorting. After sorting, this is the logic. So now write the declarations. What are the variables which we are using? N for the size of array, and size of the array, maximum size, give the maximum size, I value, j value, temp value, and everything. So declaration part, and this is the size of an array, this is printing elements before sorting. Sorry, printing elements into an array. So reading elements into an array, and here printing elements before sorting, and then insertion sort logic printing elements after sorting. See, let us compile this one. So first let us save this one. Insert.c. So right, let us take insert.c. Let us compile it. Let us run it. So enter the size of an array. Let us take 5 elements. Let us take the elements. So 20, 40, 30, 10, 50. So we can get it from F5. So before sorting it is 20, 40, 30, 10, 50, and after sorting it is 10, 20, 30, 40, 50. Once again I will show you with a clear screen. So here CLR SCR, this is for clearing all the previous inputs, and before sorting, and here we will give /n so that the display will be good. Now let us compile, let us run. So enter the size of an array, 5 elements. Let us enter the 5 elements. Let it be 30, 20, 50, 40 and 10. So 30, 20, 50, 40 and 10. See, so before sorting the elements are 30, 20, 50, 40 and 10, and after sorting 10, 20, 30, 40 and 50. Right? So hope you understood this the simple logic for this insertion sort. So just we will consider one element, and we will compare that element whether it is less than that element or not with all the previous elements, and we will find the desired position of that particular element, and we will move all these elements towards the right side, and we will insert that position, we will insert that element into the position of that particular index value.
Friends, let us trace the logic of insertion sort with a given example. So here I am considering 4 elements, so n is equal to 4. Now let us trace this one by one. So first iteration, in the first iteration the index value will be, so here the index value is 0, 1, 2 and 3. So we have to take it as 1. So I is equal to I. So I is equal to 1. So 1 is less than 4, condition is true. Then temp is equal to A of I, that is A of 1, which is 10. Right? Now J is equal to I, 1, J greater than 0, 1 greater than 0, this is true, and temp 10 less than A of J minus 1, A of 0. So A of 0 means 20. 10 less than 20. So this condition is true. So this is true, this is true. So the condition is true as it is a logical end, right? Now then if it is true, we have to copy this. That means A of J1 is equal to A of 0. So A of 0 element should be copied into the A of 1. That means A of 0 means 10. Sorry, 20. 20 will be copied into the 1. So element of A of 1 is 20 now. See. Right? Then again J minus minus. So now J is equal to 0. Comma J greater than 0. 0 greater than 0 and temp. Temp value is 10 less than A of J minus 1. A of minus 1. So this is false. If any one condition is false, automatically this statement is false, right? So this statement is false. Automatically the control will come out from the loop. A of J is equal to 10. So J value is 0. A of 0 is equal to temp value. That is 10. Right? Now 10 will be copied into the index 0. That is the output of first iteration. So right here so that you can clearly understand. 10, 20, 40 and 30. Right? So this is the index 0, 1, 2 and 3. This is the completion of first iteration. Now after completion of this one, again I++. That is second iteration. Second iteration I++. Now I is equal to 2. I is equal to 2. So 2 less than 4. Condition is true. Right? Condition is true. Then temp is equal to A of I. Temp is equal to A of I means 2, which is equal to here. So 40. Temp is equal to 40. Next, for J is equal to, so J is equal to I. I means 2. 2 greater than 0 and temp less than. Temp means, see, temp less than A of J minus 1. 2 minus 1, 1. So here temp value is 40 less than A of 1. What is the 1? 20. So 40 is less than 20. So condition fails because this is the false, this is the true. Obviously the result will be false as we are giving the logical here. Right? Automatically the control will come out from the loop. Condition fails. The control will come out from the loop. A of J is equal to 10. So A of J means 2 is equal to temp 40. So obviously A of 2 is equal to 40. There is no change. Right? Next, again I++. This ends the second iteration because here 20 is less than 40. That means immediate element is less than the current element. Automatically we can stop comparing all the remaining elements because all the remaining elements are already in the sorted order. If we are comparing the second element with the first element, the 0th element and first element are in a sorted order. Obviously, if first element is less than second element, automatically the 0th element is also less than the second element. Right? So, third iteration. I++. Now I is equal to 3. 3 less than 4. Condition true. So, temp is equal to A of 3. That is equal to 30. So after the first iteration I will write here. So 10, 20, 40, 30. After the second iteration also the values are same. Right? Now see, temp is equal to A of I. 30. Now for J is equal to I. J is equal to 3. 3 greater than 0, it's a true. and temp less than, so temp less than a of j minus 1, that means 2. Here j is 3, 2. So temp value is 30 less than a of 2 value is, see, 40. A of 2 is 40. This is true. 30 is less than 40. It's also true. So the condition true. So if this condition is true, enter into the loop. So a of j, that means a of 3 is equal to a of j minus 1, 2. So a of 2 value should be moved to a of 3. So a of 2 value is 40. 40 should be moved to third position. So 40 will be placed in position this one. So see, 40 will be copied at 3. So we are not erasing this second value, right? We are just copying the, assigning the second element to the third element. Now completed, j minus minus. Now j is equal to 2. 2 greater than 0 and 2 greater than 0 and temporary value, that is 30 less than a of j minus 1, that means a of, now j is 2, a of 1. So 30 is less than, what is the a of 1 element? 20. 30 is less than 20, this is false, this is true. So obviously if one condition is false, automatically the complete condition will be false because we are using the logical AND. This is false. Automatically the control will come out from the loop. A of j is equal to 10. So a of j, that is 2, is equal to 10, 30. So 30 will be assigned to a of 2. Here 30 will be assigned to a of 2. Right? Now again, so after this third iteration, we got the values 10, 20, 30, 40. Again, I is incremented. So this loop completed, I is incremented. Now y is equal to 4. I is equal to 4. 4 less than 4. Condition fails. Condition fails. The control will come out from the outer for loop. That means we have completed all the iterations. So here we are considering 4 elements, so that we have to do the 3 iterations. So after the 3 iterations, automatically at the 4th iteration, the control will come out from the loop. Selection sort. So as the name itself indicates, we have to select the elements and we have to keep that particular element at the desired location. So which element should be selected? So in the first iteration, we have to select the lower element. I mean the lowest element. And it will be placed in, so this is the index. This is the iteration. Or pass, okay, first pass, second pass, third pass, like we can call it as an iterations, right? Simply we can say it as iteration. So first iteration, the lowest element should be found. What should be found? Right. What should be found? The lowest element should be found and it should be placed in 0th index. In the second iteration, the next lowest element should be found and it should be placed in first iteration, first index. Third iteration, the next lower element should be identified and it should be placed in second index, and we have to repeat the same until we get the last element. That means until we complete finding the elements of that equal to the size of the array, right? So that's why we call it as a selection sort. Here we are selecting the lowest element, we are placing it in the 0th index, and then in the remaining array of elements, we are again finding the next lowest element and we are placing that element in the next index. So we follow the same procedure. Let us see one example so that we can clearly understand. See, it's a very simple sorting technique. Let us take an example: 20, 30, 10, 50 and 40. So these are the elements and these are the index values 0, 1, 2, 3 and 4. These are the index and these are the actual elements. So in the first iteration, we have to find the lowest element among all the array elements. So among all these array elements, what is the lowest element? This one is the lowest element, right? Now this element should be replaced with index 0, that is first index, as it is a first iteration, right? So here we have to apply swap 10, 20, as 10 is the lowest element and 20 is in first position. So this is the first position, that is index 0. So our after first iteration, what is the output? 10, 30, 20. Swapping means just interchanging the elements. 50 and 40. See, now coming to the second iteration. Again find the minimum lowest element from second position to last position, because already in the first position we have placed the lowest element. So we have to search for the minimum element in second element to last element. So which one is the second one? 20. So this is the lowest element. Where should be placed? It should be placed in second position, whereas it is in second iteration, right? So we have to swap 20 and 30, as it is the second position, the element of second position, that is index 1. So after the second iteration we will get 10, swap 20, 30, 50 and 40, right? See, now again we have to find the, so these two elements are already swapped, this element is already swapped, right? So we have to find the minimum element in between these three, I mean from the third element to last element. So which one is the smaller? This one is the lowest element. So where we have to place this element? It should be placed in third position. Third position means index 2. See, here the index are 1, 0, 1, 2, 3, 4. So already that element is in index 2. So there is no change. So after the third iteration also, we will get 10, 20, 30, 50 and 40. See. So all these three elements are sorted. Now we have to find the lowest among these two. Which one is lowest? This one. Where we have to place, as it is the fourth iteration, running iteration is fourth one. So we have to place in fourth one. So swap 40, 50, because the position of 50, the index of 50 is 3. So fourth position as it is, index is. So after the fourth iteration, ten, 20, 30, 40 and 50. Now 4 elements are in a sorted order. 4 elements are in sorted order. Only a single element it is there. So obviously that element is in desired position. So this is the simple technique to sort an array elements. Right? Just we have to find the lowest element and place that lowest element in first position. Next, find the second lowest from the second position to last position. So which one is the smallest element? Consider that element and replace it with in the second position. Similarly, we have to repeat the same procedure for all the elements in an array. This is a very simple technique. So hope you understood this simple technique. So let us implement this technique using a C editor so that you can clearly understood, and then we will trace the logic with some example. Right? Right.
Friends, so hope you understood the complete procedure of the selection sort. Now let us implement that selection sort using this C editor. So let us start from header files. And as usual, let us write the main function and leave the declaration part, because after completion of the program we can write the declaration. That means we can declare the variables which we are using in this program, right? So first we need the size of an array. So let us take the size. So let us take the size in the variable n, or simply we can write it as a size. And then we have to read the elements into an array. So in order to read number of elements into an array, we require some iterative statements. So I will just write for loop from 0 less than size minus 1 and I plus plus, right? Next, we have to read the input statements. That means read the variables, array elements. For the reading purpose, we have to use the scanf ampersand e of I, right? So this is the reading of array elements. Now we have to write the logic. First let us print the array elements before sorting. So for printing the array elements, just we have to write the iterative statements I less than size minus 1, oh sorry, I less than size. So here also I have to take I less than size, so the index value will be from 0 to size minus 1. Okay, it's a little bit mistake. And then use the printf for printing the array e of I. Then now we have to write the logic for selection sort. Selection sort. So we have to iterate. I mean, we have to perform the iterations for finding the lowest element. So we have to find the iterations for each and every element. We have to compare that element with all the elements, whether the element is the lowest among all the remaining elements. So for that purpose we have to write some iterative statement. Again, in that we have to start comparison of minimum. So first, before that, let us take I value as a minimum initially. Now let us take that j is equal to I plus 1, means we are considering the first element and we are comparing that first element from the second element to the size minus 1 elements. So here min is a position. So here I is also an index value, minimum is also an index value. So this iteration, this iterative statement, this for loop is used to find the lowest element among the different elements in array. So if we have to check everything, so if a of j is less than a of minimum. So once again I am saying that here minimum is a index value. In order to get the value of at that particular position, we have to mention a of minimum. So here minimum is a position, a of minimum is a value at that particular position. So we are comparing the value at that particular position. If this condition is true, automatically the minimum value will be changed to j. So the position of j will be the minimum. So after completion of these iterations, so mainly this loop, this for loop, inner for loop is used to find the lowest element, the position of lowest element. After that, just swap that lowest element with current element. Temp is equal to a of I is equal to a of minimum, a of minimum is equal to temp. So this is for swapping the elements for the first element with the minimum element, right? Close the outer loop. Now we have to print array elements after sorting. Again same iterative statements, I is equal to 0, I less than size, I plus plus, printf. As is this, this is the only single statement, we need not mention the curly braces. Okay, percentage d tab slash t is for tab, horizontal tab. Return statement, close. So this is for reading elements into an array, right? Now let us see whether the logic is right or not. First let us save the program. Cell sort dot c, right? Compile the program. So 15 errors. So we forget to declare the variables. So let us declare the variables. Int I, j and array. We have taken array. So maximum size 10 I am taking, and then temporary variable we have taken, minimum we have taken, and a size, of course size we have taken, right? So any other variable we have used in the program? No, that's all. Then the clear screen. So all the previous outputs will be cleared. So once again I will compile. So 0 errors, right? Now let us run the program. enter the size of an array. Let us take a 5 elements. So now we have to enter the elements. Let us take 20, 10, 30, 50, 40. So let us see the output. So 20, 10, 30, 50, 40. So after sorting, 10, 20, 30, 40 and 50, right? So some statements are missing, I think. Yeah, so we didn't write anything else here. Let us write here printf before sorting. Similarly, we will write here after sorting, so that the output will be easily understood by everyone. Printf after sorting. Yes, now you can get it. So I have compiled, then run the program. Take the 5 elements. Let us take 4, 3, 5, 2 and 1. So let us check the output. So before sorting, the elements are 4, 3, 5, 2, 1, and after sorting, the elements are 1, 2, 3, 4, 5. So once again, we will take it there. Right. See, 5 elements. 5, 3, 1, 2, 4. So before sorting, the elements are 5, 3, 1, 2, 4, and after sorting, the elements are 1, 2, 3, 4, 5. So hope you understood this simple logic. So a very simple thing. So first for loop is the iterations to find the number of locations, and second for loop is used for finding the lowest element, minimum element among different elements in an array. So for example, here we have taken 5 elements in an array. So this second for loop is to find the lowest among all the 5 elements. So we have to find the position where the lowest element resides. So we have to swap that particular element to with the first. If it is a first iteration, the first position, we will place the lowest element in the first position, right? In the second iteration, the second lowest will be placed in the second position. So this is for position, and this is for finding the lowest element. Hope you understood. Now let us trace this logic with a simple example, so that all your doubts will be clarified. Okay, thank you.
Right, welcome back. So hope you understand the implementation of this selection sort. Now let us trace the logic with some example, right? So as we have seen, this is the logic we have seen while implementing the program. So let us take an example so that we can trace this logic, how the sorting will be applied, how the technique will be applied. So I am considering only 5 elements here: 20, 30, 10, 50 and 40, right? 50 and 40, right? These are the elements. So this is the index value: 0, 1, 2, 3, 4. So here n is equal to 5. See, n is equal to 5. So the index values are from 0 to 4. Now let us test this one. So first iteration. So in the first iteration, first minimum is equal to I. So here I stands from. So these are the iterations as we have discussed earlier. So these are the iterations. How many iterations? We have to use the n minus 1 iterations. So here min is equal to I. First I is equal to 0. So min is equal to I. So right here I is equal to 0. and 0 less than n 5. So the condition is true. So min is equal to I. Min is equal to I means 0. So clearly observe here. So here minimum I, both are the positions, not the elements. Here minimum is the position. So how to get the value at that particular position? A of minimum. Hope you understood, right? So minimum is equal to 0 as first I is equal to 0. Now enter into the second loop. So j is equal to I plus 1. So if you consider the first element, we have to search for the lowest element throughout the array, right? So we have to search for from second element to last element, because here already we have taken the first element as minimum. So j is equal to 1 less than 5, condition is true, if a of j, that means a of 1 is less than a of minimum, that is 0. So what are the elements of a of 1 and a of 0? A of 1 is 30 less than a of 0, 20. 30 less than 20. Condition false. Right? J will be incremented. J is equal to 2. So before it's 1, j plus plus, so it's 2 now. 2 less than n. 2 less than n means 2 less than 5. So 2 less than 5, again check the condition, a of 2 less than a of minimum. What is the value of a of 2? 10 less than a of minimum. A of minimum is 0. A of 0 means 20. 10 less than 20. The condition true. Automatically min is equal to j. Now minimum is equal to j value. What is the j value? 2. So this is very important. Right? Next, j is incremented. So till now we have traversed with 2 elements. So within the, 3 elements. Within these 3 elements, the minimum element is in second position, that is 10. Now j plus plus, j is equal to 3. 3 less than 5. The condition is true. Again check the condition, a of 3 less than a of 0. So 50 less than a of 0 is 20. 50 less than 20, condition false. Again j plus plus, j is equal to 4. 4 less than 5, the condition true. Again a of 4 less than a of minimum, that is 0. A of 4 is right 40. 40 less than 20, condition fails. Again j is equal to 5. 5 less than 5, condition false. Right? J is equal to 5, 5 less than 5, condition false. Automatically the control will come out from the loop. These statements will be executed. Now the temp is equal to a of I. So here what is the I value? 0. That means a of 0 means 20. Right? Next, a of I, a of 0 is equal to a of minimum. A of minimum, here minimum is not 0, here we have changed it to 2. A of 2, that is a of 2 value, what is the value? 10. Next, a of minimum. A of minimum means a of 2. A of 2 value, how much a of 2 value is equal to 10. So temp is 20. Right? So if you print the array, first 0th element is 10. Right? So we will so 0th element is 10 and a of 2 is equal to 20. A of 2 is equal to 20. So this is the result of selection sort after first iteration. Now after completion of this statement, again I is incremented. Right? In the second iteration I is incremented. Previously I is equal to 0, now I incremented. So see, I is incremented. Now 1, I is equal to 1, 1 less than 4, condition is true, minimum is equal to I means 1, right? J is equal to, here see, minimum is equal to 1 because in the first position, that is index 0, already we have placed the lowest number. Next, J is equal to I plus 1, J is equal to I plus 1, that is 2, 2 less than 4, condition true, A of 2 less than A of minimum 1, A of 2 value is 20 less than A of 1, 30, condition true. So minimum is equal to J, here J value is 2. Hope you understood. J is equal to 2, 2 less than 4, condition is true. So the control will enter into the loop, and again the control will check the condition A of J, here J is equal to 2, so A of 2 less than A of minimum, here minimum is 1, so less than A of minimum, 20 is less than 30, condition true. So minimum is equal to J, so minimum is equal to, here J value is 2, so the position is 2. So till now the lowest element is in position 2. Next, after completion of this statement, again J will be incremented. So J is equal to 3 and 3 less than 4. Again the condition is true. So A of 3 less than A of 1. A of 3 is 50 less than A of 1, 30. Condition false. So the control will not enter into this condition, right? Again J is incremented. So J is equal to 4. 4 less than, sorry, here 5, okay, here 5, n is equal to 5, right? So 3 less than 5 and 4 less than 5, condition is true. Again A of 4 less than A of 1, so A of 4 value is 40 less than 30, condition is false. So again J will be incremented, J is equal to 5, 5 less than 5, condition fails. So automatically the control will come out from this inner for loop. So temp is equal to A of 1, A of I, temp is equal to A of I. So A of I means here I value is 1, so A of 1, A of 1 value is 30, so 30 will be saved in temp. Next, A of I, that is A of 1 is equal to A of minimum. A of minimum, here minimum value is 2. So A of 2 is 20. Next, A of minimum, A of 2 is equal to temp. So what is the value of temp? 30. 30 will be initialized to A of 2. Now, update the array. So A of 0, 10, A of 1, we place it 20, A of 2, we place it 30. So after the second iteration, this is the second iteration, right? This is the second iteration. After the second iteration, the first two elements are in a sorted order. Again, coming to the third iteration, let us check the third iteration. So we have to check all the elements and find the lowest element among them. Third iteration. So in the third iteration, now again I is incremented. So after completion of this one, I will be incremented. Now I is equal to 2. So in the previous iteration, I is equal to 1. Now I is equal to 2. So 2 less than 5. Condition true. Automatically min is equal to I. So min is equal to 2. The minimum element is 2. Then J is equal to I plus 1. J is equal to 3. I plus 1. I is equal to 2. So 3. 3 less than 5. Condition true. Enter into the loop. A of J, A of 3 less than A of minimum, A of 2. So A of 3 is 50 less than 30. Condition false. 50 less than 30. So the control will never execute this statement. Next, again J is incremented. Now J is equal to 4. So 4 less than 5. condition true. So a of 4 less than a of 2. So 40 less than 30. Less than 30. Again the condition is false. Now again j is incremented. Now j is equal to 5. 5 less than 5. Condition fails. So condition fails, automatically this statement will be executed. So temp is equal to a of I. So a of I, here I is 2. So a of 2 is 30. And then a of 2 is equal to a of minimum. So here minimum is again 2. So obviously it will be 30. No change. A of minimum means 2 is equal to temp. Temp is again 30. So there will be no change in array of elements in the third iteration. So as it is. Again, after completion of the third element, the three elements are in a sorted order. First, next we have to go for the fourth element. The element of fourth position, right? Now, coming to the fourth iteration. So I will be incremented to 3. 3 less than 5. Condition is true. Minimum is equal to I, that is 3. Then j is equal to I plus 1, 4. 4 less than 5, it's a true. A of 4 less than A of 3. A of 4 element is 40. 40 less than 50. Condition true. Right? Condition is true. Now, this statement will be executed. Now, minimum is equal to j value, sit 4. Minimum element is equal to 4. Previously, minimum is equal to 3. Here the condition is true, so minimum is equal to 4. Then, again j incremented. J is equal to 5. 5 less than 5. Fail. Come out from the loop. This one. Temp is equal to A of I. So 3. So what is the third value? 50. Next. A of I 3 is equal to A of minimum. Minimum is 4. Minimum is 4. So what is the A of 4? 40. 40 will be saved in A of 3. Next. A of 4 value is equal to 10. So what is the value of 10? 50. Now update the array. Third position, A of 3, it's a 40. A of 4, it's a 50. Right? So again, I is incremented in the fifth iteration. I is incremented in the fifth iteration. Now I is equal to 4. 4 less than 5. Condition is true. Minimum is equal to I. Minimum is equal to 4. Next, j is equal to 5. J is equal to 5. Right? 5 less than 5. Condition fails. So the control will never enter into this loop. Automatically this statement will be executed. So temp is equal to A of I. A of I means here I value, what is I value? A of 4, which is 50. Next, A of I, A of 4 is equal to A of minimum. Minimum is again 4, which is equal to 50. A of minimum 4 is equal to 10, which is a 50. That is no change. No change in fifth iteration. So 50 will be placed in fourth position itself. Again, after this one, the sixth iteration, after completion of this thing, again I is incremented. Now previously I is equal to 4, now I is equal to 5. 5 less than 5. Here the condition fails. Automatically the control will come out from the outer loop. So total 5 iterations. We have done a total 5 iterations. So in every iteration we are finding the lowest element and desired location of that particular element. So after every iteration we are sorting each element. So this is a very simple and easy procedure for sorting the elements. So in this session let us have a look on one more sorting technique, that is merge sort. So let us see the procedure of merge sort. So this merge sort works with divide and conquer rule. Divide and conquer. Divide and conquer. So divide and conquer means in case of large problems, we will divide that large problems into sub problems, and those sub problems will be solved, and all the solutions of sub problems will be combined to get the actual solution. So that is the process of divide and conquer. Now let us see the procedure, how we will how we will sort the unordered elements. So the input is, as usual, unordered elements, and output is ordered elements. So preferably it's an ascending order. Ascending order, right? So let us take some elements and let us see the procedure. Now see, let us take some elements. 40, 60, 30, 50, 10, 20. So these are the elements, right? So we have to sort by using this merge sort. See, first let us take the lower value, let us take here the high value, the index, right? So these are the indexes. So this is the index, this one is the element. So low is having the 0 index, high is having the 5 index. 5. Now first calculate the middle element. So mid is equal to low plus high by 2, right? So low plus high by 2. So here the mid is equal to, low is 0 plus high is 5 by 2, that is 2. Always consider the floor division. Floor division. Always consider the floor division, right? So this is the result, middle value. Now divide the complete elements from low to mid and mid plus 1 to high. So low to mid and mid plus 1 to high. So let us divide the complete elements into two parts. See, so 40, 60, so low to mid means 0, 1, mid here, mid is 2, so 30. So this is the first subpart, and the remaining 50, 10, 20. So this is the second part, right? Now consider this part, again consider here the low, consider here high, find out the mid. So here 0, 1 and 2, these are the indexes, right? 0 plus 1 by 2, that means 0 plus 1 by 2, it gives 0. floor division, right? It is a floor division, right? So again divide it into low to mid, mid plus 1 to high. So 40, 60 and 30. Similarly here also, it's a low, it's a high, mid is equal to 0. So 0, 1 and 2. Sorry. So 0 plus 2 by 2, that is, here we are getting 1. So 40, 60 will be in one part, 30 will be in another part. Here also 1, so 50, 10 will be in one part and 20 will be in another part, right? So low plus high, 0 plus 2 by 2, right? Sorry for the inconvenience. Now again repeat the same procedure. Let us take low, let us take high, right? So mid is equal to 0. So 40 will be the one part, 60 will be one part, 30 will be one part, and here also low, high, mid is equal to 0. So 50 will be one part, 10 will be another part, 20 will be another part. Right? So here in this step we have divided the complete elements into sub elements. Right? So this is the divide part. All this process is the divide part. So we have divided the complex problem into small problems. Now we have to conquer them by merging each and every element. We have to compare the elements and we have to perform the merging. Right. So I will just erase all these things. So hope you understood this one. Just low, high, find out the mid, divide the group of elements into two groups. Again apply the same procedure for each group. Again from each group, low and high, calculate the mid, divide the elements into two groups, right? Until we get the individual elements. Now compare these two elements. Compare these two elements, 40 and 60. So 40 and 60. So 40 is less than 60. So 40 should be on left hand side of 60. Right? So as we know that if you consider some 10, less than 10 will be on the left hand side, greater than 10 will be on the right hand side. Right? So if the elements are in sorted order, if you consider the element 10, so the element which are less than 10 will be on the left hand side, which are greater than 10 will be on the right hand side. So similarly here also let us consider 60 and 40. So 40 is less than 60, 40 should be on the left hand side of 60. So here always, here already they are in sorted order. So sort these elements and form one group. Right? So here 40, 60 are in sorted order. Now apply the same 50 and 10. So if you observe here 50 and 10, so 50 is greater than 10, so 50 should be on right hand side of the 10. Right? Now swap these two and form the sorted order. So 10 comma 50. 10 comma 50. Now sort these two groups. So 40, 60 and 30. 10, 50 and 20. Now sort out. So let us take here a loop variable I and here the loop variable j. Now compare 40 with 30. 40 with 30. So consider another group, that means a single group. So 40 and 30. So 30 is less than 40. Now just insert 30 here and increment j. So here 30 is the last element. Directly we can write this second group as it is into the single group, because this group is already in sorted order. Just write down the elements 30, 40, 60. 30, 40, 60. Similarly, apply here. So take one more group. So 10, 50, 20. Take I as 10, J as 20, 10 and 20. So 10 is less than 20, 10 will be moved to the group and I will be incremented. Now I will be here. Right? So 50, 20. 20 is less than 50. So 20 will be moved and J will be incremented. But here there is only one element in J. Directly the remaining elements will be moved to the single group. So 10, 20 and 50. Right? Now, so I will erase this thing. So we had only two group of elements and each group is having the sorted elements. So if you observe here, only two groups are there and already these groups are all in sorted order. So 30, 40, 60, those are sorted order. 10, 20, 50, those are in sorted order. Now, take a single group, right? Now, consider I here, J here, right? 30 and 10, both are compared. So, which one is lower? 10 is lower. So, 10 is moved to the single group and J will be incremented. So, J will be pointed to the second position. Now, again 30 and 20. Again 20 is lower. So, directly 20 will be moved to the single group and J will be incremented. And I remain same, right? So, whatever the element in which group is inserted into the single group, that particular loop variable will be incremented. Now, J points at the 50. So, now 50. So, 50 and 30 is compared. So, 30 is less than 50. So, 30 will be moved to the single group and I will be incremented here. Now, I is at the 40, position 40. So, 40 and 50. Again, 40 is less than 50. So, 40 will be moved and I will be again incremented with 1. So, I is pointing to 60, J is pointing to 50. Now, again compare 60 and 50. So, here 50 is lower than 60. So, 50 will be removed and 50 will be moved to the single group and J will be incremented as the 50 is the last element. So, directly the remaining elements of this remaining group will be directly moved to the single. Right? So, here if you observe, here we got all the elements in a sorted order 10, 20, 30, 40, 50 and 60. So, this process we call it as conquer, divide and conquer. So, divide until we get the list elements and just compare and swap from the bottom to top. That's we call it as a conquer method, right? This is how we have to implement the merge sort. So, hope you understood this simple merge sort. So, this majorly this will follow the divide and conquer method. Now, in this session, let us have a look on one more sorting technique, that is heap sort. So, in order to implement this heap sort, we have to follow two properties. One is we have to draw the tree that must be a complete binary tree. Another one is it should follow the heap order. It should follow the heap order. This heap order means, again, we can have two ways, that is max heap and min heap. So, what is meant by a max heap? So, first of all, what is meant by a complete binary tree? Complete binary tree. So, here we have to follow, that means we have to insert the elements First one as root, left, and then right. First thing, we have to follow the same order. Second one, so every element, every node should have two childs except the last level. Except the last level. So in every level, each node should have two children. Right? So if it satisfies these two conditions, we can call it as a complete binary tree. Next, max heap. What is meant by max heap? Here, the parent node should be greater than children, right? Then delete and replace root node with the least child. Right? We have to follow these two things in order to max heap. So parent node should be greater than the children nodes. Next, then delete and replace the root node with the least child node. Next, here the quite opposite. Parent node should be less than child nodes. Delete and replace root node the least or last, right? Last child node. So let us consider it as a last child node, right? So this will be happen, and here deleted node will be placed at last position. Right? Here also same. Deleted node will be placed at last position. Right? So these are about the complete binary tree and a heap order. Right? So complete binary tree means we have to follow while inserting the elements, that is root, left, right, and every node should have two children except the last level. And max heap, the heap order is max heap and min heap. Coming to the max heap, the parent node should be greater than the children node, and after achieving this one, delete and replace the root node with the last node, and the deleted node will be placed at the last position in the array. Right? Here also in the min heap, the quite opposite to the max heap, that means the parent node should be less than the child nodes, and delete and replace the root node with the last child node, and the deleted node will be placed at the last position in the array. So let us write in array. In array. Right? So we have to follow all these things while performing the heap sort. So let us take some elements and perform the heap sort. So let us take some elements. Let it be 40, 60, 30, 10, 20, 50. So let it be, these are the elements we are considering, and we need to get the output as 10, 20, 30, 40, 50, 60. So first let us draw the tree. So let us take root node, left node, right node, again left node, right node, left node. So this is a complete binary tree because except the last level, so there are two levels, level 1 and 2, except the last level, that means second level, every level is having two children, right? See, this we call it as a leaf node. Now this is a complete binary tree. Okay, now we have to apply the max heap. This is a complete binary tree. So max heap means we have to check whether the parent node is greater than the children's coming from the bottom. See, coming to this left child, 10, 20 and 60. So here 60 is the parent for 10 and 20, where 60 is greater than 10 and 20, so no change will be occurred. Coming to the right tree, 30 and 50. So here the children is having the 50, child is having the 50 node and the parent is having the 30 node. Here 30 is less than 50. So we have to swap these two elements. Now let us write here 40, 60, 50, 10, 20, 30. Right? Now again go to the upward. So 40 is the parent for both 60 and 50. So here 60 is greater than 40. So child is having the greater element than the root. So just swap these two. So 60, 40, 50, 10, 20, 30. So if you observe here, so this is the max heap. This is the max heap because every parent element is a greater than the child elements. So here 40 is greater than its child's 10 and 20. So 50 is greater than its child 30 and 60 is greater than its child 40 and 50. Now write down the elements in an array. So 60, 40, 50, 10, 20, 30. So these are the elements. Now after achieving the max heap, what we have to do? The maximum element, I mean the root element, should be deleted and it must be replaced with the last element. So this must be replaced with the last element. So here we have to apply the swap, right? And place the root element at the last position. So 60 here, 30 here, 40, 50, 10, 20. Right? Now consider this one, 30, 40, 50. Draw the tree. So 30, follow the binary search tree, 30, 40, left, right, again left, again right. Right? Now consider the max heap. This is not a max heap. Is it a max heap? See, 40 is a parent of 10 and 20, which is greater than 10 and 20, right? Next, 50, it's having no children elements. So go to the top level. 30 is a parent for both 40 and 50, where 50 is greater than 30. So child element is having the greater value than parent. So swap. So this will be written as 50, 40, 30, 10, 20, right? So this is in a maxi. This is in a maxi because the parent element is having greater value than the child elements. Now, right here, so here already this element is in a sorted order. See, right here 50, 40, 30, 10, 20 and 60. Right? So here the root element should be replaced with the last element. So last element is 20 here. Right? So this will be swap. Sorry, it has been swapped. So 20, 40, 30, 10, 50 and 60. See here the two elements are in a sorted order. The two elements are in sorted order, right? Now draw the tree for this one. So root element is 20, left element is 40, right element is 30, left element is 10. So is it in a maxim? See, here the 40 is a parent node, 10 is a child node, 40 is greater than 10, this level it is right. So 30 is the parent node, it doesn't have any children, so it is right. Coming to the first level, 20 is the parent node for 40 and 30, where 40 is greater than 20. So swap here. So 40, 20, 30, 10. Right? So if you observe here again, see 20 is greater than 10, it is right. 30 is a parent node which is having 0 children, so it is right. At the top level 40 is the parent for 20 and 30, where 40 is a greater than. So this is in maxim. Now replace this 40 with the last element and move this 40 to the last but third position. So write down the elements 40, 20, 30, 10, 50, 60. Already these 50, 60 are in sorted order. Swap this 40 with 10, so that we will get 10, 20, 30, 40, 50 and 60. So if you observe here, the three elements, the last three elements are in sorted order. Now draw the graph. Draw the graph for these three elements. So root element is 10, left element is 20, right element is 30. So is it in maxim? See, 10 is a parent for both 20 and 30, where 30 is a greater element which is in a child position. So swap this one. So 30, the left element will be 20 and 10. Now write down here 30, 20, 10, right, 40, 50 and 60. So already 40, 50, 60 are in sorted order. Right? Now replace this last element, I mean the root node, with last element. So here last element is 10. So we will get 10. So here we have to swap this one. Swap this one. So 10, 20, 30, 40, 50 and 60. So last 4 elements are in sorted order. Right? Replace this one. Now draw the tree for these two. So root node is 10, child node is 20. So it is also a binary tree because it's the last level. So 20 here 10 is parent and 20 is child, where 20 is greater than 10. So we have to apply swap. So this will be redrawn like 20 and left child is 10. Now replace the last element, the greater element. So here we can write here. So 20, I will write here. So 20, 10, 30, 40, 50 and 60. So already all these elements are in sorted order. So 20 and 10. So just swap, because the last, the root node should be replaced with the last element and it should be placed in the array, in the last position of the array, right? So 10, 20, 30, 40, 50 and 60. So all these are in sorted order, and write down the tree. Only 10 will be there. This is a root node. Place this in array so that we will get 10, 20, 30, 40, 50 and 60, where the elements are in sorted order. So we can get all these things. So this is the first step, this is the second step, this is the third step, this is the fourth one, and this is the fifth one, and this is the sixth one. Right? So this is the first one, this is the second, this is the third, this is the fourth, this is the fifth, and finally this is the sixth. So hope you understood. So we have to follow the two properties, that is, first one, we have to draw the tree such that the complete binary tree, it should satisfy the complete binary tree. And second one is we have to follow the heap order, that is min heap or max heap. If we consider the max heap, the resultant will be the elements in ascending order. If you consider the min heap, the elements will be in descending order. So max heap and min heap difference we have seen, that is the parent element should be greater than its child elements when we consider the max heap. Min heap, the parent element should be less than the children elements. And after achieving the max heap, we have to replace the root node with the last node and insert this root node into the array at the last position. Right? So for every iteration, the last element, the highest element will be sorted. So here we have seen the example and the working of heap sort. And today's session we will go with another sorting mechanism, that is called a quick sort. So this sorting mechanism will follow the divide and conquer method. Divide and conquer. So the name itself indicates. So divide and conquer means first the complex problem is divided into sub-problems and each sub-problem will be implemented. So like that, here also the complete large elements will be divided into different partitions and each partition will be applied for sorting technique. So each partition will be implemented by using the recursive methods. Okay. Next, so let us see the procedure first and then we will go with the example. Then first step, here we have to select the pivot and we have to find the position of the pivot element. So here we will go with the pivot element, right? So first we have to find the position of a pivot. Such that all the elements which are left towards this pivot are less than the pivot element and whatever the elements which are on right side to this position are greater than a pivot, right? So this position, first we have to find this position, then consider this as one partition, consider this as another partition. So see, this is less than pivot, this is a greater than pivot, don't get confused, okay? This is a less than symbol and a greater than symbol, okay? So less than pivot is one partition, greater than pivot is another partition. So recursively call the same procedure for this partition. Again consider a pivot and find the position of the pivot for this partition, and again divide that into two positions, right? So like this we have to find this quicksort. First, this pivot can be considered as the pivot element can be considered as first element, middle element, last element, right? So we can consider any element as a pivot element, and based upon that pivot element we have to find the position of that particular pivot element, right? For example, if the numbers are 10, 50, 40, 10, 30 and 20, this element can be considered as a pivot, or this element can be considered as a pivot, or this element can be considered as a pivot. So after considering the element as a pivot, we have to find the position of that particular pivot point such that all the elements which are less than pivot should be on the left hand side, and all the elements which are greater than the pivot should be arranged on right hand side. So in such a way we have to find the position of the pivot. First we have to consider the pivot element. What is the pivot element, right? So in our example we will consider this one, first one. So let us consider the first element as a pivot and find the pivot position. See, first consider first element as a pivot. Consider the first element as a pivot. Next, initialize I to low index, j to high index. That means the starting element, j is the last element. Next, we have to repeat the procedure. Repeat the following steps. Until I less than j. So until I becomes until I less than j, until the condition is true, we have to repeat the following procedure. So first, keep on incrementing I while A of I is less than or equal to pivot. So unless this condition becomes false, we have to keep on incrementing the I value, right? Next, similarly, keep on decrementing the j while A of j is greater than pivot. So similarly, from the starting we have to incrementing the I towards the right, and we have to decrementing the j towards the left. Okay, so while incrementing and decrementing I and j values, we have to check these conditions, whether a of I is less than or equal to pivot, and whether the a of j is greater than pivot, right? Next, so if this two condition fails, if these two at some condition, this condition, I mean at some point this condition will be failed, so we have to stop incrementing the I. At some element, this condition will be false, so we have to stop decrementing the j. Now check the condition. If I is less than j, I is less than j, yes, then if it is true, then swap the elements a of I comma a of j, a of I comma a of j. So we have to swap the elements of I value, the elements which are available in ith index and jth index. Next, if this becomes false, I less than j. So if I is greater than j, the index value of I is greater than j, then also we have to swap a of j element with the pivot, so that, this is nothing but, this is nothing but a of low, because here the pivot is the first element, right? Pivot is the first element. So we have to change the swap between the jth element and pivot value. So here j is the position of pivot. So this is very important thing, right? J is the position of a pivot, so that all the elements which are less than pivot are on the left hand side, and all the elements which are greater than the pivot will be on right hand side. So here, after completion of this one, the pivot value will be fixed. The pivot position is fixed, right? Not the pivot value, pivot position will be fixed, right? So we are supposed to find that position of a pivot. Now divide the two partitions. So one is after getting the pivot value, right? So this is one partition and this is another partition. So this is 0 to p minus 1, and here p to high, p plus 1 to high. Okay, p plus 1 to high. Instead of writing 0, we will write a low, right? Low to p minus 1. So this is one partition, this is another partition. So consider this partition, and here also consider repeat the same process. So recursively repeat the same process. Consider this partition as an array of elements. Now consider the pivot, first element as a pivot, and starting I to low index and j to high index. So I will be low, j will be p minus 1, and then repeat the following steps until I less than j. So keep on incrementing I while ia of I is less than or equal to pivot, and then keep on decrementing the j while a of j is greater than pivot, right? Then if I is less than j, the index values of I is less than j, then simply swap the positions of I and j, the elements which are at positions of I and j. Then if I is greater than j, the index value of I is greater than the index value of j, then simply swap the low value with the a of j, that means of the value present at the position j. So here a of low means nothing but a pivot value, because in the first step we are considering the first element as a pivot. So here again the pivot, the position j is the position of pivot. So position, when the pivot position is fixed, so that all the elements of which are less than pivot will be on left hand side, and all the elements which are greater than pivot are available in the right hand side, and again do the partitions and again repeat the same process, right? So this is how we will implement, we are going to implement this quick sort, right? So based upon this algorithm, let us solve an example so that your doubts will be clarified. So our aim is to find the position of a pivot, and we will implement the same thing recursively for all the partitions. So once the pivot is fixed, then we have to divide it into partitions, and considering each partition, and we have to repeat the same. Okay. Example. Let us take some elements. Consider these elements. Okay. See, so these are the elements of an array. So this is array elements. These are the indexes. This is the I value. This is the j value. I value, j value. Okay, right. Then consider this as a pivot. Consider this element as a pivot. Now repeat the process. So first step, consider the pivot as a first element. So we have considered this one, and next I is initialized to low and j is initialized to high. So I less than j, that is here 0 less than 5. The condition is true. So this condition is true. We have to repeat the process. So what we have to repeat? We have to keep on incrementing I until a of I is less than or equal to pivot. So a of I less than or equal to pivot. See this condition I plus plus. We have to repeat the same process. Okay. So here see first 30 less than or equal to 30. So I plus plus. So that means 1 it will be. Next 20 less than or equal to 30. I plus plus 2. Right. Next 10 less than or equal to 30. I plus plus 3. Index value 3. So 50 less than or equal to 30. So fails. Okay. Fail. Here the fail. Condition fails. Now here at what condition it is failing? I is equal to 3. So I is equal to 3. Right? Condition I is equal to 3 fails. So after completion of this one, I is pointing at here. Okay. Now keep on decrementing the j value. So a of j is greater than pivot if I j minus minus. So repeat this process. So a of j is nothing but a high value, high value 5. So 40 greater than or equal to greater than 30, j minus minus, so it will be 4. Next 60 greater than 30, j minus minus, it's again 3. After decrementing it will be 3. Next 50 greater than 30, again j minus minus 2. Next 10 greater than 30 fails. So at where it fails, j is equal to 2, right? So at some condition, at some element, both the condition will be fails. Now we have to check whether I is less than or j. So what is the, see, if I less than j, then swap a of I element with a of j element, right? Else we have to change swap a of j element with pivot, right? Now let us check the condition here. So I less than j, so 3 less than 2, I less than j, 3 less than 2, which is false, right? So we have to swap a of j. A of j means, see, j is 2, a of 2 comma pivot. What's the pivot? 30, or a of low, okay, a of 0, because here the pivot is a of 0, right? So swapping j position is pivot. So what is the j position? 2. Second position is a pivot element. Second position is the pivot element for the first thing. So after getting this one, see, just swap the positions a of 2 comma a of 0. A of 2 means 10. So 10 will be here, 20, then 30, then 50, 60 and a 40. See, 0, 1, 2, 3, 4 and 5. So second position is a pivot. Second position is a pivot, right? So here if you observe, all the elements which are on the left hand side of the pivot are less than this pivot, 10 and 20. So it may be in a sorted order, or it may not be in a sorted order, right? So whatever the elements which are on the right hand side of the pivot are greater than the pivot elements, right? So this may be in a sorted order and this may not be in a sorted order. So this is the partition 1, this is the partition 2, right? So now we have to consider, so this position is fixed, right? Pivot position is fixed. So we have to take care about the partition 1 and partition 2, excluding this pivot position. So that's why we are writing from 0 to low to p minus 1, and here p plus 1 to high. So we are not considering the pivot position because it's already fixed. So hope you understood this one. So after the first iteration, first recursion, this is the elements. Now let us write these elements, okay? I will write down here. So 10, 20, 30, 50, 60 and 40. Right. So I will erase all these things. So first recursion, this is about the first recursion. Now so this is the pivot element, okay, fixed. So this will be the partition 1 and this will be the partition 2, right? So let us consider these partitions. So 10 and 20, 0th index, first index. So obviously this will be I, this will be J, and also pivot. We know that we are considering the pivot as a first element, so this one. So what we have to check? We have to repeat until I is less than j. Here it is 0 less than 1, condition true. Then keep on incrementing. So a of I is less than or equal to pivot I plus plus. So for this we have to go with this. So 10 less than or equal to 10 I plus plus, that will be 1, and a 20 less than or equal to 10, okay, so false. So I is equal to 1. Oh, sorry. Right. I is equal to 1. So I value is changed from here to here. Okay. Next, A of j greater than pivot. We have to keep on decrementing the j value. We have to keep on decrementing the j value. So 20 is greater than or equal. 20 is greater than 10. J minus minus. Right? J minus minus, and the value will be 0 now because initially j is equal to 1. And 10 is greater than 20, which is a false. So j is equal to 0. See, at I is equal to 1, the condition fails. At j is equal to 0, condition fails. Here, if you observe, I is less than j, then what we have to do? Swap A of I comma A of j. Else, we can write the condition. Okay, I greater than j, then swap A of j comma pivot. Right? Pivot. Right? So here we can observe here at what positions the condition fails. I is equal to 1 and j is equal to 0. So 1 less than 0. The condition is false. So this will be happened. So swap A of j means 0 comma pivot. Here pivot means again A of low. So that implies so both the j position, both the j value and a pivot are at the same position, so we need not swap anything, right? So already those are in sorted order. That means these are in a sorted order because we need not swap any element. Okay, only two elements are there. We need not swap any element. So this will be the pivot position. Okay, so here see, j position is a pivot position, isn't it? Right. What is the j position? 0. So 0th is a pivot position. If 0th is a pivot position, see, left hand side we are not having any elements. Right hand side we are having only one element which is also greater than 10. So it implies this partition is already in sorted order. Right. Next. Hope you understood. Next we will go with the partition 2. We will go with the partition 2. So this is already in sorted order. Now we will repeat the same process with the partition 2. So 50, 60 and 40. So 0, 1 and 2. So this is the I value, this is the j value. Okay, this is the I value, this is the j value, and this is the pivot. Right. So continue the process. So I less than j, that is 0 less than 2. So this condition true. Then A of I less than or equal to pivot I plus plus. So keep on doing all these things. So A of I, that means a 50 less than or equal to 50 I plus plus, that means I becomes 1, initially 0. Next 60 less than or equal to 50 fail at I is equal to 1. At I is equal to 1 it fails. So now I becomes here. Then similarly A of j is greater than pivot j minus minus. So repeat this process. So j value is a 40, 40 greater than a 50, 40 greater than 50. Condition false. So at j is equal to 0 position. At j, at j is equal to 2. At j is equal to 2, the condition fails. Okay. Then see, if you observe here, check the condition I greater than j. Here I is 1 greater than 2, I greater than j. It is a false. So swap, sorry, I'm extremely sorry, I less than j. So if I is less than j, we have to swap the elements a of I and a of j. If I is greater than j, then we have to swap the elements a of j and pivot. So here the first condition, I is less than j, I value is 1, j value is 2, so I is less than j. So swap a of I comma a of j. So what are the elements we have to swap? Swap the 60 and 40. So the elements will be, after the iteration, the elements will be 50, 40, 60. 50, 40, 60. The positions of I and j are same. Okay. So the index values 0, 1 and 2, and this is the pivot we are considering. Right. So after swapping 60 and 40, we will get this one. Okay. Now again repeat the same process. So a of I is less than or equal to pivot. So I plus plus, consider this one, a of I, that means a 40 less than or equal to 50, I plus plus, which becomes 2. Similarly 60 less than or equal to 50, fail at I is equal to 2, right? At I is equal to 2, it fails. Now I and j are positioning at the same point. I and j are positioning at the same point. Similarly, a of j is greater than pivot, then simply decrement the j. Repeat the process. So 60 greater than or equal to 50, not equal, greater than 50, j minus minus, which becomes 1. Similarly 40 greater than 50, which fails at position j is equal to 1. Now j is positioned at 1, right? Now check the condition. So if I is less than j, then swap a of I comma a of j. Just a minute. Else swap a of j comma pivot. Right. Now here I is 2, j is 1, 2 less than 1, false. So we have to swap, false condition, swap a of j comma pivot, which is nothing but swap a of j means a of 1 40 comma a of pivot 50, and we know that j is pivot. J is pivot, that means 1 is pivot here. Okay, so here 1 is pivot. So after completion of this, okay, after completion of this, so I will erase this one. Okay, right. So here j is a pivot. J is pivot. Here what is the value of j? 1. So 1 is a pivot position. 1 is pivot position. So we have to swap. After swapping 40 comma 50, the elements are 40, 50 and 60. The positions 0, 1, 2, the position, this is the pivot position. So left hand side of the pivot is having the values less than pivot, and the right side of the pivot position are having the elements greater than pivot. So here again this is the one partition, this is the another partition. So here the partition is having only one value, so need not apply the sorting technique, and here also the partition is having only one value, here also we need not apply the sorting technique. So finally, after completion of all these things, we can simply have 40, 50 and 60. Okay, so this is a procedure we are supposed to apply. So hope you all you understood this one, right? After the first iteration, 2 is a pivot, so that 2 partitions are there. First partition, again 0 is the pivot. Second partition, 1 is a pivot. 1 means the position 1, index 1. Okay, index 0 and index 1. Right? So hope you understood this one, the quicksort algorithm, how it apply for this, how we are dividing the complete elements into different partitions, and how we are applying the recursive functions. Right? So simple thing. So first we have to consider the pivot element, and first to find out the position of that particular pivot element, and then based upon that particular pivot element we have to divide it into the partitions and recursively apply the same procedure. Today's session will go with the one more sorting techniques, that is a radix sort or a bucket sort. Radix or bucket sort. Right. So here, before going to the procedure, so first it will work with the number of digits in a given number. Right. So the sorting means just we will consider a lot of numbers, and in that numbers we have to arrange them in ascending order. That means lower value to higher value. So first we have to find the largest number, and then we have to find the number of digits in that largest number, and that many times we have to repeat the procedure. Right. Now see, the first step is find the largest number. Find the largest number. Second step, find the number of digits of large number. Okay, number of digits in large number. Then we have to repeat the number of digit times, right? So, or consider the buckets from 0 to 9. So consider the buckets from 0 to 9, because any number can be in terms of zeros 0 to 9, in between the range 0 to 9. For example, if you consider 123, so this is a 1 digit, this is the another digit, this is another digit, right? So 3 digits are there, and first digit will be in between 0 to 9, second digit will be from 0 to 9, and similarly the third digit also will be in between 0 to 9. So that's why we have to consider 9 buckets. 9 buckets. So bucket representation just like a stack representation. Okay, this is called a bucket. Just assume it, just like our stack. Okay, now starting from one's position, place the numbers in corresponding bucket. So for example, if it is 123 and let it be 456. So the ones position, this is the ones position, we know that, right? So least significant bit is a ones position. So it is a 3. Ones position, it is a 3. So this should be moved to 3 bucket, and this should be moved to 6 bucket. Bucket number 6, bucket number 3, right? So like this, we have to move all the elements into corresponding bucket based upon their ones position, right? Next, repeat step 4 for all the positions of given numbers. So we have to continue the same process for all the positions. So first we have to consider the ones position, next we have to consider the tens position, next we have to consider the hundreds position, next thousands position. So likewise, until you complete this number of digits, so we have to repeat the same process, right? Okay, right? So before applying this one, see, before applying this one, okay, after placing these these numbers into buckets, arrange the elements or numbers from left to right from all buckets. From all buckets, right? So after arranging or after moving the numbers, complete numbers into the corresponding buckets, then arrange the numbers from left to the right from all the buckets. So repeat step 4 and 5 for all the positions of a given number. So don't get confused. If you are having any doubts, let us solve an example so that everything will be clear, right? So without any delay, we will move with the example so that your doubts will be clarified. See, it's a very simple technique. So first we have to find the large number, then we have to find the number of digits for a large number. And see, this is a bucket representation. We have to consider 0 to 9 because any digit can be in between 0 to 9. Right. See, let us take an example. Let us take an example. Okay. So consider the elements 123, 45, some 67, some 456, some 3000, right? Some 3500, okay? 2200. So let us take these elements. So we are supposed to sort these elements. Now find the largest element. In this large element is 3500. Large element is 3500. So number of digits is 1, 2, 3, 4. That means ones position, tens, hundreds and thousands. So we have to repeat the process 4 times. So first, in the first recursion, that is ones position. Okay, in the ones position. So let us take the buckets. See, let us take the buckets. So this is a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the buckets. So based upon the ones position, because this is a ones position, right? See, I will write here. Ones position. Based upon the ones position, move that particular element into the corresponding bucket. So consider this one. the ones position is 3. So this element should be moved to third bucket. So 123, right? Next, 5 is at ones position, right? So fifth bucket, we have to move the 45 into fifth bucket, right? Next, 67. So 7 is the ones position. So move this to seventh bucket. Next, 456. So 6 is the last one. So ones position sixth. Right? Move to the sixth bucket. So 456. Next, 0. 0. So 0 is the first one. So ones position is 0. So we have to move this to zeroth bucket. Next, again we are having some 0. Again we are having some 0. Okay. Let us take this one more. Okay. Again we are having 0. So again place this number in the corresponding bucket. Even though there is one element in that bucket, just to follow the stack procedure. So top of the stack, it should be placed at top of the stack. So 3500. Okay. Then give the numbering. So while removing, follow the queue. While removing, follow the queue. That means first come, first serve. First in, first out. First in, first out. So in these two elements, which one is came first? 3000. So give an index value 0, give an index value 1. Here only one element, so give the index value 0. Here 0, here the 0, here also 0. Right. Again, so we missed the last element. So see the last element 2222, where one's position is 2, place it in second bucket. Okay, here also 0. Now after placing these elements into these buckets, now arrange the elements from left to right. So from left to right we have to arrange the elements. So what is the element here? First we have to start from 0th index. So 3000, next 3500, next see 2000, next 123, next 45, next 456, next 67. So after completion of one's position, the result is this one. Okay, after completion of one's position, the result will be this one. Now, so how many digits are there? 4 digits. So we have to perform like this for 4 digits. So this is the least significant bit. Now come with tens position. Now come with tens position. Similarly, consider 10 buckets. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Right. So now follow the same procedure for tens position. So we have completed for ones position. Now we have to complete for tens position. See here the tens position is this one 0. So 3000 is placed here. Okay. Next the tens position is 0. Again place here. So index 0, index 1. Next tens position 2. So place in the 2 bucket. Next again 2. Place here itself. Again index 0, index 1. 45. So 4. So right here 45. Next 5. So place in the 5th bucket. 456. Here 6. So 67 is placed in 6th bucket. Okay. So here only one thing. So index values will be 0 itself. Right. So this is how we have to place the elements into the corresponding buckets based upon the tens position. So previously ones position, now tens position. Now arrange the elements from the left to right. So based upon the index 3000, 3500, 2222, 123 and 45, 456 and 67. So this is the output after applying the tens position. After applying the tens position, right? So we should not stop here because only two digits we have completed. There are 4 digits, right? Total maximum is 4 digits. So we have to go with the third digit. Third digit means hundreds position. Hundreds position. Okay. So we will go with the hundreds position. Right. So we will erase this one. So what's the input? 3000, 3500, 2222, it's 123, it's a 45, so 456 and 67. So this is the output for second 10th position. Now from this we have to consider the third digit. Third digit means hundreds position. Hundreds position means third one, right? So 0, so 3000 is placed here. Next 5, so place in fifth bucket, 3500. 2, place into second bucket. Okay. Next again 2, place here. So here only 2 digits. Third digit will be 0. So place here. 4, place in the fourth bucket. Here again third digit is 0. So again place here. 67. Right? Hope you understood this one. Okay. So just we are following the same procedure but for the 100th position. That means the third digit. Okay. So the output will be, now after placing these elements into a bucket, now we have to arrange the elements. So 0, 1 and 2, 0 and 1. So 3000, 45, 67, 42, 123, 456 and 3500. So this is the output after completion of 100th position. Now thousands position. Now we have to consider the thousands position, right? Right. Consider. So this is the input for the thousands position. Thousands position means fourth one. 3. So place in the third bucket. So 3000. Okay. Next 45. The fourth position is 0. So place here. Here also the fourth position is 0. Place here. And here the fourth position is 2. Place here. Fourth position is 0. (123). Again fourth position is 0. 456. The fourth position is 3. So 3. So 0, 1, 2, 3. 0, 1. Right? Now rearrange the elements from left to right. So it will be 45, 67, 123, 456, 2222, 3000 and 3500. See, if you observe, after So how many times we have repeated? 4 times. That means number of digits, right? The number of digits for a large number. So first we have to find the large number in that given elements. From that large number, first we have to find the number of digits, and that many times we have to repeat the process. So here there are 4 digit number. So 4 times we have to repeat the process. One is for ones position, tens position, hundreds position, and thousands position. And place the buckets 0 to 9 because any digit can be in between 0 and 9. So place the buckets from 0 to 9 and take the element, consider the position and place that element in the corresponding bucket, right? So we have repeated. After completion of all the elements, placing in all the buckets, then arrange the elements from left to right, and if one bucket consists of more than one element, follow the first in first out. So whatever the element we are pushing into the bucket, that element should be removed first, right? So here the same process we have applied, and after completion of 4 steps, 4 procedures, right? So we got the result. So this is, if you observe, this is the sorted list. So we have taken one elements and finally we got the sorted list. This is the sorted list, right? So hope you understood this one. So this is called a RADIX sort or a bucket sort. So we have to place all the buckets, and based upon the positions we have to place the element into the bucket. That's it. So the one important thing is, first we have to find the large number and number of bits. That's it. Based upon the number of bits we have to repeat the procedure, right? So in this session we'll go with one more sorting technique, that is shell sort. So coming to this shell sort, first we are supposed to find the difference and we are supposed to compare the elements based upon the difference, right? So first we have to find the gap or a difference. Second, compare the elements with the difference or a gap. So we have to compare all the elements, those are having the distance between this difference, right? Next, this is completely done for one iteration, and for every iteration we have to reduce the gap. Reduce the gap or a difference by gap by 2 or a difference by 2, right? And at last at some or after some iterations, gap or difference will be 1, so that apply insertion sort, or simply we can say this is a generalization of insertion sort. So we will follow the same procedure. How the insertion sort we have applied, the same thing we will apply for this shell sort also. So there in the insertion sort we are comparing the just adjacent elements, but here we have to find the difference and we have to apply the insertion sort with the gap of this particular difference. So let us go with an example so that if you are having any doubts, so it will be rectified, right? So we'll go with an example. So finally, this is a generalization for an insertion sort. Okay. So let us take an example. So consider a few elements: 60, 40, 10, 30, 50 and 20. Let it be, these are the elements. These are the elements. So the index values are 0, 1, 2, 3, 4 and 5. So total number of elements, are 6, right? Now we have to find the difference or a gap or a distance. We can call anything here, right? Distance is equal to number of elements by 2. Therefore, distance is equal to 6 by 2, which is 3. See, in the first pass, the distance is 3. So we have to compare all the elements which are within this distance. So let us take this index values and find the distance. So if you take the 0th index, what is the distance of what is the another element with the distance? It is a 3. So we have to compare these two. Compare these two, and if they are in a sorted order, nothing will be done. If they are not in a sorted order, just we have to make them in a sorted order. Just sorted order means just swapping. We will do the swap. Okay. See, 0 and 3. So this is the pass 1. In the pass 1, distance is equal to 3. Right. 0, 3. 0th element is 60. Third element is 30. So these two are not in ascending order. So just swap. So simply we can say 30, 40, 10, 60, 50 and 20. Right. Next, move the index value to 1. So within the distance 3, what is the next element to be compared? 1 plus 3, that means 4. So the first element and fourth element should be compared. So what is the first element? 40, fourth element 50. So both are, see here, let us write the indication so that, right. So these two are in already sorted order, so nothing will be done. So just write down the elements. Right. Next, move the index 2. So within the distance 3, it should be compared with 5. So 2 is compared with 5. See, again, here both are in a sorted order. So simply we can write 30, 40, 10, 60, 50 and 20. And move the index 3. What's the distance? What is the next index which we have to compare with these 3 indexes? 6. So this cannot be performed as we are not having the 6th index. The index last one is 5. We cannot compare it with the 6th index. So this ends our first pass. Next, coming to the second pass. So this is all about the pass 1. Coming to the pass 2, that means the second iteration we can call, right? So we have to reduce the gap. So this completely ends with the pass 1. That means we have compared all the elements which are within the distance 3. So 0th index element should be compared with the element which is having the distance 3. That means the third index. First index, fourth index, second index, fifth index, and third and sixth. So 6 is not available. So we have to stop comparing the elements. Now pass 2, we have to reduce the distance. So distance is equal to floor of distance by 2. That means floor of 3 by 2, which is nothing but 1, right? Which is nothing but 1. So here the distance is 1. That means we have to compare the the adjacent elements. See, now in pass 2, the elements are 30, 40, 10, 60, 50 and 20. Now compare each and every element. So this is nothing but our insertion sort, because the distance is 1. So 30 is compared with 40. 30 is compared with 40. So first this is compared. So it will be 30, 40, 10, 60, 50 and 20. Now compare 40, element 40. So 40 is compared with 30. Yes, true. So 30, 40, 10, 60, 50, 20. Now compare 10 with 40. So if you compare 10 with 40, 10 is less than 40. So 40 is moved here. Next, 10 is less than 30. So 30 is moved here and 10 is placed here. So 60, 50 and 20. Right? So you can observe after every iteration the elements are being sorted. So after first iteration the first element is in sorted order. Second iteration 2 elements are in sorted order. Third iteration 3 elements are in sorted order. Right? Now moving with the 60. Right. So 60 is greater than 40, 30, 10. So 10, 30, 40, 60, 50 and 20. Now compare 50. 50 is less than 60. So 60 will be placed here. And now 50 is greater than 40. So 50 is placed here, 40, 30 and 10 and 20. Now compare 20. So 20 is less than 60. So move 60 towards its right. So 20 is less than 50. 50 is moved towards here. 20 is less than 40. 20 is less than 30. 20 is greater than 10. So here we have to place. Right? So after completion of all the iterations, we got the elements in a sorted order. So this is nothing but our insertion sort. This is our insertion sort. Right? So one thing we have to remember, that in shelf sort we have to first apply the distance, and based upon the distance we have to compare all the elements. Right? So then at one step, at one iteration the distance will become 1, so that it is completely of insertion sort. This is also an insertion sort, but here the distance is 3. Here the distance is 1. Right? So hope you understood this one. So let us take one more example with a more number of elements, right? So that we can get a 3 passes. See, I will take more elements. Some 80, 50, 60, 30, 10, 20, 40, 70. So 0, 1, 2, 3, 4, 5, 6, 7. So total number of elements are 8 now. Total number of elements are 8. So 8 divided by 2, the distance is 4. So we are supposed to compare 0, 4. So 0th element and 4th element. Okay. So here it is not in sorted order. So swap. So 10, 50, 60, 30, 80, 20, 40 and 70. Next, move the index 1. With the distance 4, we should compare 1 and 4, 1 and 5. So compare 1 with 5. So again those are not in sorted order. So swap 10, 20, 60, 30, 80, 50, 40 and 70. Next, move the index value towards right. So 2 with the distance 4, we have to compare it with 6. So 2 should be compared with 6. So also backtrack, right? So 60 and 40. Again swap 20, 40, 30, 80, 50, 60 and 70. Next, 3 and 7. 3 and 7, right? So 3 and 7. Again swap. So 10, 20, 40. Sorry. There is no swap. No swap is required because 30 is less than 70. 80, 50, 60 and 70. See, after the pass 1, so again move the index value. So you have to check backward also. So this is a third position. So backside 4 distance there is no elements because the backside distance is only 3 elements. So we need not go for the backtracking. So if you increment this index value, that means the next phase 4th must be compared with the distance 4 means 8th element. So where there is no index of 8, so we just stop here for the first pass. So this is the pass 1. This is all about pass 1. Right, pass 1. Now in the pass 2, what we have to do? We have to reduce the distance. So distance is equal to the floor of distance by 2 is equal to floor of 4 by 2 is equal to 2. So in the second pass, we have to compare all the elements which are at the distance 2. So consider this the same thing. Consider the same thing. So 10, 20, 40, 30, 80, 50, 60 and 70. So consider the first one. Coming to the index 0, 0 should be compared with 2. So 0th index is compared with 2. So they are in sorted order. Simply write the elements. So 30, 80, 50, 60 and 70. Right. Next, 1 with compared with 3. 1 is compared with 3. Right. So again they are in sorted order. 10, 20, 40, 30, 80, 50, 60 and 70. Next, 2 is compared with the 4. Second element is compared with the 4. So this is compared with this one. Okay. So 10, 20. So they are in sorted order. 40, 30, 80, 50, 60 and 70. See again. Right. Okay. So also check for the backing. Okay, backtrack also we have to check. So next 3, 5. Third element is compared with 5. So this is the third element. This is the fifth element. It's compared. So again they are in sorted order. 10, 20, 40, 30, 80, 50, 60 and 70. Right. Now see. Again, the third element is compared with 1 because the distance of 3 and 1 is 2, right? So far we didn't get in such a situation, right? So we are applying the 3 and 5. We are comparing the 3 and 5. Okay, so if they are in a sorted order, we are not swapping, just we are writing here itself. And in the next time, we have to compare the third element with the first element because 3 and 1 is also having the distance 2. So if we have swapped the element, the swapped element, the element of third index will be changing, right? So we have to compare that third element with zeroth element because the distance is 2. That also we have to consider. So again, here let us take this one. We have to consider this one, right? So 3, 0. So already in sorted order 10, 20, 40, 30, 80, 50, 60 and 70, right? So next move the index to the next one, that is 4 to 3 to 1. Okay, yes, okay, right. Next, see 4 comma 6, the distance is 6. The index value 4 must be compared with the element 6. So fourth element, what is the fourth element? 80 is compared with 60. So here there is a swapping. It requires swapping, right? 40, 30, 60, 50, 80 and 70. Now the fourth element has been changed, right? So previously the fourth element is 80. Now fourth element is 60. So backtrack. Fourth element should be compared with second element. Fourth element is to be compared with second element. So they are already in sorted order. See 10, 20, 40, 30, 60, 50, 80 and 70. And again, see, second element should be compared with the first one. So 2, 1. Again they are in sorted order 10, 20, 40, 30, 60, 50, 80 and 70. Okay, hope you understood. We have to check for the backing also. So not only the forward, we have to check for the backward also. Now continue this one. So 10, 20, 40, 30, 60, 50, 80 and 70. So 0, 1, 2, 3, 4, 5, 6 and 7. Right. So after completion of this one, so next where we have stopped? The 4. We have stopped at 4. So now we have to compare the fifth with 7th. The fifth element with 7th element. Already in sorted order. So 10, 20, 40, 30, 60, 50, 80 and 70. Right? Okay. Now again compare. There is no swapping. So there is no value change at the fifth position. If the value is changed at the fifth position, we have to again compare the fifth position with the third position. And if there is any swapping, we have to compare again the third position with the first position, right? So likewise we have to backtrack also. So not only the forward thing, we have to also compare the backward distance, right? So next element is 6, 8, where the 8th index is not available. So just stop here the second pass. Just stop here the second pass. And now pass 3. What is the pass 3? Again we have to reduce the distance. So distance is equal to distance by 2. 2 by 2 is equal to 1. Right? Distance is equal to 1. So that is nothing but our insertion sort. See. So this is a pass 3. So first 10, 20, 40, 30, 60, 50, 80 and 70. So first 20 is compared. So 20 is greater than 10. So 10, 20, 40, 30, 60, 50, 80 and 70. Next 40 is compared. So 10, 20, 40, 30, 60, 50, 80 and 70. So this element should be compared with the leftmost elements, right? Now 30 should be compared with the leftmost elements. So 30 is small than 40. So 40 will be placed here, 30 will be here. So again 30 is compared with 20. So 30 is greater than. So 30 can be inserted here. Right, 50, 80 and 70. Now 60. So 60 is greater than 40, 60 is greater than 30, 60 is greater than 20, 60 is greater than 10. So no change. 10, 20, 30, 40, 60, 50, 80 and 70. So now 50 should be compared. 50 is smaller than 60. So 60 should be moved here. And 50 is greater than 40, greater than 30, greater than 20, greater than 10. So 50, 40, 30, 20 and 10 and 80 and 70. Now 80. So 80 is greater than all the elements. So simply we can write 10, 20, 30, 40, 50, 60, 80 and 70. Now 70 should be compared. So 70 is smaller than 80. So 80 should be written here. And 70 is greater than 60, 40, 50, 30, 10, 20. So 10, 20, 30, 40, 50, 60 and 70. So this is the final result after completion of first pass. This is the final result after completion of the first pass. Right? So hope you understood this one. So just we have to remember is first we have to find the number of elements and we have to find the gap or a distance or a difference. So based upon the distance we have to compare each element with the another element which is available at this particular distance. Starting from the index 0, if it is a 4, distance 4, 0th element must be compared with the 4 which is having the distance 4. Right? Next, first element. So just increment the indexes. So first element should be compared with the 5, second element should be compared with the 6, the third element should be compared with the 7. So if in the comparisons, if the elements are not in a sorted order, just we have to swap the elements. And then coming to the after completion of the first pass, in the second pass we are supposed to keep on reduce the distance. So in the distance again the distance should be divided with a half, that means divided by 2. So in the second pass we got the distance 2. So we have to compare every element which is available at the distance 2. So from the forward direction as well as in the backward direction. So from the forward direction, 0th element should be compared with the second where the distance is 2. So similarly 1 is compared with the 3, 2 is compared with the 4, 3 is compared with the 5. Similarly, so if 3 is compared with the 5, if third element and fifth element are not in sorted order, just we are swapping. So fifth element will be now third element. So third element and which is having the distance of 2 from first element, right? So first element from first element also, the third element will be having the distance 2. So we are supposed to calculate or we are supposed to compare the elements 3 and 1 also. So that's why we are specifying here, right? So 3 and 1. If there is no swapping, nothing will be done. If there is a swapping, we have to compare the 3 and 1 also. Okay, that's simply we call it as an insertion sort. We are applying the insertion sort, right? So normally insertion sort is applied for distance 1, and here we are applying the insertion sort for distance 2 and distance 4. So that's why we call it as a generalization for insertion sort. So we are supposed to compare all the previous elements and then we are finding the position of the element and we are inserting that element into its desired position. That we are doing in the insertion sort. The same thing we are doing in this shell sort also.